Now this section is about linked lists. So in this video, we will learn why we need linked list. So for covering the topic, I'll be discussing about these two things: problems with arrays and the difference between array and linked list. So first thing, problem with an array. Array is of a fixed size. Whenever you are creating an array, you have to mention the size, and later on you cannot increase or decrease the size of an array. So once created, it remains same. That is the problem. Why fixed size is the problem? See, unless we are sure that we are going to store some number of elements, if we know the size, the number of elements, then we can create an array of that particular size. If we don't know how many elements we are going to store during the runtime of a program, then we cannot decide the size of an array. If we take some random size, then that size may be either insufficient or it may be excess. For example, I am not sure how many elements I am going to store. So in the program, if I declare an array of size 10, then in this array I cannot store more than 10 elements. Suppose I have more than 10 elements during runtime, then I cannot store them. And if I am just having 2-3 elements, then a lot of space in that array will be wasted. So I'll take a larger size, 100. Now again, I cannot store the elements more than 100. So during runtime of a program, don't know how many elements will be required. See, one thing I'll make you clear. We are programmers. We write programs, applications. For whom? For users, people who use our programs. So people who use our programs will decide how many elements they are going to enter in our program. So there, what will be the list size or array size? We don't know. So at runtime, the list size will be decided. But at coding time or compile time, we have to give the size. This is the problem. So this is the problem with the array. Then next, let us see the difference between array and linked list. So I'll discuss more about array, then I'll come to linked list. Now, little bit of revision. We already know that we can create an array either inside stack or we can create it inside heap. So for creating an array inside stack, we say integer a size, some size. I'm taking a small size here. So this array will be created inside activation record of main function. So array of size 5 will be created there. Then if you want to create an array in heap, then we should take a pointer. So for pointer, I'll take the variable name as p. Then we should say new, whatever the size you want. So this size can be taken at runtime and mentioned here. That's the benefit. But directly I am writing here as an example. So pointer p will be available here, and an array of size 5 will be created inside heap. This pointer will be pointing on that one. So this is inside stack and this is inside heap. Now the benefit of an array is that all these locations will be contiguous. They will be side by side. So you can access them with index, that this is 0th element, first element, second, third and fourth element. So randomly you can reach on any element. So array, you imagine just like a bench. There is a bench of capacity 5 people can sit on that bench. So when you are making a bench, that time only decide what size you want, then that capacity is fixed. Now only those many people can sit on that bench. If more people, there is no space. If less people, then space is wasted. So this is like a bench. Now coming to linked list. Here what we want is, we don't want a fixed size bench like this array because we don't know the size. Who is using our program and what is his requirement, how many elements he is having, we don't know. Let him go on giving the elements, as many elements as he want. So let the user give as many elements as he want. Then we cannot go for an array. And one more thing, let the user add more elements and also remove the elements. So we want some data structure which should grow and reduce in size. So we want a variable size data structure. So for that, I'll just share the idea about linked list. So for that, we must create memory in heap during runtime. And we should use linking for making it as a linked list. So how? Let us see. I'm just sharing the idea here. See, for allocating memory inside heap, the array inside heap, we had taken a pointer. And with one pointer, I have allocated 5 spaces. With one pointer, I have allocated 5 spaces. Again, I made it like a bench. But now, I will take one pointer. Let me call it as first. I'll just keep a pointer with me. Now watch this carefully. I am sharing the idea of linked list. Not showing what is linked list, just sharing an idea. I have a pointer. Now I want to store one element, just one element. Then for this, allocate the space. And this pointer first will be pointing on this one. So that is for storing just one element. Let us say 8 is the element. So with this pointer, we can point only on one element. What about next? If I want more. So along with this element, we'll also allocate the space for a pointer to the next element. If there is any next element, it will be pointing on that one. So right now there is nothing, so let it be null. So that's it. We made a node. So first pointer was there. When we have allocated the memory for just one element, then we have allocated memory for element as well as pointer to the next one. Now we have one more pointer ready. If we want one more element, then again allocate the memory like this. Here you store the element. Then this will be pointing on this one. Like this pointer was pointing on this, so this pointer will be pointing on this node. So we can call that block as a node now. The next I have one more element, 12. So again create a node. Node will contain value 12 and the pointer to next. And this pointer will be pointing on this one. So there is no node beyond this one, so let it be null. So I am creating a node whenever I want to store an element. So it is just like, it is not a bench. Imagine that we have free space. Whoever want to come and sit, he should bring his chair. Now when the next person comes, the first person will link to that person. Then that will link to next person. So in this we are forming a chain or a links of chairs. And if anybody is leaving, he can take away chair with him. So whoever is coming in will bring a chair. So every element will bring its own memory and pointer to the next element. So together, element space and the pointer space together, we call it as node. So this is how we form a linked list inside heap. So now you can see that if suppose you want to remove 3, you can easily remove 3. This 8, instead of pointing on 3, this will be pointing on 12. That's easy, and you can remove this one. I'll bring it back as it is. Now suppose you want to bring some new element in between 3 and 12, then you can simply create a node. Let us say element 7. 7 will be pointing on 12 and 3 will be pointing on 7. Now if you start from here, you will go on 8, and from 8 you can go on 3, from 3 you can go on 7, 7 you can go on 12. So it's easy to insert something in between also by just changing links. So this data structure is more flexible than array, and the size can grow and size can reduce. And you can easily insert new elements or remove the existing elements from the linked list. So that's it. I have given the introduction. What does it mean by linked list? What does it mean by an array? So remember these points once again, that array is created inside stack, array is created inside heap using a pointer. And a linked list, there is no meaning of creating a linked list inside stack. We create linked list always inside heap. So dynamically we allocate the memory. For each element, memory is separately allocated. If element is removed, the memory is gone. So the size is variable. So in the next video, we will have the details of a linked list. This was just, I was sharing the idea about linked list. In this video, we'll learn details about linked list. What is a linked list? What is a node? Like nodes already I have shown you in the previous video. Then how to define the structure of a node and how to create a node, then how to access the contents of a node. We learn basic things about a linked list. So let us start with definition of a linked list. Let us define it, what it is. A linked list is a collection of nodes where each nodes contain data and pointer to next node. Data and pointer to next node. So linked list is a collection of nodes where each node contains data and pointer to next node. If you see this first node, its address is 200 and it is having data 8 and address 210. So this 210 is the address of this node. This is the first address of this node. So 210, this node is having data 3 and address 270. So this is the node whose address is 270. So every node is having data as well as link to next node. And first is a pointer which points on first node. We call this pointer name as first, or also we call it as head. Head is a pointer pointing to first node or head node. So this address is 200, so this is 200. And the address of pointer itself is 100. Now this linked list what I have shown you is similar to the one already we have discussed in the previous video, that linked list is created inside a heap, these nodes. And this first is a pointer pointing to that first node or head node. So the address of this pointer is 100. And these addresses, just I have taken them randomly. In real, when you create some memory in heap, that addresses may be in thousands. But for making it simple, I have taken the addresses in hundreds. So these are just random addresses. Now one thing you can observe, in an array, all the addresses are contiguous. They are side by side. If this is 200, then this will be 202, like that. But here you can see that this address is 200, so this is 210, and this is somewhere else, that is 270, and this is somewhere else at 300. So all those nodes will not be side by side. Then how the continuity is maintained? Through links, that is addresses. So this is about a linked list. Linked list is created in heap. So I will remove this, then we'll talk about how to define a node, how to create a node. Now let us see how we can define a node. For defining a node, we have to define two things: data and the pointer. Data may be any type like integer, float, double, or any other type you can take. Then pointer is which type? Pointer is pointing to a node, that is next node. This is a node. So what is this then? This is also node. So pointer is of node type. Node is having a pointer of node type. So it's a pointer of its own type. Now let us define the structure of a node. A node is containing two members. Here is data and here is a pointer to next node. Let us call it as next. So this is node structure. Node is having data and pointer to next node. Then in programming, how we can define this structure? So for that, we can use a C language structure, struct node. Struct node. What are the members? Data. This is of which type? It can be any type, integer, float, double, or any other structure. You can take anything you want. But usually for learning purpose, we use integer. So I will call it as integer data. Then what is this? Pointer. Pointer to what? Pointer to a node. Then what is this? This is also a node. So this pointer is a pointer of a type node. Means the pointer of a type same node. So here struct node, pointer name is next. That's all. This is there in the structure. Now you can see that a structure is having data as well as pointer of type structure node only. So it's having a pointer of its own type. So such a structure is called as self-referential structure. Self-referential structure. Self-referential structures are famous, they are used in linked lists. So yes, we can see that they are useful in linked list. For C language programming, we use a structure. For C++ programming also, we can use a structure. C++ also supports structure. What is the structure in C++? It is same as class. Then what is the difference between class and structure? In class, everything by default is private, and in structure, everything by default is public. So if you are doing C++, if we are writing C++ program, then there also we can define a node with a structure only, or else we can use a class also. Now next thing, what is the size of the structure? So on this side I will write down, see this is integer. So we are assuming every time that integer takes 2 bytes. So let us say this is taking 2 bytes. And what about pointer? See, in any compiler, if integer is taking 2 bytes, pointer will also take 2 bytes. If integer is taking 4 bytes, then pointer will also take 4 bytes. So this is also taking 2 bytes. Total how many bytes? These are 4 bytes. So the size of a node is 4 bytes. It means this node is occupying 4 bytes. So the first byte address is 200 and the next byte is 201, 202 and 203. These are 4 bytes. And this node is also consuming memory 2, 10, 11 and 212 and 213. So every node is consuming 4 bytes. But for a pointer, just we need first byte address. So we are writing only first byte addresses. This is the size of a node. Now next, let us see how to create such nodes, how these nodes are created and the link there. So linking part, creating a linked list, we'll see afterwards. First, let us see a basic thing, how a node is created. For creating a node, first of all, we need a pointer because nodes have to be created inside heap. So for that, we must already have a pointer. So I'll take a pointer. Struct node star P. I'm calling the pointer name as P. So when you declare any variable, this is a variable, pointer variable. So where the memory will be allocated? Inside stack. We know that this pointer is in stack. So anyway, I will just show it as a pointer. This is a pointer. Now I have to create node in heap. So for that, function in C language is malloc function. Malloc. How many bytes I need? Total 2 plus 2, 4 bytes I need. Now instead of giving that 4 bytes, I can even say what? Size of struct node. Struct node. This malloc function returns void type of pointer. So we have to typecast it of this type. So here I should write down struct node star. This is typecasting. So this is very lengthy code. This is very lengthy code. This is how we do it in C language. But in C++, it's very simple. Say P assign new node. This node. Node will be created. When we said new, it is created in heap. So we will avoid writing this lengthy code. I'll just remove it and I will keep this one. While writing the program, I may be typing this code. So we'll follow this code. P assign new node. A new node will be created. A node structure is defined with a data and next pointer. So this is data and this is next pointer. Suppose the address of this node is, for example, 500, then 500 is there inside P. So it means P is pointing on this node. This is how a node is created. So we have seen how to create a node. Then how to access the members of a node. I want to fill some data and here I want to write address as 0. So I will write the data here. For writing data, P is data, P arrow data. Like P is a pointer to a structure. So the structure members are accessed using arrow symbol operator. So I should say P's data, that is this one, assign with value some 10. So 10 is stored here. Then P's next assign with 0. So 0 means null, null is stored here. So that is not pointing anywhere. So this is how we can access the members of a structure. This is how a node can be created. Creating a node and accessing the members of a node. Let us learn few more important statements that are useful when we are accessing linked lists. So I'll remove these things and take some examples and I will show you. Let us take this example. I have few nodes, a linked list is there and pointer P is pointing on some node. And this node is having a pointer to the next node. And also I have one pointer Q. Let us see some syntaxes and understand their meaning. See, if I say Q assign P, what does it mean? Q assign P means whatever is there in P, that has to be stored in Q also. So whatever is there in P has to be stored in Q also. So Q will have the address 200. So this 200 is there, so it will also get 200, and Q will be pointing on the same node. This node is 200. So if I write P assign Q means Q will also point on the same node. This is the meaning. So two pointers pointing on the same node. Now let us look at next syntax. If I say Q assign P is next, what does it mean? Inside Q we want to store P is next. So what is P is next? This is P, its address is 200. Its next is here, that is 210. So this is 210, we want to save it in Q. So Q will be getting the value 210. So this is 210. So now where Q is pointing? Q is pointing on next node. So if you read it, let Q point on the next node of P. Let Q point on the next node of P. So P is next, assign Q. So on next node of P, Q will be pointing. Then one more statement. If I say P assign P is next, like we have already seen that let Q point on next node of P. So here, what is the meaning of this? Let P point on next node of P. P point on next node of P means P is 200 right now. P is next. P is next means this one. What is the value there? 210. So that 210, where it should be stored? It should be stored in P. So it means this value should be taken and kept inside P. So this becomes 210. So when that P is having 210 means P is no more pointing on this node, P is pointing on this node because this address node is 210. So this statement has made P move to next node. P has moved on to the next node. This is very useful statement, very much useful statement in linked list. Like if I have a pointer P that was pointing on some node, moving pointer to the next node, this is the code. P assign P is next. So P is next is stored again in P. So this 210 is stored in P. So P is pointing on next node. We will see few more statements. I'll just change the example. Then we will see few more statements on this one. Next, I have two examples. Pointer P not pointing anywhere. It is null. Address is 0. And the second one, pointer P is pointing on some node in a linked list. How to make P as null? We can write here 0, it will be null, or else we can write capital NULL for null. So either you say 0 or null. So both are same thing only. Now let us see these two examples. If pointer P is not pointing on any node, then it will have a value 0, address 0, that is null. If it is pointing on some node, then it will have some valid address. And that value will not be 0, it is non-zero. And if you know, in C++ programming, 0 means false and any other non-zero value is true. So if pointer P is not pointing on any node, then it is 0. 0 means it is false. And when it is pointing on some node, it will have non-zero value. That means it is true. Now let us see the conditions to check if a pointer P is pointing on some node or not. So if I write first condition, if P is equal to null. If I say P is equal to null. So out of these two cases, in which case this condition will be true? P is equal to null. In this case, it will be true. So this means this will be true if pointer P is not pointing on any node. It's not pointing anywhere. And second condition, if I write if P is equal to 0, then out of these two cases, which condition will be true? This will be true, that P is having 0, means P is not pointing on any node. If I write not P, in which case this condition will be true? P is 0. 0 means false. But not of 0 is true. Again, this condition is true in this case. So these are the three methods of checking if a pointer is not pointing on any node or not pointing anywhere. So yes, if pointer is null, then these three conditions are there. We can check if it is null or not. If it is null, then these conditions will be true. Now how to check these conditions? I have to just write inverse of these conditions. So I can say if P is not equal to null. Here P is null, but here not equal to null. Yes, this will be true. So this condition will be true if pointer P is pointing on some node of a linked list. Then another way of writing this one is P is not equal to 0. So just inverse of this condition. And even I can write if P, just P. So what is the value of P? 200. If 200, so 200 is true or false. So 200 means true. So if P means true, true means pointer is pointing on some node in a linked list. So these are few important conditions. Now I have one more conditions to show. So for that I'll remove this. Now one more condition. I want to know whether after node P, let us call this as node P because P is pointing here, there is some more node or not, or P is a last node. So let us see this. If P caps next, that is P is next, this one, is equals to null or 0. If this is 0, then this condition will be true. It means this is not pointing on any node. So if this is not pointing on any node, means this is the last node in a linked list. If suppose it's not pointing anywhere, then that will be last node in a linked list. Another condition, if P is next is not equal to null. So then when this condition will be true, if there is some address present here, means after this also there is some node or not. Usually we require to check this type of conditions. So these are a few important statements and conditions that are commonly used while working with linked list. So that's all in this video. Yeah, in this video we'll learn how to display a linked list. If already linked list is there, how to display all the elements of a linked list. So for this we should know how to traverse a linked list. Traversing. So traversing means visiting all the nodes of a linked list once. So let us see how to traverse. So for visiting all the nodes one by one, we must start from first node. So this pointer first will give the address of first node. We should not disturb pointer first. We should take one more temporary pointer and we should take the help of that pointer. So let us take one pointer P pointing on this first node. So its address is 200. This address is 200. So this should be 200. So how that can be done programmatically? Say struct node star P. So this is a pointer. This is a pointer. And this is having address 200 means it is same as first. So assigned with first. So with this line, P will be a pointer pointing upon same node where first is pointing. So we are on the first node. Then, as I said, traverse means visiting all. So let us move to the next node. How to move P to the next node? So in the previous video we saw how a pointer can move to next node. So P will take this address. This address is what? P is next. So P is next is what? 210. Give it to P. So this should become 210. So when this is given to P, it became 210 means where P is pointing now, it's not on this 200, it's pointing on this node, 210. So assign to P. So this means P have moved to next node. So I'll remove this. P have moved to next node. So in this way, I can again move to the next node and next node and next node. So I can go on doing this. So this means this should be done repeatedly in a loop. So I will use while loop. Now why while loop? Why not for loop? We don't know how many nodes are there. If you know how many times you have to repeat, you can go for loop. When you don't know, use while loop. So this has to be done in while loop. If we continue this, P will move to next node. Again repeat. So P will move to next node. So again repeat. P will move to next node. So if this is repeated again, P will move to next node. So what is the next node? Next node is null. Nothing is there. So P became what? P became 0. So when P became 0, we should stop. It means we have reached the end of a linked list. We have gone outside the linked list. So we should continue this as long as P is not 0. So it means we should stop when P is 0. Here we should mention the condition not for termination but for continuation. Termination is when P is equal to 0. Then continuation P not equal to 0. So here I can write the condition P not equal to 0. So yes, P was not 0, so it moved, not 0, moved, not 0, moved, not 0, moved, then it became 0, stop. So this loop will help us traverse entire linked list. Instead of 0, we can also say null. I have already shown you this condition. Even we can say while P for this one. So this is very important. Traversing the entire linked list, this loop and this statement. So P is a pointer that will take you through all the nodes one by one. This is very important. Now while traversing, we can do a lot of things. For example, displaying all the nodes, counting the nodes. Just as you are going on moving, add one, count 1, 2, 3. So you can count the nodes, or you can add all the elements, or you can search for an element, sort the element. All the operations can be done by traversing. So just one operation I will write here. This statement I will write next. P assign P is next. But before that I will say printf %d P caps data. So now let me read the code. See, first it will print the data and move the pointer. Pointer goes here. Again print the data, move to next node. Pointer goes here. Pointer is not null. Print the data and move to next node. So 7 it will print and move to next node. Then pointer is not null. Print the data, print 12 and move to next node. Continue. In this way, this will print entire linked list. So this is the code for displaying a linked list. I can even make it as a function. Let us call it as a function display, which takes this as a parameter. Now how to call this function? Call it as display by passing first pointer. You can call this function by passing first pointer. So this is for displaying a linked list. In this video, we'll write a C language program for creating and displaying linked list. So already on whiteboard, I have shown you how to display a linked list, but also I will write down a piece of function for creating a linked list. Then I will display it. I'll give the function name as ll display, that is for displaying a linked list. And it's going to be a C language program, so I'll select the language as C language, then next. So it has created a project and the main function is this one. I'll clear off these comments. Yeah, project is ready. So as we have discussed, for a linked list, we define a structure for a node. So I will first define a structure, that is node. And node contains data member and a pointer to itself, that is a self-referential pointer. So I will take data as an integer type and the pointer is of type node. So struct node pointer, and the pointer name we have taken as next. Our node structure is ready. Then for implementing a linked list, I need a pointer called first. So I will declare a pointer itself here only. This becomes a global pointer. It can be directly accessed or even I can pass it as a parameter. Then here for making display function work, first of all, I will create a linked list. So for creating a linked list inside the main function, I will create an array with some numbers 3, 5, 7, 10, 15. I have taken 5 elements and I want to create a linked list using these elements. So here I will write a function for creating a linked list. Void function and the function name is create, it will take array as a parameter and the number of elements in an array. Then using those elements, it will create a linked list. So I have already declared a first pointer here. Let us initialize that first pointer as null. Now in this create function, I will scan through this array and I will take one element at a time and I will create a node and form a linked list. So for forming a linked list, I need some variables. So I will take one variable I that is useful for scanning through that array, and also I will take a temporary pointer node t. This will help creating a new node. Then also take a pointer called last that will be pointing on the last node. It will help me to add a new node at the end of a linked list. Then as the linked list is empty right now, I will create the first node. So first assign, I'll create a new node using malloc function. So I will use typecasting, then malloc function. It will take size of struct node. It will create a new node and first will be pointing on that one. Then this first data, I will assign it as a of 0. That is the very first element I will give it. And first, next should be assigned as null because this is the first node. There is nothing beyond this one. And I will make last point on first node. Now first node is ready. Rest of the nodes, I will create them using for loop, iterating through the for loop and scanning through this array. So the first element, that is a of 0, I have created in first node, and first and the last two pointers are pointing there. Now inside for loop, for integer I assigned 1 onwards, I less than number of elements, then I plus plus. I am starting I from 1 onwards because already 0th element is created. Then every time I will create a new node by using malloc function. So same code I will write on struct node pointer, then malloc function and size of struct node. Then inside this t caps data, I will fill up the data of a of I. Then the t is next. There is no next node yet, so it should be made as null. Then the last node should point on t. Last next should be t. And last should move on new node t, and that t becomes a new node. That's all. This for loop, when it is iterating through all the elements of an array A, it will create an entire linked list. This create function, I'll be using it every time whenever I have to process upon a linked list. So whenever I want to create a linked list of some elements, I will create an array and I will pass it to this function. It will create an entire linked list. So right now, don't focus on how this creation logic is working. Just we will focus on display function. So come back to main function. Here I have created an array. Then I will call this function create. It will create a linked list. I will pass array and the number of elements are 5. So linked list is created. Now I'll give some gap here. Then here I will write a display function. So as we have discussed, I will write on a display function, that is iterative function. Void display. And to this, I will pass this first pointer. No doubt it can directly access it, but I will pass a pointer to this. So I will take a pointer p. Then the logic was simple. That is, while p is not equal to null, go on printing the elements. So printf percentile d, because the data type is integer, p's data. Then after that, move p to next node. That's it. This is the only thing that we have to focus on. But already we should have a linked list, so I have already created a linked list. Now after this, I will call a function display by passing first as a pointer. So that first pointer becomes a pointer p here. So p will be pointing on the first node, then this p will scan through the entire linked list and display all the elements. It will display the data and move to next node. Let us run the program and see if there are any errors. I will remove the errors. There is a warning here that malloc function needs a header file. So I will declare a header file here. So I will include a header file here, include stdlib.h. Now let us run it. This 3, 5, 7, 10, 15 is displayed by this display function. Let us debug this display function. So inside the main function, I'll put a breakpoint here and I will run it. You can watch here inside the window, that is watch window or debug area. This array is having these values and linked list, it is already created and the first node is having value 3 that is displayed here. And next is this one and the next value is a 5. And you can see the addresses of the first node is last 4 figures are 4E90. The next is 4CA0 and next is 2F90. And if I say next, then it is having value 7. The next is a pointer to the next node and that node is having value 10 and its address is next is FB0 and the last one is null. So you can see this null also at the bottom. So you can see that entire linked list, the nodes, their addresses and the data present in them, entire thing can be seen in this debug window. Now if I continue debugging, this display function should display all these values. So P will be scanning through this entire linked list. So it will be taking these values. That is 4E90, next will be 4CA0, next will be 2F90. Let us check it. I will continue execution. So you just watch how P will be changing. Now P will also appear inside this window like, yes, P is now at first node. So it's going to print 3. So it is inside while loop right now. So it's going to enter inside while loop right now. Next, it prints the data. Then next line P is going to move to the next node. You can see that the next node is 4C0A. Right now P value is 4E90. Then it will change to 4CA0. Yes, P became 4CA0. It is on the next node now. And there the data is 5 and the next node's address is 2590. Sorry. And the next node address is 2F90. Just watch this one. I don't have to read it out. Then print the data and P moves to 2F90. Now it is on 2F90 and the node is containing 7. 7 is printed. Then P moves to 2FA0. Yes, P is on 2FA0. The data is 10. 10 is printed. Now P moves to 2FB0. Yes, on 2FB0. Now the data is 15 and next is null. So it prints 15 and the next is null. So it stops. Now P is null. So it will stop and come out of this function. So display function ends. That's all. End of this function. So I have shown you the debug area also, how this P is changing the values and moving to next node every time. And you can see the entire linked list inside the heap available here. So that's all with this display function. Now I will write a recursive function for displaying a linked list. That is a traversing as well as displaying a linked list. So I'll remove this function and I'll write a recursive function here. Function name is display. It takes a parameter of type this node, structure node pointer. Let us call the pointer name as P and it is taking P as a pointer. So we'll be passing first as a pointer to this one. Then, as this is recursive, so we should write down base condition. Base condition may be for continuation or termination. So we will write the condition for continuation. So if that P is not a null, then we will print. If P is not equal to null, then print P's data, that is data inside each node. So printf P's data. After printing data, it should go to next node recursively. So display will call itself again by passing next node's pointer. So display P is next. That's all. Close the bracket and close this one. So this is a recursive function for displaying all the elements of a linked list one by one. So it is printing and calling itself and moving on to the next node. So for this example linked list, how it works, let us look at it. So if I am calling this upon first node pointer, that is first if I pass, suppose the call is display first, then let us see how it works. So I will trace that function and show you. This tracing is important because a lot of things that we can do upon linked list, and we can write down recursive functions also. So let us see the tracing. So first time when I call this function by passing first, that is the pointer of the first node, that is 200. So it will be called upon first, that is 200. I am not writing the complete function name display, I am just writing D, that is D for display. Let us see what it does. See, 200 is passed, 200 is not null, P is not null, P is 200. So that it will print and then it will call itself on next node. So first thing it does is, it will print 8, P is here, right, P is here. So it will print 8 and call itself upon next node, that is 210, this one. So display will be called upon 210. So I am generating a tracing tree. Simultaneously, I will also show you stack contents. Let us look at stack content also, because recursion uses stack. Suppose this is a stack, system stack. First time when I have called, the address was 200. So activation record is created and the pointer P is 200. And 200 is not null, so it has printed this 8 and it has called again itself for the next address, that is 210. So for the next call, again an activation record will be created and the pointer P will have the value 210. Now in this call, P is 210, P is not null, so it will print. So print the data present here, that is 3. And then next step is call itself again for P is next. So it will call again itself for next node, that is 270. So it will take this value actually, 270. So it will call itself for 270. And this is the address of this node. So whenever pointer is not null, it is performing these two steps. So focus on these two steps. Now D of 270 is called. Again a new activation record is created. So again a new activation record. This is a fresh call and the P value is 270. 270. Enter inside. P is not null. 270 is not null. It's not 0. Print the value. 270. This node is having value 7. Then second step, call itself for the next node. Call itself for the next node. So what is next here? 300. So 300. Call upon 300. This 300 is the address of the next node. So again there is a fresh call. So again a new activation record is created and the pointer P will have the address 300. Now in this call, P is a 300. 300 is not null. Then print. What is the value inside this one? 12. The next call to next node. Call to next node, D. So what is the address here? 350. 350 is passed. Now again it's a new call. So for new call, again an activation record is created. This time P value is 350. 350. Now fresh call. P is not null. 350 is not null. Then print. What is the value in 350? Address 350. I'll remove this. Value is 9. 9. Then next step is call itself on next. Call itself on next. That is 0. So it will call itself D upon 0. Now again a new call. That 0 is nothing but null. So again an activation record is created. And in this activation record, P value is 0. So again a fresh call. P is not equal to null. No, it is equal to null. P is equal to null. It will not enter inside. So P is equal to null means false. False means don't enter inside. Exit. So function exits. This function will terminate. This call will terminate without doing anything. Now, as this is recursion, when this call has terminated, its activation record is deleted. Then it will go back to the previous call. Previous call was for this node 9, this node. So the value was printed and it went on the next node also. So the printing was also done, it went on to the next node also, work is over. So this function has finished. So its activation record is deleted. It will go back. For this also, both the steps are over. So again, this work is completed. So its activation record is deleted, and likewise, all of them are deleted. So function is returning back. So the recursive calls are made one by one, and then it will go on returning back. So that's all about display function. Now let us analyze this one. We have already written a function using loop also, and that one and this one. First of all, how much time it takes? Time, what is the work it is doing? Printing, nothing else. Then, printing takes how much time? Constant time for one node. Then, how many times it is printing? Depends on number of nodes. So, what is the time taken? N times printing, time is N. So, the time is order of N, whether you use loop or recursion. So in the loop will repeat for n times, so it is order of n. But in recursion, the code is here, so it is printing and calling itself, printing and calling itself. So how much time it is taking? Print, call, print, call, print, call. So how many times printing is done and calling is done? Depends on number of nodes. So again, it is also order of n. So the time taken by this function is n. You can remember that if there is any procedure which is traversing the linked list once, then time will be order of n only. Then next, space. Loop function was a simple function. There was no extra space. But this is recursion that uses stack. So what is the size of the stack? 1, 2, 3, 4, 5, 6. How many nodes are there? 1, 2, 3, 4, 5. 5 nodes are there, but 6 activation records. Why? 1 for null also. So total 6 activation records are created. So total n plus 1 activation records are created. And if you count the calls also, 1, 2, 3, 4, 5, 6, n plus 1 calls. So one more thing, remember, if any procedure or a recursive function is written for traversing a linked list just once, then it will be making n plus 1 call for the entire linked list, and also the stack size will be n plus 1. So asymptotically, answer is order of n. It is order of n. So the space is also order of n and time is also order of n. So that's all about this function. Now I will make changes in this display function. It is printing, then calling itself recursively. I'll just change the order. First let it call recursively, then print. Then let us see what happens. Now this is a different function. First it is calling itself recursively, then printing the element in a node. So this is the first step and this is the second step. What happens if this change is made? Let us trace this one. And as it is recursive, it will also use a stack. So maybe I'll get the same stack. So I have not removed the stack. Let us trace that one and see how it works. First time when the function is called, it is called with address 200. So this is the first call. Yes, this is the first call. Activation record is created. 200, P is 200. P is not null. Yes, it is not null. Call itself again. What about printing? Afterwards, first of all, call itself again. So first it will make a new call upon next node. P is next. So what is the next node? 210. This address. See, it will take the address from this node only. So 210. And what about printing afterwards? So first let us finish this. Again a fresh call. P assigned 210. So P is 210. P is not null. Yes. Call again for the next node and printing afterwards. So again this will make a call upon next node, upon this next node, 270. So 270 and print afterwards. So likewise it will continue. It will call for 270 when it is called, then it will call again for 300. So again a new call for 300 and printing will be done afterwards. So for 300 it will call upon next node, that is 350 and printing will be done afterwards. Again it will call upon next node, that is null, and printing will be done afterwards. Now this is at the last. So P is 0. This not null condition fails because P is null. So it will not enter inside and terminates. So this function terminates. So its activation record is deleted. So this is over. Then it will go back to the previous call. In that previous call, it has finished first step, that is go to next node. But printing it has to do. So first step is completed, printing is remaining. So it will print now. So what is the value of this 350? 350 node is having value 9. 9 is printed. So this function is over, its activation record is deleted. It will go back to the previous call. For this, the node is 12, so it will print 12, its activation record is deleted. Go back for this node, print 7, its activation record is deleted. Go back for this node 210, its value is 3, 3 is printed, its activation record is deleted. Go back for this node 8, 8 is printed, activation record is deleted. So you can see that it is printing while returning. So what is the output? Output is 9, 12, 7, 3, 8. That is 9, 12, 7, 3, 8. So these are the values printed. So these values are in reverse. 9, 12, 7, 3, 8. Yes, it is displaying a linked list in reverse. See, the previous function was printing in the same order, but this is printing in reverse order. Only the difference is the printf was before the call. Now the printf is after the call. So the order has changed because it is printing while returning. Recursion will call itself again and again, and also it will return. So while returning, it is printing. So if you are doing anything at returning time, then it will be done in reverse. Then what about the time and the space taken by the function? That is same amount of time. For 5 nodes, 1, 2, 3, 4, 5, 6 calls are there, and the size of the stack is also 6. So it is taking same amount of space and time. So the time and the space is order of n only. So that's all about traversing and displaying linked list recursively. We'll see more operations on linked list. In this video, we'll look at a recursive function for displaying a linked list. So I'm using the previous project that already we have seen in the previous video. I have an array of elements and creating a linked list of these elements. How to create? Already I have written a function. This function will create a linked list. How it is working, you will come to know when coming videos. Then also we wrote a function for displaying. This was a iterative function. Below this, I will write a recursive function for display. So let us write a recursive function. It's a small function, void r display, and this will take a node structure as parameter p. Then as the logic we have already seen, that is if p is not equal to null, then printf %d space the value inside a node, that is data. Then call itself r display by passing p's next. That's all. It's a small function. And here inside main function, I will call this r display by passing pointer first. Let us run the program. It should display all the elements in the linked list. Yes, 3, 5, 7, 10, 15. Yes, these elements are displayed by this function. Let us debug this function and see how this recursive function is working and how the stack is utilized. I'll put a breakpoint. Now run the program. Here, as we have seen in the previous video, array and the entire linked list, you can see complete linked list is already there because the create function was already executed. Linked list is created. And here inside this debug panel, you can see the function calls, how the functions all are being made. The first function is main right now, and the number is 0 now. Then it will start calling r display and it will be go on calling itself. So this stack size will grow, and here also you can see how the value of p are changing. I will continue execution. Yes, it has reached r display. R display right now, p is upon first node. You can see that the data is 3. And here inside this debug panel, you can see r display is called. The next, it will display the element 3. Then it will call upon next node recursively. And you can see that this is the second call. And the pointer is now 77b0 and the data is 5. Continue. Print 5. Call itself upon next node. Now the node is having data 7. And here you can see there are 3 calls so far. So in this topmost call, it is here in if. And in the previous call, it has called itself from this line. So it is in this line. And the previous call also, it is in the same line. Now continue. Print 7. Go to next node. Print 10. Go to next node. Print 15 and go to next node. Now it is null. So inside this watch, you can see p value is null. Now it will start returning back. It will go back to the previous node. Just watch the data So it will be going back to previous node, that is 15. Yeah, go back to 15, then go back to 10. Here you can watch, then go back to 7, then go back to 5, then go back to 3 and end. So it has called itself again and again, and also it has returned back along those same nodes. So this is recursive display. Now I'll make one change here inside this recursive display. Instead of first print then display, I will remove this print and I will write it after recursive call. Then it should print the elements while returning. Function should print the elements while returning. Let us run. Yes, while returning, when it is printing, the elements are printed in reverse. First 15, 10, then 7, 5, 3. See, these elements are displayed in reverse. So that's it in this video. I have shown you recursive function. It is printing the elements in forward as well as in reverse. While returning in backward, it is displaying the same linked list. So I have shown you our display function, which is displaying the elements from left to right as well as from right to left, that is backward. It is printing them while returning. That's all. Now let us look at a function for counting the number of nodes in a linked list. That is knowing the length of a linked list. If I count the nodes, 1, 2, 3, 4, 5 nodes I have. So for this, we have to traverse through the linked list until we reach that last node, and every time we should go on counting. So with this way, we can know the number of nodes in a linked list. So I'll show you the working. I should have some variable, let us say count, and that count is initially 0. Then I should have a pointer p pointing on this first node whose address is 200. So this p will be 200. First step, increment count. So add 1 to it and move p to the next node. Then again do the same thing. Add 1 to count and move p to next node. Add 1 to count and move p to next node. Same way, add 1 to count, move p to next node. Add 1 to count and move p to next node. So this next node is 0, so it is null. So when p became null, stop that. So this is how the procedure is, and it is very simple. So we have to traverse through the linked list and go on incrementing count. So for this, I will write on a function. Let us make it as a function integer count, which takes parameter, that is struct node pointer p. Then for counting, I need some variable, let us say c, which is having value 0. Then in this c variable, I'll be incrementing, I'll be counting it. So every time, say c++ counting for incrementing this value, and move p to next node, p assign, p is next. And this procedure, I have to go on repeating it. So this should be written in a while loop. So while, what should be the condition? I should stop when p becomes null. So I should continue when p is not equal to null. So p is not equal to 0. So null can also be written as 0. Then at the end of loop, we will have the number of nodes in variable c. So return c. That's all. Now let us analyze the time taken by this function. See, this function is traversing through all the nodes and simply counting. So if I remove this line, then this is same as a traversing, which we have seen in the previous video. So how much time it takes for traversing all the nodes in a linked list? It depends on number of nodes. So if n nodes are there, then we say time is order of n. Time taken is order of n. So mostly the functions that are written upon linked lists, they will be taking order of n time. So we may not be analyzing it every time. So I'll just mention the time. So it's order of n. Then what about the space taken by this function? The space complexity depends on the number of variables or data members it is having. Like this is one pointer and an integer. That's all. Only two things are there. So pointer takes, let us say, 2 bytes, and integer also takes 2 bytes. Assume this. Total 4 bytes of memory is taking. So 4 bytes means 4 is constant. Time is n and space is constant. So we have finished the iterative version of count. Now let us write a recursive function for counting. So I will write the recursive function, then I will explain how it works. I will write the recursive function. Function name I am taking it as count only. Then it is taking a pointer. So we will be calling it by passing first node's pointer, that is 200. What it should do, if p is not null, it should count 1 for each node. And if it is null, then it should count 0. So I will write on the condition. If p is equals to null, then return 0. So if there is no node, then return 0. Otherwise, if there is a node, then return count itself for p's next and also add 1. That's all. This is the function. Simple steps are defined. If p is null, then return 0. There is no node. If there is a node, then call for next node and add 1. So let us quickly trace this one and see how it is working. So when we call this function for first node, that is 200, I am writing C for count. Then what it does, this is not null, so it will always go into the else part. It is not null, so it goes into the else part. So for almost all the nodes, it will be in else part only. So I will simply write down the steps one by one. So call itself for the next node, that is 210, and add 1. When to add 1? Not now, because unless this answer is known, we cannot add 1 to it. So 1 will not be added right now. The next call, C for next node, that is 270 and plus 1. This will be done afterwards. The next call, C for 300 and add 1. Adding 1 will be done afterwards. C of 350 and add 1. Adding 1 will be done afterwards. So for 350, C of 0 plus 1, adding 1 will be done afterwards. So you can see that in all these steps, it has entered into the else part only. Now P became null. So P is null. So when P is null, what it returns? It returns a 0. So this time this is 0. So the result of this function is 0. So this will be 0 plus 1 is 1. And the result of this function is 1. So this will be 1 plus 1, that is 2. So the result of this function is 2. So this is 2 plus 1 is 3. So result of this function is 3. See, when this function is called, so whatever the result that we get, return value will be the value of that function only. So this is 3. So this is 3 plus 1. So it will be 4. So the result of this function is 4. So 4 plus 1 is 5. So the result of this function is 5. So this is how it works. So we can observe that addition is being done at returning time. It is not done at calling time. Now I'll make one small change and show you. See, sometimes students believe that if I write return 1 plus count, instead of writing plus 1 afterwards, if I add first, then will it add while calling? No. See this one. For this also, C of 200, 1 plus with what? This function call, C of 210. So 1 will be added with the result of 210. So unless the result of 210 is known, addition cannot be done. So still this addition has to be done at returning time only. So I have done the tracing. Now if you see the time taken by this function is 1, 2, 3, 4, 5, 6 calls. So n plus 1 calls, so it is order of n. And the space, definitely it uses a stack because it is recursion. We have already seen in previous video how the stack is constructed. So the space complexity is n plus 1, that is order of n. So the time and space for this function is order of n only. So this function is costly in terms of space. In terms of time, it is same as the iterative function, that is using loop we have written the function, it is same as that, but in terms of space it is costly. Now I will make some changes in this function and show you what are the other ways I can write down same function. Let us see what are the changes we can do in the code, and the results remain same only. See, inside if, when we have return statement, then if this is true, it will return, so it will not go further. So no need of else. Without else also you can write it. Instead of writing this termination condition, I can write it in other way, like if p is not equal to null, that is not equal to 0, then return 1 plus count p caps next, else return 0. See, here I have written this condition first, so I was returning 0, otherwise this was there. But now I have just changed the order. If p is not null, then do this, otherwise do this. So you can change the order also. Now one more thing I'll show you. I'll write the function using some variable. I will declare some variable, local variable x, having value 0. If p means p is not null. You remember in one of the video I have shown you this one. This will be true if p is pointing on some node. If p is null, then it will be false. So this is for p pointing on some node that is not null. If it is not null, then x assign call count with next node. So we'll call this function and get the result in x. Then we will return x plus 1. So I have introduced one variable. See, earlier in the previous one, this was count p is next, then plus 1. So instead of writing count here, I have taken it in some variable, then that variable I am using here. So you can introduce a variable also. Next. Then else, if it is null, then return 0. So I will return 0. So see, if it is coming in else part means x is remaining 0 only. So even I can say return x, this means 0 only. So you can introduce a variable also. Now let us write a function for finding the sum of all these elements. I want to add all these elements one by one. 8 plus 3 plus 7 plus 12 and so on. So I don't have to explain much because already we have learned in the previous videos. Just we have to see the function. So let us write a function for adding all these values. So for adding, I should traverse all these nodes. So we know very well that we need a pointer for traversing all the nodes. That pointer should start from first node. So I will call the function name as add, and it takes a pointer to node type struct node star p. So this p must be first node. Let the return type be integer. So it means I am going to call this function by passing add first. So it will be taking a pointer to first node. P is a pointer to first node. Now what I should do here? I should traverse through all the nodes and go on adding the values. So for adding the values, I should have one variable. Let us call it as sum, and sum is 0. How to traverse all these? So using a loop, we have been doing this while p. So I can write like this. This means p not equal to null. And every time what I should do, sum assign sum plus p caps data or p's data. So I should add. First time 8 will be added to this one, and next time 3 will be added. So like that I want all of them to be added. So for that I should move p to the next node. P assign p is next. So if you remember in the previous examples also we have seen that while loop and this is statement p assign p is next. This will be making p move on all the nodes one by one. So it will help us to traverse the linked list. So what I am doing while traversing, just go on adding the data in sum. So I'll get the sum of all the elements in this variable sum. So finally return sum. The analysis of this function is same. It is order of n because it's visiting all the nodes just once. Now let me write down the same function for finding the sum of all the elements using recursion. I will call the function name as add, same function I am taking, and it's taking a parameter struct node pointer p. Then it should return integer result because all these elements are integer in our example. Now in the recursive method already we have seen in counting in the previous video, similar approach we have to take. So here I will write down the termination condition. If p is equal to 0, that is null, then return 0. So if it is null means we don't have to add anything. If p is null means nothing is there, there is no element. So 0. Otherwise, else, return, add function will call itself upon next node. So this is next node plus the data of the current node. So plus P is data. P is data. So this is a recursive function. It is similar to count function only, except instead of adding 1, here I am adding P is data. So data of every node will be added. In the count function it was adding 1 every time, but here it is adding data. So the working will be same, and already we are familiar with recursion. It uses stack. So it's going through all the nodes, so time is order of n, and the stack space is also order of n. So the time and space of this function is order of n. In this video, we will write few functions upon linked list, that is counting the number of nodes and finding the sum of all the elements in a linked list. And also we will write a function for search. So all these functions we can write them iterative as well as recursive. Already I have discussed these functions upon whiteboard, so just I have to write the code and give you a demonstration. So let us write first function for counting the number of nodes in a linked list. So here already I have an array of elements and I have already created a linked list. This is the same program which we have already seen in previous videos. This create function already I have explained in the beginning of this create function already I have explained in the previous videos. So this is the create function. So I am updating the same program. This is the create function. Here you can see. So I'm updating the same program. Already structure is already defined and the pointer first is also there. So I'm adding functions to the same program. So finally it becomes a single big program for the linked list. Now here I will write a function for counting number of nodes, that is finding length of a linked list. So function should return a length of a linked list. So the return type is integer, and let us call the function as count. Let it take a node pointer to the first node. So let us call pointer p as p. Let us call the pointer as p. And here for counting length or finding the length, I will take a variable L, and that is initially 0. Now the method is I should scan through the entire linked list and count the nodes until I reach the end of a linked list. So this can be done using a while loop. While p L plus plus, this will be counting, and move p to next node. That's all. At the end it should return L, that is length. So this is the function. And here inside main function I will simply call that function inside printf. Printf length is percentile d, and here I will call the function count by passing pointer first. That's all. I should get the length. Run the program. I should get the length. Total length is 5. Yes, it is 5. I'll just give a line gap and run it again and show you. New line. Okay, one more new line. Length is 5. Let us run it. Yes, I got a message that length is 5. Let us add a few more elements here. 8, 12, 20, and the number of elements are increased. Total 8 elements I have. Now I should get the length as 8. Yes, length is 8. So it's working perfect. Then next same thing I can write it as a recursive function. So just above main function I will write on a function called rCount. This should take a structure. This should take a structure node and pointer, that is pointer to the first node. Now as this is recursive, so already I have discussed you, as it is recursive, already we have seen the logic procedure for as it is recursive, so I should check if p is not equal to null, then it can call itself by counting and return rCount on p's next, and for each node add 1. Otherwise, return 0. That's all. Just few lines of codes for recursive count. So here inside the main function at this place, I will just modify this function as rcount. Now it will be calling this function, rcount function, and this rcount should return us length 8. Yes, it is returning. It's perfect. The next function we will see finding sum. I will write a function that is iterative function for finding sum. The return type should be integer and the function name is sum, and it should take struct node pointer upon first node, that is p. Now for finding sum, it should have a variable as I am taking as now for finding sum, I should have some variable, so I'll take s and initialize to 0. Now scan through the entire linked list, that is traverse through this linked list while p is not equal to null, and every time s plus assign p's data is added. So p moves to next node. That's all. Instead of displaying, we are adding them to variable s, and finally return s, that is sum of all the elements. And here I will remove this printf and I will write a function for finding sum. So printf sum is %d, then new line, comma, I will call the function sum by passing first. So I should get the sum of all the elements. So I have few elements here, 8 elements are there, so I should get the total sum value of all these elements. Let us run it. Yes, it seems it is 80. So yes, 80 is the sum of all these elements. Then let us look at recursive sum function. I will call it as rsum, and it takes struct node pointer to first node, and here inside this function I will check if p is equal to null, means p is not pointing on any node, return 0. Otherwise, return call rsum itself, that is on next node, and also add the data of node. Then that's all. The very simple function. Recursive function is just in 2-3 lines. It has finished. Now here instead of sum, I will call rsum. Now this will be calling this function. Let us run. I should get the same. Something is wrong here. rsum. Okay, s I wrote it as capital S. Yes. Let us run it. Yes, 80. It is displaying same. It is displaying same result. So that's all. We have seen count function, and count means that is number of nodes, that is length of a linked list, and recursive count, then we saw, so this was iterative count, then we saw recursive count, then sum, iterative sum, then also we have seen recursive sum. That's all in this video, and search we will look at it in the next video. Let us write a procedure for finding a maximum element in a linked list. So first I'll show you it's working, then I will write down a function for it. I want to find out maximum element. So I should traverse all these elements in a linked list. So I should take a pointer and let the pointer traverse through all these elements. So we know how to traverse. But for finding maximum, I should have some variable, let us say max. Then it should have some initial value. This max should have some initial value. To call something maximum, that is larger, you should have some small number so that the other number becomes larger than your number. So for this, what should be the initial value? So we should have some smallest number. So we can assign minimum integer. because all these values are integer only, so we should have a smallest integer. So I will assume that smallest integer is -32768 in a 16-bit integer, that is 2 bytes integer. So we are assuming integer takes 2 bytes, so in 2 bytes this is the smallest number we can write, -32768. So I have explained you that we must have some minimum value with us. Now any value other than this one is definitely greater because this is the smallest one we are having. Now see the procedure. First value 8, is it greater than this one? Yes. So change it to 8. The next value 3, is it greater than 8? No. Move to the next value. 7, is it greater than 8? No. Move to the next value. 12, is it greater than 8? Yes. Make it 12. Change it to 12. The next number 9, is it greater than 12? No. So largest number in the linked list is 12. So this how with every time we can compare the element with max, and if the element is greater than max, we will save it in max. Now the same simple procedure I will write down it as a function. Let us call the function name as max. It should take the parameter as first pointer. So instead of writing struct node, I'll just write node p. So struct is by default, we know we have to write. Then it should return a maximum integer. Now here we should have one variable m that should have -32768. So this is nothing but minimum integer. So any of this you can assign, either assign the value or say minimum integer. So you can assign minimum integer, but I am writing this smallest value based on 2-byte integer. Now we have to traverse through all the nodes and go on comparing the values with this m. I am taking the variable name as m now. So this traversing is done using loop. So while p, if p's data is greater than the value of m, then change the value of m to p's data and move p to next node. This will be moving p to the next node for traversing. And at the end, we will be having the smallest element in variable m, return m. This is the function for finding maximum of all the elements in a linked list. Now I will write on a recursive function for this one. So let us call the function name also max, and this takes node pointer p and it returns an integer. Now recursive function how we are writing is, for null condition, if p is null, return minimum integer, that is min int. If it is not null, then else part, here I will use a temporary variable and I will call this function on next node, p's next node. Already I have shown you this in one of the example that we can declare some variable and we can take the result in variable. Now whatever the result that we are getting, if this result is greater than p's data, then return this result x. Otherwise return p's data. So here we get the result in variable x, and that result is greater than p's data, that is data inside node, then we will return that result x, otherwise we will return p's data. So this is a recursive function. I will rewrite same function in a different way. Here I will show you. Same function I will rewrite again. Int max node star p, integer x, assign something. Even you can leave it uninitialized. P assign 0, return min int, return min int. As I said, if you already have written statement inside if, you don't need else. So simply I can write on those statement without else. X assign max of p's next. Then this comparison, if else, I can write on same thing using ternary operator. So simply write return if x is greater than p's data, return x, otherwise p's data. So this function looks simple, Just in few lines it has finished. It is not lengthy like this. So by using ternary operator, we can reduce the code. So if you are used to with this type of statements, then it will be very concise statement. Then it will be very easy to read than writing this lengthy if and else code. So this is a function for finding maximum. Now I don't have to explain how to find minimum. So for max we are checking for greater, for min we have to check it for smaller. Yeah, in this video we will see function for finding the maximum element from a linked list. So already we have a project on linked list, the same project I am continuing, and here I will write down a function for finding a maximum element. So as we have discussed on board, I will write down iterative version as well as recursive function. So first is iterative function. Let us call it as max, which takes a pointer to first node. Let the pointer name be p. So here I will take a variable for storing a maximum number. So the variable name is max, and I should initialize with some minimum integer, and our integer is 32-bit integer, so min int 32 min. So this is a built-in constant available in this compiler for C language, so I'm using that one. Depends on your compiler, you can take the value, otherwise you can set a minimum value like -32767 or -65535. The next is while p is not equal to null, we should continue. Every time check if p's data is greater than max. If so, we will modify max with p's data. So we'll store that data in max variable, and p should move to next element. So p assign p's next. That's all. By the end of this loop, we'll be getting a maximum element in a variable max. So we will return max. So this function I will call inside the main function, and directly I'll print its result. So max is percentile d and also /n, and here I will call a function max by passing pointer first, that is a pointer to a first node of a linked list. So already we have created this linked list with 8 elements. On the same linked list it will find out the maximum number. Here we have maximum number is 20. I'll try to change this one. I'll make it as 2. So now the largest number we have is 15. So we should get the answer 15. Let us run. Yes, we got the number as 15. If I change this to 25 and run it again, yes, maximum number is 25. Now similarly, you can implement a function for finding minimum by yourself. That's a student exercise. Now next, I will write on a recursive version for finding maximum element. So int, I will call it as rmax. It will take a structure node pointer p, and here I should have some variable of type integer which is initialized with a 0, and as per the code we have seen on board, so the same thing I am writing. If p is null, that is 0, I have return int 32 min. Otherwise we will call a function rmax by passing p's next, and whatever the value we receive, we compare and return the value. If x is greater than p's data, then return x, otherwise return p's data. That's all. This is the function already we have seen. I'll just give a line gap here. From here our function code starts, that is p is 0, then return minimum number. Otherwise call the function recursively and take the result in x, and if x is greater, return x, otherwise return p's data. So I will write it in next line. Now from here inside main function I will call rmax function, then I should get the same result, that is 25. Let us run. Yes, we got the value 25. I'll try to modify this. This is 12, so I'll make it as 32. Let us run. I should get the answer as 32. Yes, I got the answer as 32. So that's all in this video. We have written different functions for finding a maximum, that is iterative version as well as recursive version. Now let us look at searching in a linked list. We know two search procedures, that are linear search and binary search. Linear search is sequential, will check for the element one by one. Then binary search will work only on sorted list, and it will check in the middle of a list. If the element is found, it's okay. If it is small, it will check on the left side. Otherwise, it will check on the right side. We know this one. That procedure, binary search, we cannot perform upon linked list, because we cannot directly go in the middle of a linked list. We have to traverse from here. So traversing takes order of n time. We cannot reach in the middle in constant time. So that is the reason binary search is not suitable. So we'll look at only linear search. So let us understand linear search. For linear search, suppose I am searching for a key 12. Then how to search? Go on looking for the value 12 starting from the first node. Is it 12? No. Is it 12? No. Is it 12? No. Is it 12? Yes. Found. Stop. So it means I have to traverse the linked list and go on looking for the key element. So traversing, we know it is as simple as traversing. Just the thing is, if the key is found, stop there only. If suppose I am searching for a value that is 25, 25 is not here. So go on looking for it. It's not 25, not 25, not 25, end. So we reach the null value, so the key is not found. So directly let us write a function for searching. Let us call a function name as search, and this is taking struct node pointer p. So this should also take a key as parameter, the key that we are searching. We may be searching for a value 12 or we may be searching for a value 25, whatever it is, the key also we have to take parameter. So then, as I said, we have to traverse. So directly I will write on the code for traversing. So for traversing, we say while p is not equal to null, and every time we move p to next node. This is the code for traversing, going through all the nodes. Now while traversing, what I have to do? Check if key is equal to p's data. If on any node, if key is equal to data. Like suppose p is here. So check if key, that is, let us say it is 12. So is this 12 equal to p's data 8? No. So then move to next node. Then again check if this key is equal to p's data. No. So to move to next node. If it is equal, then what we should do? Return the address of that node p. Means suppose when p is here, now p is equal to data, key is equal to data. Then return p means we want the address of a node. Return type is node pointer. So this is for searching. And if the key is not found, then it will become null and come outside. So return null means key is not found. So this is the code for search. So this is the simplest function. I will write on a recursive version also. Directly I will write on node star, function name is search, same signature, same prototype, node and pointer, node, pointer and key. Now condition for null, if p is null means there is no node. There is no node means return null. Else do what? Check if key is equal to p's data. If data is matching, then return p. If it is not matching, then return call itself search. This is recursive. Search p is next and key also. First it will check if the data is matching with the key. It will return the address of a node. Otherwise it will call itself again upon next node. So we know very well how recursive function works. I don't have to trace this one and show you. So I have simply written the code. Now next, one more thing we have to learn. In linear search, we know that we can improve linear search. So for improving linear search, there are two methods. One is transposition, second one is move to head. We have already discussed this in arrays topic. In searching in an array, I have shown you there are two methods. For improving linear search, we have seen two methods, that is transposition and move to head. We have already learned this in arrays. So transposition, so this procedure is for improving so that next time when you search for the same key, it can be found in less time. So transposition was a method where we interchange the value with the previous value. So if suppose we are searching for 12, 12 should be brought here and 7 should be sent there. And the second method we saw that move to head means the key value should be brought in the beginning so that next time if you search for the same key, it is found just in one comparison. So here in linked list, which is suitable, transposition we don't do because we avoid movement of data in a linked list. We prefer movement of nodes. So it's better if we take out this node and add it into front, that is beginning of a linked list. We'll make it as a first node. So next time when we search, it can be found just in one comparison. So I will explain you how it can be done, and also I will write on the code. So let us look at the code for linear search along with move to head. Let us see if how to bring a search key in the beginning of a linked list. Suppose the key that we are searching is 12. This is the key. We want to bring this in the beginning of a linked list. So for this, what are the steps I have to perform? See, for searching, we have taken a pointer P, and this pointer P was moving forward and it was stopping here. When searching, P was stopping on the key node. Then we have to bring this node here. So for that, we have to modify which node? This node we have to modify anyway. Then we should modify this node also. This node is pointing on 12 node, that is node 7 is pointing on node 12. It should point on 9. So I have to modify previous node also. So for that, I should have a pointer on previous node also. Then how to get a pointer on previous node? In a linked list, we can get a pointer on next node. But how about previous node? So let us get a pointer on previous node. Let us see the procedure. Initially, when P is here, we should also have one more pointer Q, that is a following P. We will call it as a tail pointer. So we should also have one pointer Q. So Q is initially null. So Q is null and P is upon first node. So let us search using P for a key 12, and also let Q pointer follow P pointer. So first step. So let us see the steps. First, check P's data. Is it matching with the key? Key is matching with this one? No. So if it is not matching, then move Q here upon this node and move P to next node. Then again search. Is it matching? No. Then move Q to next node and move P to the next node. Now again check whether it is matching. No. Then bring Q pointer upon node P and move P to next node. Now it is matching. It is found. So that's how we can have a pointer Q following pointer P and stops before the key node. So this is the key found. Then we have to bring this into front. Let me write on the code up to here. Then I will show you what are the changes we require. Search function, which is taking a node pointer P and key. We should also have a pointer called Q, which should be initially null. Then we know well that using while loop, we will be searching while P is not equal to null. Check if key is equal to P's data. If it is equal, then we have stopped here. So what all we have to do, we will do it here. Otherwise, move Q on P. So move Q on P, then move P to next node. Move P to next node. P assign P is next. Then here return type is node star. Now I have the code ready. See, this is traversing, searching. If key found, then what we have to do, we will see now. If not found, then move Q on P and move P to next node. These are the two statements by which we have brought P on this node and Q on this node. Now key is found. What are the changes I have to make? I should make Q's next, this one. This is 300. It should point on P's next, that is 350, this one. So it should point on this one. So this address should change to 350. This address should change to 350. So what I should do? In Q's next, I should write down the address of P's next. So this is the statement. In Q's next, write P's next. So this link is changed. Now if you come from first node, after 8 it is 3, after 3 it is 7, after 7 it is 9. So this node is removed from linked list. Now this should be made as a first node. Then make it point on first node. So write the address here as 200. So P's next should be 200. So P's next is 200, this one. So who is having this address? First. So P's next is first. So this node will be pointing on first node. Then this becomes first node, P becomes first node. So you should bring first from here and make it point here. So directly I am writing here. So it should brought here. So first should be brought on P. So that became a first node. So that's what we want. We want to make that key node as head node. That is first node. Now this is first. First is having this address 300. Now from this node we can go on this node. Then this is sending us on this one. Then this is sending on this one. And this is sending on this one. So if I rearrange those nodes here, it looks like this. So who is first node? First node is this one, 12. I'll just write keys. Then 12 is pointing on whom? 8. Then 8 is pointing on whom? 3. Then 3 is pointing on whom? 7. Then 7 is pointing on which node? On whom? 9. 9. This is the arrangement. Though the nodes are at different places, but this has become a first node. Next time when you search for 12, it will be found in just one single comparison. Start from first, it is found. That's all. Stop. So all these things we should do. If Q is not null, we should do all these things. So these are the steps that we have to perform when we want to bring any node as a first node. Make that as first node. So the pointer first itself moves there and that becomes the first node. And that is pointing on the previously first node. The previously whichever was the first node, it will point there and the linked list continues. So this is move to front and an improvement in linear search. In this video, we will write a function for linear search, the one which we have already discussed. I will show you iterative version as well as recursive version, and also I will show you move to front operation after linear search. I am using the same program for a linked list which is having all the functions that we have already written. I am making it as a single large program for all the operations of a linked list. So here above the main function, I will write a function for linear search. Linear search function should return a structure type node. So this should be struct node, and let us call this function as L search, that is linear search, and it should take a pointer to a structure node, and let us call the pointer as P. And the next thing is the key that we want to search. Now inside the function we should scan through a linked list searching for a key value. So for that we can use a while loop, while P that is not equal to null, or we can just write while P and check if key is equal to P's data. If it is found, then return P. We will return a node. Otherwise, we will move P to next node. So it will be linearly searching, and whenever key is found, it will return that key node. At the end of the loop means it has reached the end of a loop means the key is not found, so we will return null, that is 0. That's all. This is a linear search function. Let us call this linear search function, that is L search function, inside main function. As the linear search function is returning a node, so I will declare a node pointer, that is temporary pointer I will take. Let us call it as a temp, and this should be of type struct node. And here inside temp, I will take the address returned by that function, so I will call function L search by passing pointer first and the key value that I want to search. So the key value that I want to search is 25. Let us send 25. Now this temp, if it is not null, means if temp means it is not null, then only I can print the result. So I will print the result, that is data is found, key is found at, and the key is so and so. So already we know the key, but still I will display the key. A message key is found is sufficient for us. If we have to process anything upon that key, then we can do it, but in our example just we want to know whether key is there or not there. If temp is null, then we will print key is not found. That's all. Let us run the program. See, key is found. That key is 25. I'll give /n here so that it comes in the next line. Now this time I will look for a key that is 17. 17 is not there in the list, so I should get a message key not found. Yes, key not found. If I give the value 7, then I should get a message key found and 7. Yes, key found and 7. That's it. This is working. So this is a iterative version of linear search. Then let us write a recursive version of linear search. Function should return a node type pointer, and let us call this function as R search, and it should take a parameter that is struct node that is pointed to a first node and also a key that we want to search. If P is null, means it is not pointing on any node, then return null, means the key is not found. Else it can return a recursive call to a next node that is P's data and also a key. That's it. If P is not null, then it should check if key is equal to P's data. If key is equal to P data, then it should return P. Otherwise, it should call itself recursively R search by sending P's next and also a key. So here also I will write return. That's all. This is a recursive version of linear search. Now instead of L search, I will call R search here, that is recursive search, and rest of the things are same inside main function. So I have just modified the function name, that is recursive search. I will be calling this function. Now I am searching for a key value 7. Let us see, I should get a message that key is found. Yes, key is found. If I give 27, key is not found. Yes, here is the message, key is not found. If I give 25, then key is found. Yes, I got a message that is key is found. So that's all. This is the demo for linear search using iteration as well as recursion. Now inside linear search, I have already discussed how we can perform move to front operation so that next time when we search for the same key, it can be done faster. So for that, I have to take one more temporary pointer, that is tail pointer, and let it be Q. And inside the loop, before moving P to the next node, I should move Q upon P. Already we have discussed the code, so just I am modifying based on that code. And inside F, if the key is found, then I should make that key node as a first node. So for that, I should say Q's next should point on P's next, and P's next should point on first node, and first should be moved upon P. See, first pointer is actually global. Here we have declared. So this function can directly modify this first. So these are the 3 steps by which we can move a node, key node, and make it as a first node, that is header node. Now let us try this and see. Here inside the main function, I will call LSearch function, that is iterative linear search function, which we have modified and made it as move to front. Now suppose I am searching for a key value 25, then after searching, when it is found, it should be brought as the first node. So for testing this one, I should call display function. So for testing this one, I should call display function by sending first pointer. I should get that 25 as the first element. Let us run this. Yes, key found 25, and if you look at the linked list now, 25 is the first node, that is before 3. Here I will try something. After performing linear search for 25, I will again perform linear search for one more key value by passing first, and I will also search for 8. Let us see what happens. See, first 25 should be brought as a first node, then again 8 should be brought as a first node. Then after these two search operation, I should get the keys as first 8, then 25, then after that I should have 3. Let us run. Yeah, here you can see that first is 8, then 25, then 3, then 5, 7, 10, 32, and 2. So this 8 and 25 are removed and they are brought as the first node. First time 25, then next is 8. So 8 is the latest first node. So next time if I search for 8, it will be found faster just in one comparison. So this is how we can improve linear search in a linked list by performing move to front. So these were few lines for performing move to front, and here it's giving a warning that queue is not initialized because here I have declared but not initialized, so it's guessing that it is not initialized, so it may cause any error. So we should initialize the variable. So if you initialize them, then this error will be gone. Anyway, it's not an issue. Our code is perfect because Q is initialized here. That compiler is unable to see that, so it's giving a warning. Or else we should remove this Q assign P and make it as a first statement. So it makes no difference whether it is done at this place or this place, makes no difference. So if I compile now, this error is gone. Yes, warning is gone. So that's all in this video. We have seen linear search and two versions of linear search, that is iterative as well as recursive. Then also we have seen move to front operation. Let us see how to insert a new node in an existing linked list. Here is an example. Already I have a linked list of 5 nodes. Then in this linked list, I want to insert a new node. For insertion, I should mention at what position I want to insert, at what index I want to insert. So there are no indices here. So let us give some indices to these nodes. Let us call this node as first node and this is second. So I have given indices. See, usually in arrays we start index from 0 onward. So that is given by the compiler itself. But here it's our wish. We can give the indices from 1 onwards also. Or if you want, you can change them to zeros also. Now inserting a new node. Let us see what are the places that are available where I can insert a new node. I can insert a new node before first node. Let us call this as one of the position. And next I can insert it in between these two or in between this and so on. And also I can insert a new node after the last node. Let us give indices for these positions. Let us call this as 0 because this is the first node before that position. Let us say this is 0, this is 1 and 2. So I have given indices from 0 to 5. So if I am inserting here, let us call this as index 0. I want to insert at index 0. Then if I say I want to insert at index 1 means after first node. If I say index 3 means after third node. Let us call it like this. I may want to insert a new node before first node, or I may want to insert a new node after a given position. Let us say fourth position. So I want to insert after fourth node. So let us take these as two cases of insertion. First case is inserting before first node. Second case is inserting after given position. So these are the two cases of insertion. So we look at first case. First one, inserting before first node. If you are inserting a new node before first node, then you have to move first pointer also because that new node becomes first node. Otherwise, inserting after any node, there is no change in first. Simply you can insert a new node at any given index. So we will handle these as two different cases. So let us look at first case, inserting before first node. Let us see the steps for inserting a new node before first node. So first step, create a new node. Let us take a new node with the help of a pointer. Let us say T. So first step is creating a new node. Then after creating a new node, initialize the node. Whatever the data you want to insert, insert that data. So let's say I want to store 10. This is the second step. Now this node should become a first node because it's getting inserted before first node. So this should point on this one. So this is the third step. Create a node, insert data and make it point on first. Then move first from here to this new node. First. So these are the steps. I'll just write those steps. So first step, creating a new node. For creating a new node, we need a pointer named as a T, node T, and directly here in single step, I will say new node. A new node will be created. Then in this place, I should write down data, that is T's data should be assigned with value 10. So T's data, assign it with some value, whatever the value is. So let us say there is some value in X. So I'm assigning that X. The next step, make T's next point on first. So T's next point on first. The next step is bring first on this new node T. So change first to T. So these are the 4 steps required for inserting a new node before first node. So steps are just 4. So there are constant steps. If you want to know the time complexity for inserting before first node, then the time is order of 1. So it means inserting a new node on this side of a linked list, that is left hand side of a linked list, takes constant time. Remember this. Now next, let us learn how to insert a new node at a given position. Let us insert a new node after position 4, that is index 4. So let us call position as 4 as example. So I am taking a variable, let us say POS position as 4. So I want to insert a new node after position 4. What are the things I have to do? First of all, I should create a new node. So for creating a new node, again take a temporary pointer and create a new node T and initialize with some data, whatever the data you want to insert. This is ready. Now what are the things I have to do? I have to make this T point on 6, that is node 5, and the node 4, that is 7, this node should point on T. So these are the two changes I have to make. So for modifying this one, I should know the address of this node 5, and to modify this one, I should have some pointer accessing this node. Like this node you can access because you have a pointer on this node. Now same way, there should be some pointer on this node, then only we can access that one or modify that one. For having a pointer there, I should bring a pointer from the first node onwards. I cannot directly get a pointer on this node. So let us take some pointer P and bring it till there. So let us take a pointer. Take a pointer P pointing on first node. This is pointing on same node. Now move P to next node here. So P assign P is next. Then one more time, P assign P is next. 2 times it is done. Then again P assign P is next. So P comes here. So in 3 steps P will come here. First step, second step, and 3 steps P will move there. So 3 times I should move P so that it comes on a node 4, so that I can insert a new node after that node. So it means if the position is 4, I should move P for 3 times. If suppose the position was 3, then P should move just 2 times. So P should move for position minus 1 times. So this is one step. Now I have to modify the links. So what are the links should be modified? T is next should point on this node. So how do you get the address of this node? That is P is next. Yes, T is next should point on the node whose address is present in P is next. So this is one step. Now last step, P is next, this one should point on T. That's all. Now if you start from first node, you can go to the next node, that is 3, the next node is 9, the next node is 7, the next node is 10, and next node is 6. So this 10 is inserted in between that node 4 and 5 or after node 4. These are the steps. Let me write down the code for doing this one. What was the first step? Create a new node. So for creating a new node, node T, and say new node, a node will be created in heap. The next step, I have written data here. So T's data is X, whatever the value you want. Then I brought a pointer P till here. So start P from first. So P starts from first and move P for how many times? It was 4, so we have moved for 3 times. So if it is position POS, then it should be position minus 1 times, POS minus 1 times. So go on moving P. So how to move P? P assign P is next. This is the method for moving P. And this step, I should perform it for position minus 1 times. So let us write a for loop for doing this. For I assign 0, I is less than position minus 1, like position is given here, I plus plus. This will bring P on that 4th node. Then after this, what are the steps? T is next should point on this one. So when at that time P was pointing here, if you remember. So T is next should point on P is next. So T is next should be pointing on P is next. So wherever P is next is, at same place let T also point on that one. Then change P is next to T. So modify P is next as T. That's all. So these are the steps. Creating a new node, filling the data, bringing P on that node, 4th node, then modifying links. Let us analyze this code. First thing, how many extra pointers required? 2 extra pointers. One for creating a new node T and one for changing links, modifying links. Without P we cannot insert it. So 2 extra pointers. Then second thing, how many links are modified? See, we modified, these are called as links, like These are pointers. Actually, this is also a pointer, but these pointers are meant for linking and these pointers are meant for accessing. So the pointers which are meant for accessing, we call them as pointers, and the pointers which are meant for holding the next node, we call them as link. So how many links are modified? One link and two links. So two links are modified in this one. Next, how much time it is taking? So all the steps are taking constant time, creating a new node, filling the data, modifying links. But who is taking more time? This moving P to that particular position takes more time. And the time for moving P depends on the position. So position may be nth position. So it is order of n. So the time taken by this procedure is order of n. Now one more thing in this one. So the time taken is order of n. That depends on the position. See, if I am inserting after last position, then it will take maximum time. What if I am inserting after first node? How much time it takes? So P will not move at all. P will remain on first node only. P will not move. So it will not take n time. It will take one time. So the time taken for insertion, minimum time is 1. Maximum time is order of n. So here I write down minimum time taken is 1, order of 1, and maximum time taken is order of n. So when it is 1, if you are inserting after first node here, because P will not move, we don't have to move P. And when it is n, if you are inserting after last node. So this is the analysis. Now one more thing. This code, I have taken an example for insertion after fourth node. Do you think it will work inserting after third node also? Yes. After second node also? Yes. After first node, if you have a doubt, let us check it. Then after last node, will this code work? Maybe. Let us verify. So let us verify whether this code will work for inserting after first node and inserting after last node. So I will remove few things and I will trace this code for inserting after first node and after last node, and let us check it. Let us see inserting after first node. First of all, create a new node with the help of pointer t. So create a new node. Then make t's data as x. Suppose I want to insert 10. The next is p on first, p on first. Then next is p will move for position minus 1 time. So what is the position here? Position is 1. So position is 1. 1 minus 1 time means 0 times. So it means this loop will not execute at all. P will not move. So P remains on the first node only. Then the next step is T's next is P's next. So T's next is P's next. So where P's next is? Second node. So it will point on second node. Then P's next is T. So P's next, which is pointing on second node, now it will point on this new node. Yes, it is working. Same steps are working. So if I start from first node, after 8 I will be going on 10, then 10 will send me on this node 3. So it's inserted. Let us verify whether it will insert after fifth position or not, means after last node. Now the position is 5, suppose. I want to insert after last node. Let us follow these steps and trace them and see whether it's working or not. First of all, create a new node with the help of pointer t. So with the help of pointer t, create a new node. Then fill data there. So okay, 10 is filled. Then P assign first. P is on first node. Then move P for position minus 1 time. This line is for moving P for position minus 1 time. So what is position? 5. So it has to move P for 4 times. 1, 2, 3, 4. So P comes here. So P is on the last node. Next step is T's next is P's next. So T's next should be same as P's next. What is P's next? Null. So it is null. Then P's next is T. So P's next is T. It's working. It has inserted a new node after last node. So if you start from here, 8 sends you on 3, 3 sends you on 9, 9 sends you on 7, 7 sends on 6, and 6 sends you on 10. And after 10, there is nothing. So this is inserting comfortably after the last node also. So this code is perfect for inserting anywhere in the linked list, but after a given position. But if you want to insert before first node, then the code is special. We have already seen this. Now I will combine these two things and write it as a single function for insertion. I will write on the code and just quickly explain you the code. I have written an insert function here. Let us quickly read this function. See, insert function is taking two parameters, at which position you want to insert and what is the value that you want to insert. Then we need a pointer first for the linked list also. Assume that it is a global variable. Pointer first is accessible to all the functions in a program, so this function can also access it. Now let us see what is happening inside a function. I am taking two pointers t and p that we require extra pointers. Then if position is 0 means we have to insert before first node. Then create a new node, insert data and make that new node point on first node and bring first on that new node. These are the steps already we have seen. So these are the steps that are required for inserting before first node. This work is over. Else, if the position is greater than 0 means any other position apart from 0, then we already know the steps. We have to take pointer p and bring it till a given position. For example, 4. So we have to bring it up to 4. So that movement of p I am doing it first. And while moving p, I am also checking whether p is not null or not. If p becomes null, it's useless. Stop. Means if there are only 5 nodes and I am giving index as a 10, so p has to stop after 5. It should not continue. Otherwise, it's a runtime error and the program will crash. So I am also checking whether p is pointing on some node or not. It should not be null. So it will stop if it has reached the exact position or p became null. So afterwards, here I am checking whether p is valid or not. It's pointing on some node or not. If it is pointing, then these are the steps. Creating a new node, assigning data, making new node point on next node of p, and then p is next pointing on t. These are steps already we have seen. So like this, we can write a single function for inserting anywhere in the linked list at a given position, starting from 0 up to the length of a linked list. So that's all about insertion. In this video, we will write a function for inserting a new element in a linked list. As we have already discussed, there are two cases of insertion, that is inserting before first node or inserting at any other given position. So I will write on a function for insert. And this is the same project that we are continuing. We have already written all the previous functions inside the same program. This is having all those functions. Now here above the main function, I will write down insert function. Void insert. This insert function should take pointer to a first node. So let us call it as p as a pointer to a first node. Then index at which we want to insert and the value that we want to insert. Now the first thing I have to check whether the index given is valid or not. Index will be valid if it is greater than or equal to 0 and less than or equal to length of a linked list. So for that, I will write on the condition here. If index is less than 0, then it means it is invalid. I cannot continue. Or if index is greater than length of a linked list, then it is invalid. Then how to know the length of a linked list? So for finding the length of a linked list, we should count the number of nodes. So for count, we already have a function present here. We have already written a function count, which takes pointer to a first node and it returns the length of a linked list, that is number of nodes in the linked list. We can use that function here. So back to this insert function, say if index is greater than count, and I should send the pointer to the first node, this is the pointer to a first node p. If it is greater, then the index is invalid, so I should just stop the function by saying return. Now we have checked for the validity of index. Then next is, if the index is valid, then we can insert a new node. For inserting a new node, I should first of all create a new node. So for creation, I will take a temporary pointer t. Then here, after this condition, I will create a new node. T assign struct node pointer, and malloc is a function for creating a new node in heap. So I should give the size of struct node. So it will create a new node. Then after creating a new node, I should fill the data in the node. So data assign x. Now the node is ready. Now next I have to link this new node, that is t, in the linked list. So there are two cases, that if the index is less than 0, then it should be on the left hand side of first. Otherwise, it should be at given position. So first I will check the condition if index is equal to 0. If it is equal to 0 means it should be inserted as a first node. So the procedure already we have seen that t's next should point on first and first should be pointing on t. That's it. These are the two steps for inserting a new node before first node. If index is not equal to 0, then we have to insert at some given position. So for that, I should move this pointer p to a given index, then insert an element. So for moving this, I need a for loop. So using for loop, I need a variable I. Now here, first of all, I should move the pointer for index -1 time. So for I assign 0, I is less than index -1 and I++. For these many times, pointer P should be moved. Then after that, I have to make necessary links for inserting a new node. So T's next should be P's next, then P's next should point on T. That's it. So these are the steps for insertion. So as I have explained you on whiteboard, I have written the entire code. Now extra thing here is I am checking whether the given index is valid or not. Now coming to the main function, we have already written a create function for creating a linked list for this given array of elements. I will remove few elements. I will just take 3 elements in this one. I have reduced the size so we can see it clearly how insert function is working. So there are 3 elements. This will create a linked list. So let us display this linked list, and afterwards I'll show you how we can insert the elements. Here it is displaying 3, 5, 7. Display function is displaying the linked list. So we have a linked list of elements 3, 5 and 7. Now let us try insert function. After create function, I will call insert, and I will send the pointer to a first node, that is first pointer, and I want to insert a new node at index 0 and the value is 10. Now after that I will display a linked list. So let us see whether this 10 gets inserted before 3 or not. Yes, it is getting inserted. 10, 3, 5 and 7. I will try with few more elements. The elements are 3, 5 and 7, so there are total 3 elements. So I will insert a new element 10 at index 3. So I have modified this index. It was 0. Now let us insert at 3. 3 means it should be inserted after 7. Let us check it. Yes, it is inserted after 7. 3, 5, 7, 0. Yes, it's working. Now I will try to give a invalid index. Instead of 3rd position, I will say insert at 8th position. Though I have only 3 elements, 8th position is not there, so it should not insert anything, and the linked list should remain same, that is 3, 5, 7. Yes, linked list is same, that is 3, 5, 7. 10 is not inserted because the index was invalid. So we have tried various positions for insert function. We have inserted at different locations. Now using the insert function, I will try to create an entire linked list. So I will remove these 2 lines. Let us directly use insert function for inserting various nodes. See, the very first node that I can insert is I can insert at index 0 because there is nothing in the linked list. If it is not index 0, if I give some other index, then let us see what happens. See, there is nothing to display because there are no nodes at all. Now let me insert this at index 0 and run the program. Yes, one element is inserted. I have inserted one element at index 0, then I have displayed it. So yes, it is inserting because 0 is the valid index. I cannot insert at any other index because the linked list is empty. I can insert only at index 0. Now the next element I can insert it at index 0 as well as 1. So I will insert it at index 1 and I will insert value 20. Then next I can insert an element. Now already I have 2 nodes, so I have 3 indices available, that is 0, 1 or 2. So I will insert it at 2 and I will insert the element 30. Let us run. I should get the elements 10, 20 and 30. Yes, I got the element 10, 20 and 30. Now next I will insert an element at index 0, that is 5. This is before first node, that is 10. Let us run this. Yes, 5 is inserted before 10, so the elements are 5, 10, 20, 30. That's it. So it means even using insert function, I can create a linked list. I can call insert function one by one and I can insert various elements in a linked list. So this is a method I can use for creating an entire linked list. That's all with display function. Let us create a linked list. Pointer first is null. There is nothing. So I want to insert first node. So say insert, I want to insert 8. I can insert only at index 0 because there are no nodes in the linked list. So the first value that will be inserted in the linked list will be 8 and is null. So this function, insert function, will create a node like this. The next, I will insert one more. Now what are the options I have? 2 options. I can say 0, a node will be inserted here. 1 means inserted here because this is one node. I can insert at 0 also, 1 also. So I will insert at 1, index 1, and the value is 3. So a new node 3 will be inserted here. And this will be linked with this one. Now I have 2 nodes. So I have 3 places to insert, 0, 1 and 2. So I'll insert a new node 6 at index 0, 1, 2. So I will insert it at 2. So 6 will be inserted here. This is third node. Now I will insert one node, insert at index 0, I will insert 5. So this 5 will be inserted here. This will be pointing on this one. So first we'll move on to this node now. So far first was pointing here. Now this became first node and this is second and third and fourth. Now what are the possible indices? 0, 1, 2, 3, 4. Now I'll insert a new element at index 3, value 9. So it means I want to insert here. So 9 will be inserted here. This will point on this one and this will point here. So by using this function, we can create a linked list. The way how I have shown you, you have to mention the first one must be 0, then always make sure you are giving valid indices. So by using this operation, once we have created a linked list, then we can perform all other operations on a linked list like counting the nodes or adding all the elements, searching, reversing, all those things that we can do once we have a linked list with us. So this is the basic operation that we need, creating a linked list. Now I have one more method for creating a linked list. So first I'll show you how we can create a linked list, then I will write on the code. Now next method, see, this is a present linked list with 3 nodes. Now I want to insert new nodes in this one. Where I want to insert, I can insert anywhere. But suppose always I want to insert at the end of a linked list. That a new value that I want to insert is 9 and I want it to be inserted here. So we know very well that for inserting a new node at the last, we should take a pointer and traverse till here, then we can insert a node. But when you are repeatedly inserting at the last only, then one suggestion is we can maintain one pointer called last upon the last node. That will help us inserting. How? Let us see. I want to insert a new value that is 7. So using a pointer, create a new node, insert the value, make this as null. Then last next should point on this one and the last should move on to the new node. This is how we can insert a new node. Let me insert one more node and show you. I want to insert one more node that is 15. So create a new node with a temporary pointer t, insert the value 15, make this as null, make last next point on this one and move last to new node. So in this way you can go on inserting at the last. So with the help of pointer last, we can insert it at the end of a linked list in just constant time because we don't have to traverse the linked list. This is possible if you are always inserting at the last. Then let me show it from the beginning. Suppose I have just one node, 8. Then where first is, this is the first node, so first will be here. Then where last should be, last should also be on the same node. So if there is only one node, then both first and last should point on that same node. So this is a special case that we have to handle. Now let us add something to this. Create a new node with a temporary pointer t and insert the value, make this as null. Now last next should point on this t and bring last on the new node t. Now one more case I will show you. If suppose there are no nodes, then both first and last should be null. When there are no nodes, initially they must be null. Yes. So when we are creating first node using a temporary pointer t and inserting a value, then that time we should bring first upon this node as well as last upon this node. So this is the special case that we have to take care, that make both first and last point on that new node. Then afterwards you can go on creating the nodes and with the help of last pointer. So let me write down the code for doing all this. Now I will write down a function called insert last. Insert last. So let us call the function as insert last. So insert last means it will not ask where to insert it, right? So just it will take the value that we want to insert. So let it take the value x. Now this function will insert a new node in a linked list that is at the last. So let us see how we can do this one. First of all, create a new node with the help of temporary pointer t. Okay, node t assign new node. New node is created. Then assign the value x here, whatever the value that you are sending. So t's data should be x and make t's next as null. So t's next as null. So this is null. So a new node is ready. New node is ready. Now we have to look at the cases. Are there any nodes in the linked list, or linked list is empty? There are no nodes. How we can know that? If first or last both any one of them is null, then it means there are no nodes. This is the first node. So let us check that condition. If first, that is pointer first, is equal to null, means there are no nodes in the linked list, then make first as well as last as a new node T. So it means I will create it here separately. Suppose this is the first node, then both first will come here as well as last will come here. So this is the situation we have handled if the linked list was already empty. Otherwise, the repeating steps. So always what we were doing. So what we were doing, make last next point on T. Make last next point on T. Then move last to new node. Move last to new node T. This is a function. This is the insert function which will always insert at the last, and it will always insert a node. There are no positions, so there is no question of invalid position. Always it will insert a node at the end of a linked list. If there are no nodes in a linked list, then it will make that as first node of a linked list. Otherwise, it will insert at the last. I will write down few function calls for creating this linked list. I'll just write the calls here. So first call, I will say insert last 8. So this is the first node 8. So both first and last will be pointing here. This is the first one. No doubt T is helping here, but I am not showing T here in picture. Then again say insert last, value is 3. So 3 will be created here, and this will be pointing on this one, and last will be on this one. Then again say insert last 9. So 9 will be created, 3 will be pointing on this one, and this becomes a last node. So in this way you can go on calling this function as long as you want to insert the element. As many elements you want, you can insert by calling this function. This function is for just inserting one node at the end of a linked list. And it works even the linked list is empty. So it always guarantees to insert some node in a linked list. There are no invalid indices because we are always inserting at the last. So by using this procedure, we can create a linked list, and then we can perform all other operations on linked list, like adding all the nodes, finding maximum, reversing a linked list, and so on. So I'll be using this function in my program for creating linked list. Let us see how to insert a new node in a sorted list at a sorted position. So what does it mean? If you look at this linked list, it is sorted 3, 7, 9, 15, 20. So all these keys are sorted, the elements are sorted. Suppose I want to insert a new element, that is 18. Then where it should come? This 18 should come after 15 or before 20. So it should be after 15. So inserting a new element in a sorted list at a sorted position. So this should be the position. If suppose I want to insert 10, where it should come? It should come in between 9 and 15, means after 9, before 15. Let us see how to do this. What should be the procedure? So let us take an example of key 18 and try to insert it in this sorted list. So the first thing, we will try to find out the position where this 18 should be inserted. So for that, we'll take up help of a pointer. Let us take P upon this node and start finding the position for this particular element. So how to find the position? The element here is 3 and this is 18. So 3 is smaller than 18. So move to the next node. Come on to this one. And the 7 is smaller than 18. So 18 will come after this one. So yes, move P to the next node. And this is 9. 9 is smaller than 18. 18 should come after 9. So move pointer P to next node. And this is 15 and this is 18. 15 is smaller than 18. So 18 should come after that one. Move. This is 20. So 18 should come before that, 20. So we found an element which is greater than 18. So it means we found a position where we have to insert this 18. It should come before that node. So this key should be inserted after node 15, before P. Now for inserting before P, before this node, I have to modify this node, but I don't have any pointer on that one. Then what I should do? So let us start again. For bringing a pointer here, what I should do? Start P again from here, and we will take a tailing pointer or following pointer. One pointer will be following P. So let us take one more pointer Q, that is null. I am restarting the steps once again. Check this value 3 and this is 18. 3 is smaller. So if 3 is smaller, bring Q here and move P to next node. Then 7 is smaller than 18. So 18 will come after this one. So move Q upon P and move P to next node. Then 9, that is smaller than 18. So 18 should be after this one. So still we did not find the position. Okay, move Q, move P. Then again move Q and move P. So yes, we got an element which is greater than 18. So this means 18 should come before that 20, that is P. So who will help this 18 to join in this linked list at this place? Q will help. So first of all, you have to find out the position where this key has to be inserted. So for that, we can take the help of 2 pointers. Even it can be done using single pointer also, but I am using 2 pointers here. So Q will finally help this new node to get inserted. So what are the steps that are required for creating a new node and inserting it there? So create a new node with a T and insert value 18. Then make it point on T's next should point on Q's next, and the Q's next should point here. That's all. These are the steps. Let me write down the code for doing all these things. I will not write the complete executable function. Just I will write down the steps that are used for inserting this node. First of all, we need a pointer P upon first node. I'm not declaring P. And we need Q, which is null. Then P should start searching for an element that is greater than X. While P and also means P is not null, and also P's data is less than X. Go on searching for an element until you get this one or P becomes null. Then each step, what is happening? Q will come upon P and P will move on to next node. So this is how P and Q are moving further. So P will stop, either it finds an element greater than this one or P becomes null. So if P becomes null, it will go outside the linked list and Q will be on the last node. After this, create a new node, insert the data and perform linking. So T assign new node, create a new node, and T's data assign X. So a new node is created and the data is written in this one. Now we have to perform 2 links, that is T's next should point on Q's next. See, earlier Q was pointing there, right here. So T's next should be Q's next. And then Q's next should be T. So T's next is Q's next, then Q's next is T. So these are the steps for inserting a node in a sorted list. Now a little bit analysis. How many extra pointers required? 3. Can we do it using just 2 pointers? Yes. T for new node, and with the P we can do it. So P should stand here and check the next node instead of checking the current node. With that way you can do it. So you can try that one. I am taking 3 pointers. Smoothly everything is working. Then how much time it is taking? So the time spent for creating a new node and performing links is constant. But bringing P and Q at these positions, it will take order of n time they have to traverse. And that traversing may be as minimum as 1, as maximum as n. So if I am inserting suppose 5, that will get inserted here. If I am inserting 25, then they will move till the end. So minimum time is order of 1 and maximum time is order of n. Now one thing is missing in this code. If I am giving a key that is X value that is smaller than first, then what? So I should first check if the value is smaller than first. If so, insert it on the left hand side. So that code I did not write and those conditions we did not check here. If suppose it is smaller, we should insert it before first. So That piece of code I will write on when I write the program. So that's all about inserting in a sorted position. In this video, we will look at a function for inserting a new node in a sorted linked list. Here I am using the same project. Already we have written so many functions upon linked lists. Now we will write a function for inserting in a sorted linked list. So already I have a linked list created here. Inside the main function, I have an array of elements, and create function is creating a linked list out of those 5 elements. Now above the main function, I will write on a function for inserting in a sorted list. So I will call the function name as sorted insert, and it will take parameters that is pointed to first node, p is a pointer to first node, then the element that we want to insert. Now what all the variables required, I will be declaring them, but first of all I need a variable for creating a new node. So I will take a pointer for creating a new node, t, and also we need a tailing pointer that will be following pointer p. So I will take q, and that is initialized to null initially. Now this element will be definitely get inserted in a linked list. So as it's going to be inserted for sure, I will create a new node. T assign struct node pointer, and using malloc function I will create a new node size of struct node. A node is created, and I will also set the data in this node. Data is also set. And I will also set the next pointer also null, so this will complete the work of creating and initializing a node. Now we can deal with the rest of the things. Now we have to check for some special cases here that I did not discuss on whiteboard. The very first thing is it a first node created? If this is the first node, then already pointer first will be null. That is, p will be null. We can say p is null, or I can use global variable first and check whether it is null. Then if it is the very first node, then I should make first point on t. This is the first special case. Then else, if it is not a first node, then we have to insert it in a sorted position. So for that, we use a loop for iterating through a linked list for finding a position. So I will write on that loop while p and p's data is less than x, and every time q will move upon p and p will move to next node. This we have already seen. And once we have reached a node whose data is greater than or equal to x, then there will stop and insert a node. Now again, this is a special case. The place where we have stopped, is it the first node? If it is the first node, then the new node will be inserted on the left hand side. So I should check the condition that if p is equal to first, then I should insert a new node before first node. So for that, I should say t's next should be equal to first, and first should point on t. If p is not first, then I can insert a new node between p and q pointers, taking the help of q pointers. So t's next should be same as q's next, and q's next should point on t. That's it. So on whiteboard, I have shown you only these things, that is taking a following pointer and moving p and q and then linking them. But here we have to deal with the special case also. If the element that we are inserting is the smallest, then it will come before the first node. So if p is staying upon the first node only, then we have to insert a new node before first node. And above this, initially if there is no node at all, then t should be a very first node. So two special cases, I have handled them here. So this makes a complete program or complete function for inserting in a sorted list. Let us run the program and display the linked list here. Inside the main function, I will call display function for displaying a linked list. So right now I have only 5 elements, that is 10 to 50. Then it should display all those elements. Let us run and see. Yes, 10 to 50 elements are displayed. After display function, I will also give a new line so that I can clearly see the output. Now, before display function, I will call sorted insert. Now, sorted insert, I will give an element that is 35. So it should come in between this 30 and 40. Then after that, anyway, I am displaying a linked list. So I should get the elements 10, 20, 30, 35, 40 and 50. Here also, I should send a pointer first as a parameter. Then 35 is the element. So let us see output. Yes, I got the elements 10, 20, 30, 35, 40, 50. Yes, it is inserting it properly. Then I will insert an element just 5, so it should be inserted before 10. Yes, it's working. 5 is inserted before 10. I will insert a new element that is 55 that should be inserted after 50. Yes, this is also working. 55 is inserted after 50. Now let us do one thing. I will make this as comment, so there is no linked list at all. Then I am inserting the very first element, that is 55. So 55 will become the very first element. There is no linked list at all. The first is null. So when I display, I should get the element 55. Yes, I got it. So even if the linked list is empty, there is nothing, and first is null, then also it is inserting. Then after that, I will call it for one more time first, and I will give the value that is 25. So 25 should come before 55. Yes, 25 and 55. Yes, it is working perfectly. So that's all in this video. We have seen how to insert an element in a sorted linked list. And apart from the discussion upon whiteboard, we have written the code for two extra cases, that is if the linked list is already empty or the new element is going to be inserted before the first node. So practice this program, and even you can find a PDF below this video. Let us look at a delete operation, that is deleting a particular node from a linked list. So for deleting a node, there are two cases. First one is deleting first node, and second one is deleting a node at a given position. So in the linked list, first is a pointer pointing on the first node. So if you are deleting first node, that is a special case, because if this node is gone, then the next node should become first node. That is the extra thing that we have to take care when we are deleting first node. Then deleting any other node, suppose I want to delete fourth node, then simply delete the node, first will not be disturbed. First remains on the same node. Let us look at case 1, deleting first node. How to delete first node? Deleting first node. So for deleting first node, we should move this pointer first to the next node. If suppose I am simply moving the pointer here on the first node, then this becomes the first node. Now when first is moved here, our linked list starts from here. So if you go to first, it gives the address of this node. Then you can access all these nodes one by one. Then what about this node? There is no first pointer here, so this node is not reachable. You cannot go to this node at all. Nobody is having this address. So this node became useless, but it is still there in the main memory. So now listen, very important thing. Whenever you are deleting a node, make sure that you are deallocating the memory for that node also. Because when we are creating a node, we are saying new and creating a new node in heap. This is how we are creating a new node in heap. Then we should also say delete for deleting a node. That is allocation from heap and deallocation from heap. So when a node is not in use, it must be deleted. Now let us see how to delete first node. I'll bring back first on the node 8. Now we have to delete this node. For deleting this node, first should move to the next node. Then who should delete this node physically from the heap? Who should use delete on this one? So for deleting this node, we will take one pointer P on first node. Take a pointer P on first node. Then move first to next node. Now our linked list starts from here. This is the starting point of our linked list. This is no more a part of linked list. Then delete this node from the main memory. That's it. So by using first, we cannot delete it, because if we delete, we will lose the address of the next node. So we need one extra pointer for deletion of this node. So first we'll move to the next node, then the other pointer will take care of deletion of this one. So let us write down the program code and see how deletion is done. So I will do it once again. So the first step is we need a pointer P. So I'll declare it node P that should point on first node. So pointer P is pointing on first node. Then move first to next node. So for movement of a pointer on a linked list, we use this statement. First assign first caps next. So first will move to next node. First comes here. Then linked list starts from here. This node is outside the linked list. Now delete the node. Delete P. That's all. This node will be deleted. It will be removed from the memory. So everything will be gone. One more thing, deletion means not throwing away the value, taking out the value from the linked list. For what purpose? You want to use the value. So if you want to use the value, take out the value. So let us take the value in some variable x before deleting the node. So P's data, let us take it in some variable x. So these are 4 steps for deleting first node. Now analysis, what is the time taken for deleting first node? 1, 2, 3, 4, 4 steps. So the time is constant. Time for deleting just first node is constant, order of 1. Then one more thing, do you need extra pointer for deletion? Yes, definitely we need extra pointer for deletion, that is P. With first we cannot do that. Let me show you. See, if suppose first is here, then if I say first delete, then I'll go there. So if you delete, this node is gone. How do you go to this node? You cannot get the address of this node. So you need the address of that node that is kept here. So before deletion, you need that address. So definitely you need the help of another pointer. So that's all about deleting first node. Now next, let us look at deletion of any other node. Deleting a node from given position. I will say position is 4, that is I want to delete this node. What should be the procedure? First let us look at the procedure, then I will write on the code. Deleting fourth node, that is this one. So for deleting this node from the linked list means this node 3, that is 9, should point on 6. If this node is pointing on 6, then automatically this node is gone from the linked list. So this link is pointing here now. It's no more pointing on 7. So this node is not reachable. So if you start from first 8, that is first node gives the address of this node gives the address of this node gives the address of 6. So this node is not reachable. So in this way the node is deleted. Then also we know that this node should be physically deleted from the memory. So I should delete it, deallocate the memory for this node. That's all. That's what I have to do. So now for deletion, what I have to do? I have to modify the link of this node. So if you want to delete fourth node, you should modify the link of a node before that node, that is third node. And the second thing is you must delete this node physically. How many pointers required? 2 pointers required. You need a pointer on this node for modifying its link, and you need a pointer on this node for deallocating it from the memory. So 2 pointers needed. Let us see how we can have 2 pointers. One pointer we want on this node and one pointer we want on previous node. So it means if one pointer is reaching on this node, then the other pointer can be following that pointer and reach there. So we will take a following pointer or tail pointer. So I will take a pointer P here and Q here, null. Is it a fourth node? No. So move Q here and move P to next node. Then we are not on the fourth node. See, we have done it for one time. Then again bring Q on P and move P to next node. So 2 times I have done. So we are still not on fourth position. Then bring Q on node P and move P to next node. So we have reached node 4. So P is on the node to be deleted and Q is on the node before that node. So how many times I have moved P? 3 times, because I am deleting fourth node, position 4. So for any position, K position, I should move it for K minus 1 time. So for POS position, I should move it for POS, that is position minus 1 time. It is just like an insert we have done. So P will be reaching that node and Q will be helping P for deleting that node. So let us write on the code till here. We want P on first and node pointer Q should be null. So initially P was here and Q was null. Now go on moving them. For how many times? Position minus 1 times. I can do it using for loop. So for I assign 0 to position minus 1 times. What I should do? Q should come on P and P should move to next node. That's all. P is on 4th position and Q is on 3rd position node. Now what are the things I have to do? Make this Q point on this node. From where do you get the address of this node? That is P's next. So modify Q's next to P's next. Modify Q's next to P's next. This is modified. Now that node is free. It's not reachable. So simply delete the node. But before deletion, you take the value and then delete it. So I'll take the value in variable X and delete it. X assign P's data. Delete node P. That's all. So node will be deleted. So this is the procedure for deleting a node from any position. It will delete any node starting from 2nd position onwards, because for the first position, first node, this is the procedure we have seen. right? For any other position, even the last node also gets deleted with this one. You can verify this code, even the last node get deleted. Now analysis. How many links are modified? Just one link is modified, you see. One link is modified. This link is changed. This link actually node itself is deleted. So there is no modification of link. One link is modified. How many pointers required? Extra pointers. 2 pointers are required. P and Q, that are for deleting a node. 2 extra pointers required. What is the time taken? The time spent here is only in this for loop. This for loop will move P and Q. So for loop is used for reaching a given position. So it will take P and Q to that position. So the time taken by this loop depends on the position that you are giving. If you are giving second position, then the time is constant. P and Q will not move at all. If you are giving last position, then the time is maximum n. So the time taken by this procedure is minimum constant and maximum n. So the time taken is minimum 1, maximum n. So that's all about deletion. Now I will write a single function which will take the index and deleted node, whether it may be a first node or any other node. I will write a single function and show you. Now let us see the function for deletion. Function name is delete. It takes a position and returns a deleted value, that is integer value, because all these values are integer. I need 2 pointers P and Q, so I have taken P and Q, and variable x and I. If position is 1, then delete first node. So these are the steps that we are already familiar with. Just now we have discussed how to delete first node. Take out the data from first and make P point on first, move first to next node and delete P. Otherwise, if it is not first node, means if position is not 1, then we have to delete a node from any other position. So we need 2 pointers P on first node and Q on null, and P and Q will reach on the particular index. And one more thing, I am checking that whether P is becoming null at any time. See, in this linked list I have only 5 nodes. If I say position as a 10, then what happens? This P should move total 9 times. So it will move for 1 time, 2 times, 3, 4. At 5th time P becomes null. So there is no 10th index, so it cannot reach there. So P becomes null. So I am also checking whether P is not null or not. If it is null, then it will stop. And after coming out, I am confirming whether P has reached on a valid node or not, or it has become null. If it has become null, means it was invalid index. If it is not null, then these are the 3 steps that are required for deletion. That is, we have to modify a link, that is, make a Q's next point on P's next. Already we saw it, right? Then delete the node. If suppose you want to delete 4th node, then delete the node. At last, return the value that you have deleted. So that's all about deletion. In this video, we will write a function for deleting a node from a given linked list at a given position. So I'm using the same project here. Main function is already creating a linked list. Now before the main function, I will write on a function for deleting a node. So let us write a function delete, and it should take a pointer to a first node and index from which we want to delete an element. So inside this function, I may need few variables like a pointer to a node, that is tail pointer, and also to store a deleted element, I will take a variable x, and in that I will assign -1. Now before deleting an element, I will check whether the indices are given valid or not. So the possible indices are starting from 1 onwards, as we have discussed on whiteboard. Indices starting from 1 onwards, and that will go up to the length of a linked list. So I can give the index from 1 to length. So here I will write on the condition that if index is less than 1, then it is invalid. Or if the index is greater than length of a linked list, that is, for length of a linked list we have a function called count. To that we will send a pointer P, which is a pointer to a first node. So if this is the case, that is either index is less than 1 or index is greater than count, then it is an invalid index. So I should simply return -1, that is, element is not deleted. So or else I can say x also here. So element is not deleted. Otherwise, we can insert an element. So this is the extra condition I am showing here. This I have not discussed on whiteboard. Now, as per our discussion, here we have two cases, that is inserting first node or inserting any other node. So first of all, if the given index is equal to 1, then we have to handle it specially, that this is the first node. So if it is the first node, then I should make a queue point upon this first node as this is the first index. Then I should take the data from first node and I should move the first pointer to a next node. Then I should delete the previous first node, that is q, where q is pointing. Then after this I should return x. The deleted element is in x. So this is the first case. Though the pointers used here may be different, so p or q, whatever the pointer is used, so logic is same. Next, otherwise means if it is not first index, then any other index. Then if it is any other index, then using a for loop, I should use p and q to move them and make a p point on an exact node which we want to delete. So for that, using a for loop, I need one more variable I. So here I will declare a variable I. Then using a for loop, I will move this pointer p and q. I assign 0, I is less than index minus 1 and I++. So already I have checked for valid index, so I don't have to check anything extra here. And every time q will move upon p and p will move to next node. Then after moving p and q for index minus 1 time, p will be pointing on a node which we want to delete. So as we have already seen the steps, that q's next will be pointing on p's next. So now p will be logically removed from a linked list. Then in x we will take the data from p's data and then delete p, and finally say return x, the deleted value. That's all. So this is the portion of the code that we have already seen. Then before this I have added extra line, that is checking for validity of an index. Yeah, delete function is ready. Now let me check it once. Oh, see, the return type is integer type. Initially I wrote it as void. Delete return type is integer, the value we are returning, the deleted value we are returning. And this pointer q is a tailing pointer, so it can be initialized to 0. And for deleting nodes, I should use a function free instead of calling delete. Delete is a keyword that is in C++, but here we should call a function free. Yes, everything is perfect. Now let us go back to main function. Inside the main function, already I have a linked list with a set of elements here, that is 10 to 50. Let us delete 40 and check. So after creating a linked list, I will call the delete function and I will give the first pointer as a parameter and the indexes. If I want to delete 40, then it is fourth node. Like see, this is first and then second, then third and fourth node. Yes, I should give the index as 4. 40 should be deleted. And after that, when I display a linked list, I should not get 40. Now let us run the program and see. Yes, I am getting the nodes, that is 10, 20, 30 and 50. 40 is deleted. Let us check whether it is deleting fifth element or not. Yes, it is deleting fifth element also. What about the first element? Yes, it is deleting 10 also, that is 20, 30, 40, 50 we got. If I give index 0, then what happens? Nothing is deleted, that is 10 to 50, all the elements are as it is, nothing is deleted. If I give the index as 8, there are no 8 elements here, then it is invalid index. So it's not deleting anything. All the elements are as it is. I'll make one more change here. When I am calling delete function, I will directly print its result, that is deleted element %d and /n. So whatever the element is deleted, it will display that element also. Let us run it again. Deleted element is -1, means it is invalid index and I am getting all the elements as it is in a linked list. So instead of 8, I will give the index as 2. So 20 should be deleted. Yes, deleted element is 20, then I am having 10, 30, 40 and 50. Yes, it is perfect. So that's all. In this video we have completed delete function. See here we are writing all the functions upon a linked list, so it is becoming a single big program useful for linked list. So further in our subject, in our course, wherever we require a linked list, we will be using this as a header file and we will be including it and we will be calling all the functions whatever we needed. Let us look at a procedure for finding whether a given linked list is sorted or not. So the example what I have here, the list is sorted. All the elements are sorted. That's what we want to detect, whether it is sorted or not sorted. So let us see the example of sorted list first. Then what should be the procedure? See, the procedure is I should start from the first node. There is nothing here. So let's go to the next node. This node value should be greater than this value. Then it is in the increasing order. Then go to the next node. This value should be greater than this one. Yes, it is in increasing order. Go to the next node and check whether this value is greater than this one. Yes, it's greater. So continue in the same way. If any point, suppose instead of 12, I have 4 here. Then let us start once again. 3, then come to 5 first. 3, there is nothing to compare. So 5, this is greater than this one. Perfect. 8 is greater than this one. Perfect. 4 is smaller than the previous node. Means it is not sorted. So just check the condition whether you are getting any value that is smaller than the previous value. If so, it is not sorted. If not, you have reached the end of the list, you have checked all, then it is sorted. The procedure is very simple. So let us see a procedure for this one. See, what I need is, being on every node, I need a value of a previous node. So what I'll do is, I'll take one variable x and let it be a minimum integer -32768. See, this is the minimum integer value for 2-byte integer. So let it be a minimum value. Now take a pointer on first node of a linked list here. Now the procedure. So what is the procedure? Check 3. Is it greater than this one? Yes, greater. So modify this to 3 and move to the next node. See, when I am presently on this node, I need the value of the previous node. So that value I am keeping in this x. 5. Is it greater than 3? Yes. So modify this as 5 and move to next node. Now this node value is present in x, right? I am on that node 8. So this 8, is it greater than 5? Yes. So modify this and move to the next node. So I am storing the current node value and moving to the next node. 12, is it greater than 8? Yes. Modify this and go to the next node. 16, is it greater than 12? Yes. Modify this and go to the next node. So when we go to the next node, it is null. So we have reached null, means we have thoroughly checked all the nodes. There is no contradiction found. There is no failure. So linked list is sorted. If suppose, I'll modify it once again. See, when I was on 8, this value was 8, right? Now suppose this is 4. When I am here, 4, that is it greater than 8? No. So I got a value which is not in increasing order. After 8, I should have next number that is increasing, but this is decreasing. So stop and say linked list is not sorted. So the procedure is simple. Quickly I will write on the procedure. I need a variable x with minimum value. I need a pointer p upon first node. I should scan through the whole list, comparing the value with x and also modifying x. So what I have to do is, if that value, this value is greater than this initial value was -327. -32768. This was the initial value. Is this greater? If it is greater, I will continue. If it is smaller, then it is not sorted. I should stop suddenly. If it is smaller, then it is not sorted. I should stop. So I should check which condition, success condition or failure condition. We should check for failure condition. If P's data, if it is smaller than x, then return false. Means list is not sorted. So I should check the condition for failure, not for success. If anywhere, if the conflict is found, then stop. Otherwise, continue. So I am writing the condition for failure. Then, if it is not less, then modify x with P's data and move P to next node. P to next node. This should be repeated how long? While P not equal to null, until you reach the last node. And the end of this one, say return true. So this is the procedure for checking whether the linked list is sorted or not. Let me trace this one for some examples. I'll take the data. Here I will take, after 5, I will take 2 here, right? So this is not sorted. 3, 5, 2, 12, 16, 2. So this is not sorted. Because of 2, they are not sorted. So let us check this one. Let us trace this and how it works. P is on first node and this is minus 3, 2, 6, 7. Now first one, P data, is it less than X? P data 3, is it less than X? No. So don't return anything. Take data in X, so 3 in X, and move P to next node. Move P to next node. Then continue. P data, is it less than X? 5, is it less than 3? No. So modify this X to 5 and move P to next node. Move P to next node. Then continue. If P's data is less than X, 2, is it less than? Yes, it is less. 2 is less than 5. So return false. So if this procedure is returning false, means list is not sorted. So it returns false if the list is not sorted. I will change that one and I will continue from there only. I'll make it as 8. Now at this place, P data, is it less than 8? Is it less than 5? No. Modify this X and make it as 8 and move P to next node. P will move to next node. Continue. P data, is it less than X? 12, is it less than 8? No. So modify this to 12 and move P to next node. Continue. P data, is it less than X? 16, is it less than 12? No. Then modify data, then modify X with the data, that is this becomes 16 and move P to next node. P moves to next node. So P became null. Continue. No, P became null. P became null. So come out of this loop and return true. So this is working. So inside the loop, we have checked for the false condition, not for the true condition. So we believe that the linked list is already sorted. If not sorted, then when it is not sorted, if this condition is true, then it is not sorted. So that's all about checking whether a linked list is sorted or not. The time taken by this procedure is, there is a loop, so n, order of n, but if the list is sorted, it is n. If it is not sorted, it can be minimum 1 also. See, this is 3 and if this is 2, then in second node only it will stop. So the time may be order of 1. So minimum time taken is 1, maximum time taken is n. So the time is minimum constant, maximum n. So that's all about this procedure. In this video, we will write a function to check whether a linked list is already sorted or not. So here I have a main function already written and I have a linked list which is already sorted. So before the main function, I will write a function to check whether linked list is sorted or not. So let us write a function. Return type is integer, means it will return Boolean value, that is integer, that is true or false, that is 0 or 1. So function name is sorted and let the function take a pointer to first node and call the pointer name as p. Now, as we have discussed, we need one variable to hold the previous node's value. So the initial value in that variable, let us say x, will be minimum value. So the minimum value for 4-byte integer is -65536. So this is the smallest number. Then I have to traverse through a linked list by using this pointer p, and if any point, if the value is smaller than this previous value, then I should stop. So already we have discussed the code, so let us write down the code. While p is not equal to null, so this will be traversing a linked list, and at any time if p's data, that is current node's data, is less than previous node data, then return false. False means 0. Otherwise, we will copy the data of this current node before moving on to the next node. Then p moves to next node. At the end of a loop, once we have reached the end of a linked list, we will return 1, saying that the linked list is sorted. That's all. It's a simple function. Now here inside the main function, already we have a linked list which is already sorted. So let us call that function and print its result. So I will directly write down printf %d and a new line. Then here I will call function is sorted by passing pointer first. Let us run this. Yes, it has returned the result 1. I'll change a number here. 10, 20, 30. Instead of 30, I'll make it as 3. So now the linked list is not sorted, so it should return 0. Yes, it is returning 0. So it's working perfectly. So instead of printf, I'll just write the code here. I'll display whether it is sorted or not sorted. So if is sorted means if sorted function will return either true or false. If it returns true, then we will print sorted and slash n, else we will print not sorted and a new line. That's all. I will hide this display function. I'll make it as a comment. This is coming from the previous program. Let us run this. Now I should get a message not sorted. Yes, not sorted is a message. I'll change this number to 30 and let us run once again. I should get a message that is sorted. Yes, it is sorted. So that's all in this function. You can practice this function. In this video, we will see the procedure for removing duplicate elements from a sorted linked list. Here is an example of sorted linked list. The elements are 3, 5, 5, 8, 8, 8. So there are duplicate elements. If you take only distinct elements that are 3, 5 and 8, so we want to remove duplicates. What should be the procedure for removing duplicates? So let me show you the procedure. For removing duplicates, we need two pointers. Let us take one pointer P upon first node, and also on the next node, we should have one pointer Q. The idea is we have to check whether the current node and the next node data is same. If data is same, we can delete any one of the nodes. So let us delete the second node. So for that, we need two pointers. So I have first pointer upon first node and the pointer Q upon next node. Now let us see the procedure. The procedure is check whether the data in P's node and the Q node, is it matching? It's not matching. If the data is not matching, that is Q3 and 5, they are not matching, then move P upon Q and move Q to next node. If they're not matching, then slide them. Now let us see next. P's data and Q's data, it's matching. If the data is matching, then what we should do? We have to delete the node. So which one? We will delete the second node. Actually, we can delete any node, but here we are deleting second node. So how to delete this node? Make P's next point on Q's next. This is the first step. Then delete this node at Q. Okay, delete the node. Then make a Q point on this node. That is P's next. So these are the three steps. Make this P point on next node of Q, delete Q, then move Q to P's next. So till here, let me write down some procedure, the code, then I will continue rest of the nodes. See, we need a pointer P upon first node, then we need a pointer Q on next node of first node. Q is pointing on second node, that is next of first. We have already seen this, initial. Then what we have to do? Compare the data of P and Q if they are equal or not equal. So if they are not equal, then we will slide the pointers. So let us write on that code. If P cap's data, if P cap data is not equal to Q cap data, then move P upon Q and move Q to next node. So they will be sliding like this. This is over. Sure. If the data is equal, then what are the steps we have done? In else part, I will write down. P's next should be Q's next. So remember Q was here, right? So P's next here, it should be Q's next. So P's next is Q's next. Then delete this node where Q is pointing. Delete Q, this node will be deleted. Then move Q to next node of P. So Q will be pointing on next node of P. So Q will be pointing here. So I have written the program code up to what all we have learned. Now let us continue, and this time we will be tracing the code. We'll be tracing the code. Now P is here and Q is here. Check the data, 5 and 8, they are not equal. So P should point on Q and Q should point on next node. They have slided if part was executed. Once again repeat. Is the data matching? 8, 8, they are not equal? No, they are equal, it's matching. Enter into else part. So what we should do in else part? P's next should be Q's next. P's next should be Q's next. So this one. Then delete node Q. Node Q is deleted. Then make a Q point on P's next. Q should point on P's next. So when they were matching, we did this one. Continue. Data not equal, 8, 8 not equal. No, it is equal. Enter into else part. Okay. P's next should be Q's next. P's next should be Q's next. What is Q's next? Null. So make it null. Make it null. Then delete Q. This node is deleted. Next, Q is equals to P's next. So Q should become P's next. What is P's next? Null. So Q became null. So Q has reached the end of the linked list. So there are no nodes further. So we should stop. We should stop. So this repeatedly we have done, and we have stopped when the Q became null. So this should be repeated in a loop while Q is not equal to null. So our condition is Q is not equal to null. So this is the procedure for removing duplicates from a linked list. Little bit of analysis. How many pointers required? Extra pointers? P and Q. Can we do it with less number of pointers? That is just one pointer. Check it whether it is possible or not. You find out. Then what is the time taken by this one? It is scanning through entire linked list, that is traversing a linked list. It's order of n, and it must traverse the entire linked list. So it's always order of n. So there is no minimum maximum. So time is order of n. In this video, we look at a demonstration for a function which removes duplicate elements from a sorted linked list. So here in the main function, already I have a linked list created for these 7 elements, and the elements are sorted, and this value 20 is duplicated. Let us write a function which we have already discussed on whiteboard and try it on this linked list. So here I will write on a function. Function name is remove duplicate, and it should take a pointer to first node. So let us call it as P is a pointer to a first node. Then inside the function we need one more pointer, that is Q, which will be before P. So let us take Q, and that is on P's next. So in this function we have taken P as a tail pointer for Q. So Q is ahead and P is following Q. Now we have to scan through a linked list using pointer Q. So while Q is not equal to null, and every time we check if data is matching, P's and Q data is matching. If P's data is not equal to Q's data, means they are not same, it means there is no duplicate, just we should move ahead. So P should come upon Q and Q should move to next node. This is what we have written. We have seen it on whiteboard. Else it means they are equal. So node Q should be deleted. So P's next should point on Q's next. So Q will be logically removed from the linked list. Then we can free a node, that is delete a node. So in C language we have to use a free as a function instead of delete keyword. So delete a node Q and make a Q point on next node of P. That's all. So this is a simple function. Let us run it upon this linked list. So I will call a function here remove duplicate upon first node of a linked list, and after that I will also display a linked list by passing pointer first, and also I will give a line gap after printing yes. Let us run. This 20 should be removed. Yes, 20 is removed. It was 3 times, so it is taking only 1 time. So 10, 20, 30, 40 and 50. Let us try it once more. I will add more 40, 2 more 40s I will insert. So now total number of elements are 9. So it should delete 20 as well as 40. Yes, 40s are also removed. Let us try it once more. I will have initial 10. So if the duplicates are in the beginning itself, now I have 11 elements. Yes, it is removing 10s also. Perfect. I'll do one more test. I'll remove all these elements. Only I will have 3 10s. So it should take just 1 10. Yes, it's working. Just 1 10 is there. Display is printing just 1 element. So that's all. The function is perfectly working in all possible cases. So that's all. You can try this function by yourself. You can write this program by yourself and practice this one. In this video, we will learn how to reverse a linked list. Reversing a linked list means right now the contents are 2, 4, 6, 8. We have to change the order of the elements and make the elements as 8, 6, 4, 2. There are 2 methods of reversing. I'll show you the methods. First one is reversing elements. In this node value 2 is there and the last node value 8 is there. I should interchange them. So here it should be 2 and here I should have 8. Node will be same. What does it mean? Suppose the address of this node is 200 and the address of this node is 210 and this is 250 and this is 300, then this node 200 should contain the value 8 and this node 300 with address 300 should contain the value 2. So reversing a linked list by interchanging elements or reversing elements. Then second method is reversing links. So in this one, you can see that 200 node 200 is pointing on 210, 210 is pointing on 250, 250 is pointing on 300. We want to reverse it, means 300 should point on 250, 250 should point on 210 and 210 should point on 200. So the value 2 remains in the same node, in its node only, it will not change the node. So every value remains in its own node, only the links will change and that node should become first node. Right now node 200 is first node, then after reversing node 300 should become first node. So these are the two approaches. One is reversing elements. Now once again I'll tell reversing elements and then reversing links. So in a linked list we prefer reversing links rather than reversing elements. Why? I'll tell you afterwards. So first let us look at the method how we can reverse the elements. Reversing the elements, one method is I can take an array of size same as the number of elements in a linked list. Like there are 4 elements, so I should take an array of size 4. So I have an array ready, then what I should do? I should copy all these elements in this array. After copying all the elements, then again reverse copy all the elements in that linked list. So the elements will be reversed. So copy those elements first. Let us run the procedure and see. Copy this element p caps data at this place and then move p to the next element and move I to the next index. Copy p's data here and move p and move I. Copy p's data 6 here, move p and move I. Then copy that data also here and p becomes null and move I. This is one part. I have copied all the elements. After copying all the elements, again bring p on the first node and decrement I. I was outside the array, now again bring it back on the last element. Now what to do? Copy this a of I in here, make it 8 and move p, decrement I. So in this way go on decrementing and copying the elements. So 6 is copied here, 4 is copied there and 2 is copied there. So this becomes 6 and this becomes 4 and this becomes 2. So I don't have to explain the whole thing. So now I guess you have understood. So by taking one extra array, auxiliary array, extra array we can call it as auxiliary array, then in that we can copy the elements as it is, then reverse copy them in the linked list. So you can see that the elements has changed their nodes. Here this node was meant for 2, but now 8 is copied there. So the elements, new elements are 8, 6, 4 and 2. So let me write down the procedure, the code for this one. So I need a pointer p on first node initially and I is 0. Assume that array is already existing, right? I am not showing creation of an array. Then what I have to do? While p is not equal to null, means until you reach the null, copy the element in a of I from p's data. Then afterwards move p to next node and also move I to next index. Now this loop will be copying all the elements. Then after that you saw that when p was null, bring again p on first node. So bring p again on first node. Then decrement I was outside, so I said decrement I. So I will write down in the same line I minus minus. So I will come on this last node. Then I should copy these elements back in this one. So again I need a loop. So while p is not equal to null, this time do what? In p caps data, copy the element from a of I and also decrement I. So I should be decrementing and p should be moving forward only. So p assign p is next. So p will be moving forward. This is the loop. So I have written the piece of program code. It's not a complete function or not a complete program, just the steps that are required for performing this operation. So you can see that this loop is copying all the elements from linked list to array, and this loop is copying all the elements from array to linked list. So the elements will be reversed. Analysis. This method needs extra space, array equal to the size of a linked list. Then time taken by this procedure is first copying all the elements here, it's order of n, this is n. Then again copying all these elements back there is n. So 2 times n, so this is 2n. It's not n square, remember this. First time all the elements are copied from there to array, this one. Then second time all the elements are copied from array to linked list. So this is separate n, 2 different n. So total it is 2n, so the time is order of n. So it's always order of n. It has to access all the elements in a linked list, so it's always order of n. Now let us reverse a linked list by reversing links. Reversing links means this node 4, instead of pointing on node 6, it should point on 2, and 6 should point on 4, and 8 should point on 6, and 2 should become null. Now before showing you how to reverse, I'll show you one small concept, that is sliding pointers. Sliding pointers. I am naming it as sliding pointers. What I mean by sliding pointers, let us see. I'll take 3 pointers. One is pointer P, and pointer Q, and pointer R. Initially pointer P is pointing on first node, and Q is null, that is before it, and R is also null, that is before it. I am assuming that are before first node. Actually they are null, they are nowhere actually, but assume that they are here. Now this is the initial state. So what I want is these 3 pointers should slide. Slide means move. It is just like a trailing pointer. If you remember, one pointer P and Q was following it. Now R is following Q. So all 3 together are moving, so I am calling it as sliding. So let us see how I want them to work. See, first R should come on Q, and Q should move on to P, and P should move to next node. This is one movement, one step. Then continue. R should come on Q, Q should move on to P, and P should move to next node. See, all 3 are moving together. So that's why I'm calling them as sliding pointers. Then again, R should move on Q, Q should move on P, P should move to next node. So in this way, we can move 3 pointers together. So for that, I will write on the code here. Initially, P is on first, and Q and R both are null. Then in each step, what I am doing, R is coming over Q, Q is coming over P, and P is moving to next node. I want this to continue until P becomes null. So I can write a condition that while P not equal to null. So it will stop when P becomes null. So these are the steps for sliding pointers. So now you know what are sliding pointers. Now let us see how we can reverse the links. So I'll take a small example and show you what are the requirements for reversing the links. So I'll take 3 nodes. Assume that this is already pointing on the previous node. Then I have to reverse the link of this node so that it points on this previous node. That's what we want, right? 4 should point on 2, 6 should point on 4, means this node should point on the previous node. Now I have to modify this one. So let us take a pointer Q on this one. Then for changing Q's link to this node, I should know the address of this node also. So I'll have one pointer here, R. Then when this link is modified, this will be pointing here. Then where is the address of the next node? We lost the address. We don't have the address. Just now we were having the address of this node. If we modify it and make it point here, we will not get the address of the next node. So for that, we should also have a pointer on the next node. Let us call it as P. So we need 3 pointers. The node which is being modified, and the previous node, and the next node. So I am taking the names as P, Q, R. So what I should do? Q's link should point on R. This modification I should do. So this has reversed the link. Now I have to modify the link of this node. Beyond that, there are few more nodes. Assume that there are more nodes ahead. So I have to modify this node. So for that, Q should go there. Then R should come here. So R should come here. And Q should move to this node. And P should move to next node. Like there is some node again. So that's it. So it means this P, Q, R are sliding. So that's the reason already I have explained you what does it mean by sliding. So how to reverse this? Slide and reverse the link. They have slided. Then say Q's next assign R. That's it. So we need to do two things. Slide 3 pointers and with the help of Q reverse the link. So already I have the code here for sliding. So only one step is remaining, that is Q's next should point on R. So I will write on that code also. Q's next is point on R. So this is the extra line. Till here everything was for sliding, but now I have added Q's next as R. That's all. This is the procedure for reversing a linked list by reversing their links. Let me trace this and show you really it works on this example linked list or not. So I am tracing it. P upon first node. Okay, P upon first node. Q and R are null. Q and R are null. While P not equal to null, yes, P is not null. These are the steps. So the first 3 steps are for sliding. R upon Q, Q upon P and P on next node. R upon Q. So R is again null. Q upon this node. Then P on next node. So these 3 steps I have performed, slided. Then Q's next is R. So Q's next, this one is R. What is R? Null. So this is the first step. Continue. P not null. Yes, P is pointing on some node. Then slide them. These 3 steps. So R comes on Q. Q goes on P. P moves to next node. 3 steps over. Now Q's next is R. Q's next is R. R is this node, so it is pointing on this node. Means here the address 200 will be written. Earlier it was 250, but now it is 200. Next, again continue. P is not null. Then slide them. R upon Q, R upon Q. Then Q upon P, Q upon P. Then P to next, P to next. Then Q's next on R. So Q's next is this one. This was having 300. Now this will point on R. What is R? Address 210. 210. R is a pointer pointing on this node, means it is having address 210. So that address 210 is written here. Continue. P not null. Yes, not null. R upon Q. R upon Q. Q upon P. Q upon P. P is null. P is next. So P became null now. Next, last step, 3 steps over. Q's next is R. So Q's next is R. So here what the address was null. So now what will be written? 250 will be written here. Continue. P not equal to null. No, P became null. Stop. So you can see that linked list is reverse. Now who became first node? Wherever Q is pointing. So the last step I will add, first should be upon Q. So we should bring this first upon Q. This is the first node now. First node is pointing on this node and this is pointing on this. And the last node is null. So the linked list is reverse. So these are the simple steps for reversing a linked list. I have used the concept of sliding pointers and I have reversed it. So with the help of 3 pointers, it's possible to reverse a linked list. Now, as I said that we prefer modifying links for reversing a linked list. We don't prefer movement of data in a linked list. We don't prefer that 8 is brought in this node 200 and 2 is sent in this node 300. We don't want to change the contents of node. We want to reverse the link. Reason. See, in a linked list, as per the example, for learning purpose, we are taking only integers. Integers, 2 bytes, 2 bytes. We are just taking 2 bytes. But that need not be an integer always. It may be a record. It may be having a lot of values. For example, I'll show you, there is a node having roll number of a student, name of a student, address of a student, year of a student, department of a student, mobile phone number of a student, then there is a link. So this whole record is there. It's not just one value like 2, 4, 6, 8. There is a complete record. So it's a linked list of records. Now if you say I want to bring that data here and copy. Now if you say I want to swap this data, then a lot of contents have to be swapped. In our example, that are 2 bytes, 2 byte integers. But here, suppose this is 200 bytes. The size of this record is 200 bytes. Then you will be copying 200 bytes. So what is preferable? Copying just links, changing the pointers. Pointer, how much memory they take? They take 2 byte in 16-bit compiler or 4 bytes in 32-bit compiler. So again, that depends on the compiler. So pointer always takes same amount of memory. Let us say 2 bytes, for example, because in our examples, we are calling integer as 2 bytes. So pointer also 2 bytes. So how much data you have to modify? Just 2 bytes pointer we have to reverse. That's it. So instead of reversing data, we prefer modifying links. So that's all. The procedure is very simple. Using sliding pointers, we have reverse a linked list. Now one more method I'll show you. Reversing a linked list using recursion. So we'll see that. Let us look at a recursive procedure for reversing a linked list. So already we have learned recursion in many topics. So we know that recursion will have 2 phases. One is calling phase and then returning phase. Now let us decide. Shall we reverse the link of each node while going or calling or while returning? We should do it in returning. If we are doing it while going, if we point on this one, then how we can get the address of this one? But while returning, we can make it point on this and come back on this node and make it point on this node, and this is still will be pointing here. So come back on this node, we can make it point here. While returning, we should do that. Okay, let us see how we can do. Let us take a pointer P pointing here, and it will move in the next call here, the next call here, the next call here, the next call, P becomes null. Now when it come back while returning, now when P is on that node, it has to point on this node. So we need one tail pointer also. Because this node should point on this node means we should have the address of this node. So we should also have one more pointer which is following P. So we need 2 pointers. So let me show you how this can be written. So when I have a pointer P upon this node, then I need one pointer Q here, which is null. Now when P is moving, Q should come here. When P comes here, Q should be here. When P comes here, Q should be here. Then while returning, P can point on this node Q. Then again return, P can point on Q, return. So while returning, we can reverse the links. So let me write down a function. Reverse. It should take 2 pointers. First one is Q, second one is P. So a function reverse taking 2 pointers. First one is Q, that is previous one, and next this one is P. So 2 pointers is taking. Then what we should do? Calling time, just go forward. So if P is not equal to null, then do what? Call itself again. By making first one as P, means Q should come on P. Then P should move to next node. So next pointer, P is next. So first pointer is Q, that will become P, and P will become next. It will be calling itself again and again. So recursively when it is calling, at the end, P becomes null, Q is here. So at that time, when P became null, what I should do? See, now I will be returning back. So that is first. This is first. So I should make first point on that Q. So first should point on Q. When I should do this? When P became null. If P is not null, it was calling. When P is null, first became Q. Now it is returning. While returning, first time P will be here and Q will be here. So while returning, what I should do? P's next should point on Q. So P's next should point on Q. That's all. Then again it will return. So return means P will be here and Q will be here. So P is next will point on Q. So you can see that this is a recursive call. So it is calling itself again and again. Whatever is there after recursive call will be executed at returning time. So at returning time, links will be reversed. So this is a simple function for reversing a linked list using recursion, for which we require two pointers. P is ahead and Q is a tail of that P. And when P became null, also I have written in else part that bring first upon that node. See, when Q was here, that time only first was brought here. So this becomes the first node, then next, then next, then next. At last, this will be null and this will be pointing on this one. So that's all about reversing a linked list. Yeah, here in this video, we will look at the demonstration for reversing a linked list. We have seen different versions of functions for reversing a linked list. So I will show you all those methods. So the first method was using array. So let us write down a function for reversing a linked list using array. So I'm using the same main function having some set of elements and the linked list is already created. So let us write the function for reversing a linked list. So here above the main function, I will write a function reverse1, which will take a pointer to a first node and call it as P. Then for reversing, we will store the elements in an array. So for storing an elements in an array, we should create an array. And we don't know how many elements we need. So we will find the length of a linked list and we will create an array of that size. So for that, I will take a pointer so that we can create dynamically. So I will take a pointer A. Then next, here I will create an array of size equal to the length of a linked list. So A assign integer type pointer and dynamic memory allocation malloc, then size of integer type because the data is integer type multiplied by length of a linked list. So for length of a linked list, we already have a function count. We will use that function and pass pointer P. Count is already available here. I'm using the same project. So count will count the number of nodes in a linked list. That is nothing but length of a linked list, this function. So coming back to reverse function. So array is created. So now for reversing, I have to scan through the linked list two times. One for copying the elements from linked list to array, second time from array to linked list. So for traversing, I will take one more pointer that will help me to traverse a linked list, that is Q. I will use pointer Q for traversing instead of P because P is already pointing on first node. Then also I may need a index, that is I, and I is initialized to 0. Now here I will scan through a linked list, that is while Q, as I said, I am using Q instead of P, Q is not equal to null. And every time in an array of I, copy an element from Q's data, yes, then Q should move on to next node. So this will copy, and also I++. I should be incremented. Then once it has reached the end of a linked list, all the elements are copied in an array, then Q should again start from first pointer, that is P. So P is first here, and I minus minus, I should go back to the last element. Then again run a loop while Q is not equal to null. Again scan through a linked list, and while scanning, we will copy the elements from array to linked list. So Q's data is assigned with A of I, and then Q should move to next node and also I minus minus. That's all. So already I have explained you the whole procedure. So the code I have written and for demonstration. Now inside the main function, I will call a function that is reverse1. Reverse1 upon first. Now after reversing, it should display a linked list, so the linked list must be reversed. Let us run the program. Yes, linked list is reversed. So the elements are 50, 40, 30, 20 and 10. Originally linked list was 10, 20, 30, 40, 50. So it's working perfectly. So see on the whiteboard, I have used a pointer P for scanning through the linked list. Here I have used P, it is not Q. But here P is coming as a pointer to a first node, so I am using Q. So Q starts from P and Q will be scanning through a linked list first time, and again Q starts from P and Q will be scanning through a linked list for second time. So don't get confused with the variables, we can use any variable name. Now I will write down second method which I have shown you for reversing a linked list. So for that, I will call a function as reverse2. Reverse2, it takes a pointer to a first node, and let us call that pointer name as p. P is a pointer to a first node. And in this procedure, we require 3 pointers. P is already there. Q we require, that should be initially null. And also we require R, that is also null. Then P, I will be using it. So P is pointing upon first node. So I have 3 pointers we will use, and I will directly write on the code how it works. Already I have explained you. While P is not equal to null, until P reaches null, then first of all R should come upon Q, and Q should come upon P, and the P should move to next node. Then after that, Q should point on Q's next should point on R. This is how we proceed. Then once we come out of the while loop, first pointer should point on node Q. That's all. Function is finished. Now inside main function, instead of calling reverse1, I will call reverse2 and run it and see whether it works. Yes, it is working. 50, 40, 30, 20 and 10. It's perfect. So we have seen 2 functions. Now the last function is recursive function for reversing a linked list. So I will write down reverse3 for recursive function. So it should take 2 pointers. Struct node pointer, first of all Q, and the next pointer is current pointer, that is P. Then if P, that is P, is not equal to null, it will be calling itself reverse3 by passing here P, and next is P's next. Yes, 2 pointers it will be passing, and while returning it will make P's next as Q. And if P is null, then it should make first as Q. That's all. Just 3-4 lines of code, and inside the main function, instead of reverse2, now I will call reverse3. Let us see. Oops, I should pass 2 parameters. So the first parameter is null and the second parameter is first. So it's taking 2 parameters. Yes, linked list is reverse. 50, 40, 30, 20, 10. I'll try with different values. I will change the values and make them as 50, 40, 10, 30, 20. So I should get 20, 30, 10, 40 and 50. 20, 30, 10, 40 and 50. Yes, it's perfect. So that's all. We have seen 3 different versions of reversing a linked list. One is using an array, and the second one is using 3 pointers, and the third one is recursive function. So you can practice these functions. Now in this video, we'll look at concatenation of 2 linked lists. The topic is very simple. Here I have 2 linked lists. This is the first linked list and this is the second linked list. Concatenation means joining them or appending one linked list with the another linked list. Like I want to append second linked list to first linked list. It can be done in other way also, like you can append first list with second list, anyone. So it is just like doing first plus second, and we want to generate a combined linked list. Procedure is simple. Let us look at the procedure. We have to reach the end of the first linked list, and instead of null, let it point on first node of second linked list. So it becomes a complete single linked list, one single linked list. So for this, I should take a pointer P and traverse it and make it stop at last node. Move next, 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 and let it stop at the last node. So how do we know that node is last node? Because its next is null. So stop at a node whose next pointer is null. And once you reach that node, join these two. So till here I will write on the code. P assign first. So P is on the first node. Then go on moving P. P assign P is next. How long I should do this? While P's next is not equal to null. If it is not equal to null, continue. When it is equal to null, stop. Don't move further. So with a simple loop, I can reach here. Then I have to join them. So for that, make P's next point on second. P's next point on the first node of second linked list. So we have a pointer that is second pointing there. So set it as second. That's all. From first, I can go on node 2. 2 will send on 9. 9 will send on 6. 6 will send us on 8. And 8 will give the address of 10 and so on. So this became just one linked list. Now, whether you want that pointer second still pointing on that or not, it's your choice. If you say no, remove it from there. So we can make pointer second as null. So pointer second is removed from there. Then analysis. We need one extra pointer. This is one thing. Second thing, it requires order of n time. Why? Because we have to traverse the pointer p so that it reaches the last node, and the time taken for reaching the last node depends on the number of node in the linked list. So that is n, order of n. So time is order of n. That's all about concatenation of two linked lists. In this video, we'll look at merging of two linked lists. If you look into the section arrays, there we have seen how to merge two arrays. Now we are learning how to merge two linked lists. So let me tell you briefly about merge process. Merging is a process of combining two sorted lists into a single sorted list. So I have two sorted lists. First linked list is sorted 2, 8, 10, 15. Second is also sorted 4, 7, 12, 14. Both are sorted. So combine them. We will combine these two into a single sorted list. The next thing, if you remember, merging two arrays, you require one more third array. But in linked list, it's not necessary. If you want, you can take third linked list. Otherwise, you can combine these two and make it as a single linked list, one single linked list. You don't need extra linked list. I'll explain you the procedure, how merging is done over linked list, and also simultaneously I may write down the program code also. So let us see. This is first linked list, this is second linked list. For merging, we require one more pointer. Let us call it as a third. I will take one pointer called third, pointer third. And for helping that pointer, I will take one more pointer, that is last. I need two pointers. One is a third, that will be pointing on the first node of third linked list, that is merged linked list. And also I will use one more pointer called last. This will be pointing on the last node of that merged linked list. So I have to use two pointers. Let us start the procedure. What is the procedure? Compare the element of first node in first linked list and element of first node in second linked list. Which one is smaller? This is smaller. When this is smaller, bring last as well as third upon this node. We'll bring third as well as last on this node. Because this is the first node, we are starting from here. So make it point on that one. Then move first to next node. First will move to next node. I'll just write F instead of first. Then make this as null. So now you can see that the first linked list is having only 3 nodes and this is the first node. Then what about the previous node that was already there in the linked list? Now it belongs to merged linked list where both third and last are pointing there. In the first step, we have to bring both third and last on same node. Next, again continue, compare 8 and 4. Who is small? Second one is small. So now the steps are repeating. Watch this step. What I should do? Last next should point on this node. Okay. Last next should point on this node. And bring last on this node. Okay. Then move second to the next node. Second is moved on to the next node. So let us call just as for second. And make this last next as null. Now there are 2 nodes in this third linked list. This is the starting node and this is the next node. Then continue the same procedure. Compare first and second value. So this is smaller. So make this last next point on this node and move last on this node. I'll call it as just L. And move second to next node and make this as null. So now the procedure will be repeating. I will continue, but till here let us write down the code. So I'll bring back the things as it is and again show you the code. Now back to the same thing. What was the first step? First step is to check who is smaller, whether first one or second one. Whoever is smaller, bring 2 pointers, that is the third and last on that node. So I will write down that code. If first data is less than second's data, then bring third as well as last upon first. That is bringing third and last upon the same node. We did this one. Then move first to next node. So take first to next node. First will move to next node. First should move to first next node. Then after that, this last next should be made as null. So last next is made as null. This is what we did for the first time. We did this with first linked list node because this was smaller. If suppose this was smaller, we would have done the same thing on this node. So I should write on inside else part for the second. Same steps, third and last should point on second. And second should move on to next node. Second should move on second's next node. And last next should be made as null. As we did upon first linked list nodes, we should do the same thing for second linked list also. So this is the initial step that we have to do. Then after this, we were doing repeating steps. What were the repeating steps? Compare the data of first and second, whichever is smaller. Now this is smaller. So make last next point on this one. This is one step. Then bring last on this node. This is the second step. Then if it is first or second, we don't know, whoever it may be, it should move to next node. Okay, second is moving to the next node. The next, make last next as null. These are the steps that we are doing. Let me repeat once again. Compare first data with second data, which is smaller, that is 8 and this is 7, so this is smaller. So make last next point on this node and bring last upon this node and move second to next node and make last as null. This is what we are doing. Again, I'll do one more time. Compare first data with the second's data. First data is smaller. So make last next point on this data and move last to that pointer, whether it is first or second. Then move first to next node. First is moved to next node. And last next should be made as null. This is what I have to do. Whoever's data is smaller. So again, I will write on the code here. If first data is less than second's data. This is a repeating part. So here we will be having loop, right? So this is a part of loop as we are going on repeating this one. So what should be the condition in loop? I will show you afterwards. But let us see this one. Now let us compare now. First data is a 10 and second's data is a 12, right? So that is smaller. So what I should do? Last next should point on first. Last next should point on first. Then last should be pointing upon first. I'll continue in the same line. Last should be same as first. Then move first to next node. Move first to next node. Move first to next node. How to move first to next node? First assign first caps next. Then make last next as null. Make last next as null. So I'll continue here only. Last next should be made as null. Lack of space, so I have written in a single line. You can see that these are the statements. This is one, then next statement, then next, and next. So total 1, 2, 3, 4. 4 steps I am performing if this is smaller, first is smaller. Otherwise, if second one is smaller, then for the second, same steps should be performed. So that is last to next should be made to point on second. Then last should point on second. I'll complete the steps. Same step, just instead of first, it will be second. I have written same steps. If first data is small, do this. If second data is small, do this. Steps are same, only the pointers are different. Pointer is either first or pointer is either second. So this we have to go on doing it. So let me continue for some more time and see. Next, compare the data. This one is smaller, 12 is smaller. So last to next should be pointing on this one, and last should come here, and second should move on this one. I'll just write S, and last to next should be null. Then again compare. First data 15, second's data 14. This is smaller. So last next should point here, and the last should point on this one, and the second should move to the next node. So the second becomes null, and the last null next should be made as null. Now I have finished all the elements in one of the linked lists, that is second linked list, and second linked list there are no elements because S became null, so I should stop. So it means this repetition I can do as long as there are some nodes in either first list or second list. If any one of the list ends, I should stop. Means if first becomes null or second become null, whoever becomes null, I should stop. So I should continue if both are not null. First should also be not null, second should also be not null. So while first not equal to null and second not equal to null. This is the condition. So I'll just highlight this condition. See, this is the condition. So as long as none of them is null, I should continue, right? So this is a loop. Loop is having these two things, like those four steps, either for the first node, first linked list, or for the second linked list. They are there. Now at last, what is remaining? See, one of the linked lists has finished and last is pointing on this node. Now there are some nodes remaining in first. So if there are some nodes remaining in first, then last of this one should point on first. That's all. Last to next should point on first. If suppose there are nodes remaining in second linked list, then it should point on second. So here I will write down that part. If first is not null, after this loop, anyone is not null, right? Because one of them has become null, so it has came out. If first one is not null, then make last next as first. That's what I have done here. See, last is pointing on this one. Else, definitely second one will be not null. So last next should point on second. So wherever the nodes are remaining, it should point on that one. So this is the code for merging. The code is little lengthy. So if you see the third linked list, let me trace this one. Third, this gives the address of 2, 2 gives the address of 4, 4 gives the address of 7, 7 gives the address of 8, 8 gives the address of 10, 10 gives the address of 12, 12 is leading us to 14, 14 is leading us to 15, and after 15 there is null. So this has formed a one single linked list. That's all. This is merging. Now let us do some analysis. In analysis, there is no extra linked list required here. So that is the benefit of merging upon linked list. So you can say that merging is suitable for linked list because it doesn't require any extra space. In case of arrays, you need extra space. Then second thing is, what is the time taken by merge process? So if we say there are m elements in first linked list, then n elements in second linked list, so the time is theta of m plus n. This analysis we have already done in merging in an array. So you can watch that video if you want to know the analysis. Analysis is same here, m plus n. So whenever we say merging, we should mention the time as m plus n. So m are the number of elements in first linked list or n are the number of elements in the second linked list. Usually we don't take two variables, but to show that this is merging, we are making it as a notation for merging. So M plus N means, okay, this is merging. Merging is used here. So it has become a notation for merge. So that's all about merging two linked lists. In this video, we will look at demonstration for concatenation of two linked lists as well as merging of two linked lists. So I should already have two linked lists with me, and this program which I have been using is having one linked list that's already created using create function. If we look back to the create function, this was the first function we have written. This is creating first linked list. It is directly accessing pointer first and it is creating first linked list. So as I need one more linked list, I will have one more pointer, that is second, and one more pointer I may need, that is third pointer for third linked list. And I will initialize these pointers also as null. Now, as we already have a function for creating first linked list, now for creating second linked list, I should have separate function. So what I'll do is I'll copy the same function and paste it here. I'll paste it here and I will call this function name as create2. This is the second function. Now here, instead of using pointer first, I will use pointer second. I'll modify this. Yes, this is enough. It will create second linked list. Now first of all, let us try to create two linked lists, that is first and second, and display them individually. I should create a linked list using this create2 function. Let us go back to main function. Here create function is creating first linked list. Then I will have one more array, that is B, and in this I will have some elements. 5 elements I have taken. Now I will call function create2 by passing array B and the number of elements are 5. So it should create a second linked list. Then here I am displaying first linked list. So let us call it as first new line, and for the second linked list also I should print it. So for displaying I will copy this code and paste it here. Now this code I will make it for second linked list and I will pass the pointer, that is second. It's a global pointer. Now let us run this program and see I should get a two linked list. First linked list, then followed by that I should get second linked list. Yes, first linked list is 50, 40, 10, 30 and 20, and second linked list is 1, 2, 3, 4, 5. Yes, it's perfect. So I'll remove this code for displaying. Now I have two linked lists created here, that is first linked list and second linked list, by using two different functions. Now I have to write on the code for concatenation of two linked lists. So I will write function name, that is concat, which will take two pointers, that is first linked list and second linked list pointer. I will take first pointer as P and second pointer as Q. So for concatenation, I should scan through the first linked list, that is using pointer P, and I should reach the end, and from there I should connect the linked list to the second linked list, that is to Q. So it's a simple process, easy process. But first of all, I should make pointer third point on P, that is upon the first linked list. Now concatenated linked list, we will have it in a pointer third. Now I should scan through first linked list and I should stop at last node. So I should say P's next is not equal to null. So it will stop upon last node. And every time I should move P assign P's next. Now once it has reached on the last node, then I should say P's next assign Q. It will be concatenating. That's all. The procedure is very simple. So I'll get the third linked list pointed by pointer third. So here I will display third linked list, which should be concatenation of first linked list with the second linked list. Printf concatenated, that is next line. I should call display function upon third linked list, and after display I should give new line to separate the output, make it clearly readable. That's all. Now let us run the program. Now here inside the main function, after creating two linked lists, I should call function concat by passing first linked list, that is first, and the second linked list, that is second. So this should concatenate and the result should be in third linked list. Then I should display this, so I will write on the code quickly for displaying. Yes, printf concatenated linked list, that is display third linked list. So third will be a pointer pointing to a concatenated linked list. Let us run this. I should get concatenated linked list. Yes, 50, 40, 10, 30, 20, then 1, 2, 3, 4, 5. So first linked list, then followed by that is a second linked list. I'll try to just change the order. Instead of first linked list, I'll give first second one, then next first linked list. So I should get 1, 2, 3, 4, 5, then 50, so on. Yes, 1, 2, 3, 4, 5. Now this is the first is the second linked list, and followed by that is a first linked list. So that's all with concatenation. It's working perfectly. I'll remove this Now let us write a function for merging two linked lists. So for merging, first of all, I will modify this linked list. First linked list, I will take the values like 10, 20, 30, 40 and 50. And for the second linked list, I'll take the elements like 5, 15, 25, 35 and 45. Now let us write down the code for merging two linked lists that already we have seen merge. So it should take pointer to first linked list, that is P, and also pointer to second linked list, that is Q. So P and Q I am taking as pointers to first linked list and second linked list. Now here I should merge two linked lists and make a third pointer point on merged linked list. So for merging process, I need a pointer, that is last pointer, that is useful for merging. I'll declare it. The first thing I should make pointer third point either on P or Q, whoever's element is smaller, like first linked list or second linked list. So for that, I should check the condition, that is if P's data is smaller than Q's data, then third as well as last both should point on P, and next P should move to next node and third's next should be made as null. Otherwise, if Q's data is smaller, then the same thing should be done upon Q. So I will copy this. This I should make it for Q. Yes. Here it is done. Now the process is repeating process. I should keep on checking the elements of P and Q, whichever is smaller, that should be linked with the third linked list with the help of pointer last. So while P and Q, every time check if P's data is smaller than Q's data. If so, then I should make proper links like last next should point on P and P should move to next node and last next should be made as null. Otherwise, I should do the same thing with last next should point on P and last should move upon P, then P should move to next node and last next should be made as null. Then otherwise, I should perform same set of operation upon Q. So I will copy this and paste it here. Now the same process should be done for Q, that is last should point on Q and Q should move on to next node and last next should be made as null. So this while loop will keep on copying the elements whichever is smaller, and at the end of while loop, whichever linked list is remaining, I should link that one. If P is not null, means P, if P, then last next should point on P. Then last next should point on P. If Q, then last next should point on Q. That's all. That's what we have already discussed on whiteboard. Now let us go to main function and merge these two linked lists. Merge by passing pointer first, comma, pointer second. Then the third linked list will be formed and let us display third linked list. Let us run the program. Yes, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. All elements are merged. Let us change few elements and try again. So I'll give all these elements that are greater than first linked list. So 52 and this is 152, this is 252, 352, 452. So all these elements are greater than first linked list. So let us see whether it's managed or not, whether it is merged or not. Yes, it is merging. It's working perfectly even in this worst case, that is all small elements in first linked list, then all larger element in the second linked list. So they are being just like concatenated and it is merging perfectly. Now I'll do one thing. I'll make this first element as 5 and rest of them are greater. So this 5 should come before 10 and rest of these elements should come after 50. Let us run. Yes, 5, then 10, 20, 30, 40, 50, then followed by that 150, 252, so on. Say yes, this merge function is working perfectly. So that's all with our merge function. I have shown you how to concatenate and how to merge. The code is little lengthy, but this is an interesting function, that is merging two linked lists. So you try it by yourself, write a program and practice this one. In this video, we will see how to detect if a linked list is having a loop or a linked list is linear. So what is a loop? I'll explain first. See, there is a linked list and the last node of a linked list is pointing on some node in a linked list. It's not the first node, it is some other node. So if a last node is pointing on some node of a linked list, then it is forming a loop. So this linked list is having a loop. Then I have one more linked list which is ending with null. Last node is having null. So this linked list is linear. So there is one linked list with loop and there is one linked list that is linear. Now the problem is, if a linked list is given to us, we have to find out whether it is linear or it is having a loop. How to detect? So first let us see how to detect whether it is linear or not. A linked list will be linear if it is ending with a null. Last node is having null. Now how to know whether the last node is having null or not? So we have to start from first node and reach the last node and check that it is really having null or not. So for that, let us take a pointer P and go on moving upon this one. Next, 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 and at one point P becomes null. So if P becomes null means it is linear. So if you are scanning through a linked list or traversing a linked list and the pointer becomes null, means it is linear. Now how to know whether it's having a loop or not? So if I take a pointer P and go on scanning the linked list or traversing a linked list, then P will be moving on to this node, then 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 again it will come to this node, then this will give the address of this one. So it will be moving around these set of nodes only. Then how I should stop and say that this is having a loop? How to know that there is a loop in this linked list? So there are different suggestions like store the addresses of the nodes, and if you come across the same node once again, then there is a loop in this one. Or you can store the elements if the elements are unique. If you are sure that the elements are unique, then if you come across the same element once again, then you can say there is a loop. There is one more method using two pointers. I'll show you that one. See, we will take two pointers on a linked list. One is P and other one is Q. They both start from first node. Then P will move by one step and Q will move by two steps. So I can compare these two pointers with one example. Like suppose there is a race track. So these are two cars on the track. This is the starting point and the track is 15 kilometers, and suppose this car is moving with a 100 km per hour speed and this car is moving by 150 km per hour speed. So this car is very fast. Now from the starting point, when they start off the race, then do you think they will meet again at any place? No, this car is slow, that car is fast, they never meet again. Definitely this will reach first and this will be reaching there slowly. Now instead of having a straight linear track, we can have a circular track also. Suppose this track is of 1 kilometer and these two cars, they have to take laps of this track 15 times. They have to move around this one for 15 times. So if this car is 100 km per hour and this car is 150 km per hour, as they are going to make 15 rounds of this one, then definitely they will meet at one point. So it means if one car is slow, one car is fast, they never meet if the track is linear. They will meet once again if the track is circular. So same way, if the linked list is having a loop, then these two pointers will meet. If it is linear, they never meet. So let us apply the same idea upon the pointers. One pointer will move it slowly by one node and one pointer will move it fast by two nodes. So I have P and Q. So let us move P by one node and Q by two nodes, 1, 2. So Q is here. Then move P by one node and Q by two nodes, 1, 2. So Q is here. Then move P by just one node. Then move Q by two nodes, 1, 2. So Q is here. Then move P by one node. Move Q by two nodes, 1, 2. So they are meeting again. So if the two pointers are meeting again after the starting point, if they meet once again, then there is a loop. Let us apply the same thing there. I have P and Q here. Now let us move P by one node and Q by two nodes. Then P by one node and Q by two nodes, 1, 2. So in the next step, Q becomes null. So if any one pointer becomes null, we should stop and say that this linked list is linear. So in a linear linked list, one of the pointer will become null. Definitely Q will become null because it is moving faster. So we can take two pointers and find out whether it is having a loop or it is linear. If they meet again, then there is a loop. If one of the pointer becomes null, then they are linear. Now let me write down the function for checking whether there is a loop or not. If no loop means it's linear. I'll write a function. Let us call the function as isLoop. So this will return true if there is a loop. If it is linear, it will return false. So this takes a pointer to the first node. This is f. Then it is going to return true or false, so it is integer type. Now we need two pointers, node p and q. Two pointers are needed, and p and q both are on first. This is f. F is for first. I am calling it as first. First we will be passing it as parameter. Now what they have to do? So using do while, just move p by one step and move q by two steps. So q assign q is next. This is the first step. And second step, don't take it blindly. If q already became null, then there is no next node. So check if it has become null. If it is not null, then move to the next. So if q is not equal to null, then q should be assigned with q's next. Otherwise, let q be null only. Now here inside while, I will write down the condition that while p and q continue as long as both the pointers are not null. Both the pointers are not null. Now at the end of this, there is no space, so I will continue here. If p is equal to null, means both are at same place, then return true. True. I am writing true here. True means 1. I will be returning 1. If they are not equal, means definitely one of the pointer is null, so return false, means it is not having loop. Not having loop means definitely it is a linear linked list. So this is the code. So there is no space, so I continued here, just conditional statement. I can write down that condition here also. I can say simply return if p is equals to q, return true, else return false. Suppose true means once and false means 0, so function ends here. So that all that conditional statement if else I have written in just one single line. Return if p is equal to q, return true, otherwise return false. So this is the procedure for finding whether there is a loop or not. So analysis. How many pointers required? 2 pointers. What's the time taken? Order of n, that depends on the number of nodes. So this scanning is done depends on the number of nodes. They may be scanning the portion of a loop more than one time. That doesn't make much difference. Even we can say 3 times of n also, it is order of n. So it is multiple of n, that is number of nodes. So it's not n times of n, so to call it as n square, some number of times of n. So we can call the time as order of n. So that's all about this procedure. In this video, we'll look at the demonstration of a function to check whether a linked list is having a loop or is it linear. So this is the main function which we have been using, and it is creating a linked list of these nodes, and this is a linear linked list. I will form a loop in this linked list. So how to form? For that, I will first of all take 2 pointers, temporary pointers, struct node t1 and t2. Now using these pointers, I will form a loop. So I will make a t1 point upon third node, that is 30. So let us do it. So t1 assign first, this will be the first node, then its next means it will be on 20, then its next means it will be on 30. So t1 will be pointing on node 30. First means node 10, then its next is node 20, then its next is node 30. Then I will take pointer t2 and make it point upon last node. So for that, first is the first node, then next means second node, then next is third node, then next is fourth node, then next is fifth node. Yes, t2 is pointing on the last node. See, even I can make it move till there by using loop, while loop. Instead of while loop, I am directly writing a single line. Now t2 next is null because it's pointing on node 50. So t2's next is made as t1. So it becomes a loop. So it is just like from 50, it is pointing on, from 50, it is pointing on 30. So it's having a loop. I have formed a loop. Now let us write on a function that is a simple function for checking whether a linked list is having a loop or not. Now here let us write a function for checking if it is loop. So it should return an integer type that is true or false, and the function name is loop, and it should take a pointer to first node. So I will call the pointer name as f. Then for accessing I need two pointers, that is pointer p and q, so I will declare them pointer p and pointer q. Initially p as well as q both are pointing on first. Now the process is a repeating process to check whether a linked list is having a loop. So using do while I have explained. So first pointer p is moved to a next node by just taking one step, and the q will take two steps. So first of all, first step is taken. Then the second step is conditional, that if q is not equal to null, then q will move to next node. Otherwise, it will remain there only. And this process should continue until p and q, means none of them should be null, as well as p is not equal to q. So it will stop when any one of these condition fails. So when they become equal, it means there is a loop. So I think I have missed this condition upon board. So we have to write on this condition also, that is it will stop when both are meeting at one place. And if p is equal to q, means both are at same place, then return true, that is it's a loop. Otherwise return false, that is it's not a loop. So this condition I have missed on whiteboard when I wrote the code on whiteboard. This is missing, that is p is not equal to null, means if they are equal we should stop. That's all. So already I have created a loop here. Then I will printf the result of that function. I will call that function is loop, and I will send the pointer to a first node. That's it. Let us run. Yes, 1, it is having a loop. Return true. Okay, I'll do one thing. I will make these statements as comment, then I will run it. So it should return false. No, it is not a loop. I got a warning because this t1 and t2 are not in use. So the result is 0, means false. It's not a loop. So when I have made it as a loop, it is returning true. Yes, perfect. So the code is working perfect. It is detecting whether a linked list is having a loop or not. Let me run once more. Yes, return true. So here even I can write down a message that it's a loop or it's a linear linked list by using conditional statement, but directly I am printing its result, that is true or false. That's all. Write on this function by yourself and check it. In this video, we will write a C++ class for linked list. So I'm starting a new project for C++ class, linked list CPP, that is the project name, and the language is C++. Create a project. Yes, create a project. Let us go to main function. I'll remove all these comments. Yeah, let us start writing a class for linked list. I don't have to discuss much because already we have seen the procedures. So simply I will write on the code. So here we will focus on the style of writing the code, how to write on the code. So let us write few functions and let us define a class and write few functions. Class linked list. Now private data members we require. First of all, we need a class for node, and in this class everything must be public so that it is directly accessible. I should have data and a pointer to next node. So node next, that is a pointer, and of this class. So instead of structure we are writing class, then class linked list. Now inside this class the public members, then inside this class the private members, I need a pointer called first. So node first. That's it. This is sufficient. If anything more, we will see later on. Then next is public. We should write the functions. So the first function is constructor. So let us call it linked list, and the constructor is non-parameterized. Nothing should be there. There are no arguments, and the first should be made as null. This is what we do for initialization of linked list. So single line constructor, nothing else. There is no size, nothing. So it will be initially empty, null. And as we go on inserting the elements, it will be increasing. That's why this is the constructor which is making first as null. Then destructor, I will be showing it afterwards. So I will write the prototype of a function. Then the other functions that we will have are display. Then the other functions that we will have are display, which will display a linked list. No need of parameters because it's a part of linked list function. The next is insert function, which will take index at which we want to insert and the element that we want to insert. And the return type of these functions should be void. Yes. Then delete function should return an element, deleted element, and the parameter, it should take it as index. Then as in the C program, we have seen a function for creating a linked list by taking array of elements. I will also have one function for create. So that's all. This is over. Now as in the C language function, we have written a Now as in C language, we have written a function for creating a linked list by sending an array. Let us have that type of constructor also, linked list, which will take an array of elements and number of elements, and it will create a linked list. So this function I will define outside. नहीं सब गलत सलत हो जा रहा, सब गलत सलत हो जा रहा भैया. यहाँ से निकाल दो ज़रा, डिस्प्ले फंक्शन सब निकाल दो. The next constructor I will write down, that is, we have written C language function for creating a linked list by taking an array of elements and number of elements. That same function I will write it here. So let us make it as a constructor. So here, for making a linked list faster, we will send an array, it will create a linked list. Then I should have a destructor. Destructor, I will implement it outside. All these functions I am going to implement them outside using scope resolution. Then the remaining functions, void display, this will display all the elements. Then void insert function, which will take index at which we want to insert an element and also the element itself. Then delete function, this will delete an element from a given index and it will return the deleted element. Then also I will write one function for finding length of a linked list, that is the count of a linked list, number of nodes in a linked list. That's all. I will implement these functions and I will explain you. I will not type them because already we know the methods, because already we know the procedures how to write these functions. you have completed the class. Let me explain you the class. See, these are the functions we have written: constructor, destructor, and display, insert, delete, and length function. So here, using scope resolution, I have defined a function. This is a constructor which is taking array of elements and the number of elements, and this is same as the create function that we have written using C language program. First I have created first node, then using for loop I have created remaining nodes by filling the elements from an array. Then this is a deleting of an entire linked list. So with the help of a pointer p, I am deleting all the nodes, and first is moving to the next node and p is keep on deleting all the nodes. Then display function is as usual. So one thing you can observe here is that I am taking a pointer of type node and pointing onto the first node, and here internally I am. Now one thing to observe that the functions are not taking parameter as a pointer to a first node. First is already there inside the class, so I am taking a local pointer p which is pointing on first node and then displaying all the elements. See, this is the style of code I have already used on whiteboard most of the time. Then this is the length function which is same as count function of a C language program. Then this is insert function having the same procedure, like checking whether the index is correct or not, then creating a node. If the node is first, then first pointer should point on that one. That is, index is 0, then first should point on first node. Otherwise, we should go to that index and insert a new node. Then deleting a node, I am checking the index whether it is valid or not. And if the index is 1, deleting first node. Otherwise, deleting a node from a given position. Then here inside the main function, already I have written a array and I am creating a linked list using that array and displaying it. Let us run this program. I should get the output, that is 1, 2, 3, 4, 5. Yes, I am getting the elements that are 1, 2, 3, 4, 5. Let me try other functions. So I will use cout and I will call delete function. Delete first element. So it should delete 1. Let us run. Yes, it has deleted 1 and the rest of the elements are 2, 3, 4, 5. I delete an element, that is third element, and also I will give endl. So this is the deleted element. So I should get the elements 1, 2, 4, 5. Yes, 3 is deleted and the rest of the elements are 1, 2, 4, 5. Now instead of delete, let me try a function that is length. Yes, length is 5. It is displaying the length of a linked list. Now I'll remove this. Let us try insert function. L dot insert. I'll insert at index 0 element 10. So 10 should be inserted before 1. ये क्या है, कैसा हुआ ये? Yes, 10 is inserted before 1. Now let me change the index. I'll insert at index 3. So it should be inserted after 3. So 1, 2, 3, 10, 4, 5. Yes, 1, 2, 3, 10, 4, 5. Perfect. See, the benefit of writing a C++ class is the code is so smooth. See, the benefit of writing a C++ class is the code is properly organized in the form of a class, and the class is having member functions, and we can use the class and call its functions, create an object of a class and call the functions. Then one more thing I have to explain you that this is a linked list of type integer. Suppose if you want to change it, then you can make it as a template. So I'll quickly convert into a template. So for converting into a template of any data type, now one more thing I have to show you here is that this is a linked list of type integer. So if you want the linked list to work for any type of data, then we can convert this as a template. So for converting as a template, we should define a class T and change this data type to T. Now wherever I am using node, I should pass T as a template parameter. So I will make this class linked list also template class T. Then wherever I have written node, I should write a T there. Yes, this array should be of type T. Then the element that I am inserting in a linked list should be of type T, and the deleted element should be of type T. And outside the class, for every function, I should write template class T, and just beside the class name I should write down T, as this array is of type T. Node is also made as T. So I'm making changes, just watch it closely. Then here is node, then here is node T, then here also, then inside destructor template class T. Acquire. देन वो सब टेम्पलेट जहाँ से बोले वहाँ से हटा दो, खाली इतना ही बोलना है. Then already I have shown you how to convert a class into a template class, so you can make this class as a template. That's a student exercise. It should be able to work for any type of data. That's all. So you can practice this program, write a C++ class for linked list. In this video, we'll have introduction to circular linked list. What are the methods of representing a circular linked list? There are two methods. I'll show you both the methods for representing a circular linked list. So first one, already I have an example here. This is a circular linked list. So what is a circular linked list? With respect to a linear linked list, linear means a last node was having null. So far what we have studied was a linear. So this is circular. So how it became circular? A linked list in which the last node will point on first node. Then it is circular linked list. This is how it is defined. Or the other definition is The nodes are circularly connected. Collection of nodes circularly connected. So the collection of nodes, when they are circularly connected, then which one is first node? So there is no first. So for that, we usually use a term head, that is a pointer name head for one of the node. So there is no first node or last node. They are circular. So one of the node we can call it as head node. So here head is more suitable than calling it as first. So I will be using pointer name as head. Anyway, you can use head first, that is your choice. It's not a big issue. What is the benefit of circular linked list? We can traverse these nodes circularly. Suppose you have started from head, you can go to next node, then next node, then next node. From this node, if you go next, again you will be back on head node. So you can traverse this linked list circularly. In our computer system or in our mobile apps, at many places we find the things or a list or collection is handled circularly. If you take the example of a contact list in your mobile phone, suppose you are scrolling up the contacts and you have reached the last contact that is starting with the Z, then again in some mobile phones or in some apps, if you scroll up again, the contacts with A will start again. So it means we are able to access the list of contacts circularly. We can move circularly. Though in that app you can move up and down, bidirectional movement is there, but here there is only forward direction movement and it is circular. So just we have added one extra feature to the linked list that we have been studying so far. We were learning about a singly linked list. Now it is singly and circular linked list. So just we have added one feature extra to make the access circular. Now where to use it? If you have only one direction access and you also want circular access, then you can go for it. Now when we talk about circular linked list, we don't have to study much, because what all you can do on a linear linked list, same thing you can do here also. We'll not be studying much about this one. Few important things we will discuss. Now let us see more about this one. See, there are 5 nodes in this linked list. Suppose there is only one node in a linked list. If suppose there is only one node, then it should point on itself. This is a head node. If there is only one node, then how it can be circular? If it should point on itself, then it is circular. If there are 0 nodes, no nodes at all, then this will be null. Now one problem here. If suppose I have a linear linked list, so let us call the pointer name as first. There are 2 nodes in a linear linked list. If there are no nodes in a linear linked list, then first pointer will be null. So here also, if there are no nodes in a circular linked list, then the head pointer is null. Now when there are no nodes here, there are no nodes there, both are null, how do you prove that this is circular? There is no way to show that this is circular. Just by name we cannot say. I will not use a readable name. I will use a name P. Let us say P is a pointer for the first node. P is a pointer for one of the node on the linked list. Now P is a pointer. From name you cannot say that this is circular, that is linear. Both are null. So there is an argument that a circular linked list cannot be null. How it can be null? If it is empty also, it should be circular. Yes, it is empty. There are no nodes. But it should be circular. So to support this argument, there is one more representation. I will draw that one and show you. Now this is the second representation of circular linked list. So listen carefully. We have 2 representation, this one and this one. It's your choice, whichever you want. Just based on the argument that if it is empty also, it should be circular. For that we have introduced a new representation. There are only 3 nodes in a circular linked list and the last node is pointing on first node, I should say, right? Or these nodes are circularly connected. Now this node is empty. What is the purpose of this node? This is acting as head node. It is pointing on one of the node in this circular linked list so that we can access this circular linked list. Like that we have a pointer here so that you can access all the nodes. So this node is pointing on some node so that we can access all the nodes. So this is the head node. There is no data in this node. This is not used for storing data. These nodes are meant for storing data. So how many nodes are there? Not 4, only 3 nodes are there. So if there is only one node, how the linked list looks like? If there is only one node, then this will point on itself and this is a head node. Yeah, this is circular. This is circular. So from head, if you go to this node, then from there, that node, you will be reaching that node only. So this is how it looks like if there is only one node. How it look like if there are no nodes at all. If there are no nodes at all, then this will be pointing on itself, that is head node. Now it is empty and it is circular. If you start from head, you will be reaching on head only. Then you can say it is circular. So there are two representations. This is the first representation and second representation. Now which representation should be followed? That is your choice. In your applications, you can use any one you want, either this one or this one. If you feel that no, when it is empty also it should be circular, then go for this one. And it works perfect whether you use it like this or like this. So it's not a big change that you are introducing empty node and making circular even if it is empty. That is not much important. So commonly used linked list, even in the books you find, is the first one. So we'll study the first one. What about second representation? So if we follow second representation also, the procedures will be same as that linked list only with minor changes. So that's all about introduction to circular linked list. In this video, we'll learn about how to display a circular linked list. So we already know how to display a linear linked list. So the procedure will be same definitely. But the difference is in linear linked list, last node was having null, so we were stopping there. But now they are circular. So if you start from this node, then if you go on accessing, you may be reaching back on the same node. So here we have to stop when you are reaching on the starting point again. Then the list has finished. So let us see how we can do this one. So I'll write on the code. So I will write on a function for displaying a circular linked list. Display function. It takes a pointer to head node. P is a pointer to head node. So when we call this function, we should call it like this. Display and pass the pointer head. So if you pass the pointer head, then this function is called. Let us write the function. So P is here. Okay, P is here. So let us see the procedure how to display it, and simultaneously I will write down instructions here. I have a pointer P pointing on head node. So let us say P is pointing on head node. Print this data. So printf %d P's data. So P's data is printed. Then move P to next node. P assign P is next. So P will move to next node. Okay, P will move to next node. Now next what I should do? Repeat the same thing. Print and move next. Print and move next. So okay, I will write down it in a loop, while loop. So what should be the condition here? Let us see. This will print and move next. So print and move next. So suppose P is here. Print this and move next. Print this and move next. Now print this and move next. We are back on head. So now we should not print. Now we should not print. We should stop when it has reached head once again. So what condition I should write? So I should continue when P is not equal to head, while P is not equal to head. So while P is not equal to head. If I write this condition, the problem is first time only P is equal to head. So it will not enter at all. It will not print anything. So this cannot be done using while loop then. This cannot be done using while loop. I have to do this using do while loop. Do while loop. Because first time only P is equal to head, so it will not enter in. We are talking about second time when it is coming on head, then we should stop. So better use do while loop. So first of all, let it print and move next, then we will see if it is coming back on head. So this has to be written as do while. Do while P not equal to head. So this do while will work perfectly. So this function is for printing a circular linked list. Now let me write down a display function using recursion. It is little difficult. It's not so easy like the other recursions we have seen. So let me write the function and explain you. A display function, I am going to make it recursive. This is taking parameter node. So let us call it by passing head. Head node, that is the beginning node of a linked list. Now here, in the previous recursion for a linear linked list, we were writing the condition if P is not equal to null. This was the condition. But we cannot use this condition. We never get this condition satisfied because there is no null here. Then what I have to say? P not equal to head, I should say. Not equal to head, if I say, then already it is head. First time when you pass, P will be on this head and it will never enter inside. Then what I mean to say here is that first time P and head will be same. And when the P moves around all the nodes, then again back on the same node, again it will be on same node. So second time, if it is coming for the second time, then stop. So how to know this is the first time or second time? So for that, I have to take some variable flag. So let us take a flag. So here I will declare a variable that is integer flag, and this flag value is 0. So if flag value is 0 means this is first time. If flag value is 1 means second time. So by this 0 and 1 value we can identify whether this is the first time that P and head are on the same node or this is the second time. So let us write down the code. Let us write down this. If P is not equal to head or flag equal to 0. So this will continue. See, first time P is equal to head. So this is false. But flag is 0. Yes, this is true. The next I will print it. P's data is printed and call itself again. Call itself again for the next node. That's all. But once it has print entered inside, then flag should become 1. So I should make flag as 1. So here inside I will make flag as 1. Let us trace this one. Let us trace this. First time P is here. P not equal to head? No, it's equal. False. But flag is 0. Yes, flag is 0. Then enter inside. Make flag as 1. So flag will become now 1. Flag will become 1. Then print the value and call itself for the next node. So P will be called upon next node. Now this time P not equal to head. Yes, P is not equal to head. This condition is true. Or flag equals to 0. No, flag is equal to 1. So this is false. This is true. But OR condition is used here. So if any one is true, it is true. So this is true. So it will continue. So it will print this one, then this one, then this one, then this one. Then again it comes here. So like it is calling itself again and again. Now this time P not equal to head. No, it's equal to head. False. Flag equals to 0. No, flag is equals to 1. So both the conditions are false. So it will come out of this one. And it will not enter inside. So when it is exiting, I should make flag as again 0 and exit. Now one more thing is missing. See, this flag variable, for every call a new variable will be created. Right? Inside the stack activation record, two variables are used by this function, node pointer and flag. So every time two new variable will be created inside the stack. Already you know how stack works, so I'm not going to trace this one now. So every time flag becomes 0. So it's not the same flag. What I want is for all recursive calls, there should be only one flag. Then I should declare the flag outside as a global variable. Or if I want to keep it only inside this function, then I should make it as static variable. So static variable will be just like a global variable only, but limited to a function. It is accessible only inside a function. So there will be just one single copy of flag variable for all the function calls. So how many times a function will call itself? 1, 2, 3, 4, 5, then again here 6. So 6 calls it will make, and at the 6th call make the flag as 0 and terminates. So finally, for writing a recursive function upon linked list, we have to use static variables. So this static variable will help us know whether this is for the first time P and head are same or is it the second time they are same. So I'm using flag for 0 and 1. That's it. In this video, we'll develop a C language program for circular linked list. So I'll start a new project for this one. Let us call it as circular linked list. And the language, I will select it as C language project, create a project, and this is the main function. I'll remove all these comments. I will hide panels. Yeah, the project is ready. For implementing a circular linked list, first of all, I should define a structure for a node. And node will contain data of integer type I am taking, and next is self-referential pointer, and next is self-referential pointer node, that is next. I will declare a pointer called head as a global pointer, and I will be using it in the entire program, and wherever required I may be passing it as parameter also. Now the first thing is I will write a function for creating a circular linked list by taking array of elements. So here I will write on the function create, which will take a integer type array as well as the number of elements. So for creating a node and for accessing that array, I may require some variables. So I will declare those variables. Struct node, a temporary pointer for creating a node. Now very first thing what I have to do is create first node and make head point on that node. So using head pointer, I will create a new node by calling malloc function, and first I have to typecast it, then malloc, then say size of struct node. So this will create a head node, and a head node should have the data, that is the first element from an array, that is 0th element. Then head node's next pointer should point on head itself. That's it. So it is circular now, and there is only one single node. Now for the rest of the nodes, I will scan through this array and I will create nodes and go on linking them with this linked list. So for this, I will take one more pointer called last. That will help me for inserting a new node always at the last. So let us make last point on head. Now using for loop, I'll scan through this linked list for I assigned 1, I is less than n, and I++. Now inside this for loop, every time I will create a new node. So for creating a new node, this is the code. I will copy it and paste it here. This is the node creation, and t's data I should assign it from a of I. Then I have to make linkings and I should insert it after the last node. So t's next should be pointing on last next because this is circular, so I cannot use null here. Then last next will be pointing on new node T, then last should move on to new node T. That's it. So with this code, a linked list will be created from a given array and it will be a circular linked list. And this is how I made it circular, by making head pointing on itself, and every time I am trying to maintain that same link with the help of last. Now inside main function, I will create an array of elements 2, 3, 4, 5, 6. Then I will call create function by passing array as well as the number of elements. So I am passing 5 elements. So 5 elements are passed. A linked list should be created. Then next I should display a linked list. For displaying a linked list, I will write down a display function here, void display. It should take a pointer to a node, that is head node. So I will call it as pointer h for head node. Then as we have discussed that it has to be implemented using do while loop. So do while, every time I should print an element from h caps data and also move h to next node. H assign x caps next, it will be moving on to the next node. And here in a while condition, while h is not equal to head. Head is a global variable, so it can be accessed directly. That's all. Then after displaying all the elements, let us give a line gap so that we can clearly see the output. That's all. Now from the main function, I should call display head. Let us run this. Yes, I got the element, that is 2, 3, 4, 5, 6. It is displaying all the elements. A circular linked list is created and elements are displayed. Now here I am getting a warning that this malloc function is used because I did not include header file. Yes. Now I will not get any warning. If I run the program, it runs smoothly and I got all the list of elements. If I debug it by putting a breakpoint upon the display function, then I will run it. Let us look at debug window. Here is a debug window. Head is a pointer pointing on the element, that is 2, and 2 is pointing on 3, 3 is pointing on 4, 4 is pointing on a node, that is 5, 5 is pointing on a node 6, then 6 is pointing on again 2, then 2 is pointing on 3. See, it is circular, so if I go on clicking, it never stops. So you can see that from 2, 3, 4, 5, 6, then again there is a link to 2. So yes, it has formed a circular linked list. So it will never stop now. If I go on expanding this one, I'll be getting the elements below this one. Same elements will be repeating again and again. So this is enough to understand or confirm that a linked list created is circular. So I'll stop this. The next, I have shown you a function for recursive display. So let us write down recursive display R display, which takes a node pointer to head, that is h. Then inside this function, I have shown you that we should have a static variable, that is flag, and flag should be assigned with initially 0. And the condition we should check that h is not equal to head or flag equals to 0. If both of these are false, then it will stop. So right now flag is equals to 0, so it will continue. So what we'll do is, first of all, we'll make flag as 1. Then we will print the element, that is percentile d, and h is the pointer I am using here, and display its data. Then after that, call recursive display by passing h next node. So instead of p, I am using h here. Don't get confused with variable name. In linear linked list, always I was using p as a variable. Here I am using it as h. And on whiteboard also I have used p. But while writing the code, I am using h. Then when this is becoming false, I should also make flag as 0 once again. Now let us see how it works. I'll remove the breakpoint, and instead of display, I will call R display for the same linked list. Let us run the program. Yes, it is displaying 2, 3, 4, 5, 6. It is perfectly displaying all the elements. So that's all. You can write down these programs by yourself. See, practicing these programs is very important. You must practice them at least once. Then it becomes very handy and very easy for you to write the code. And the code is becoming lengthy and lengthy every time as we go on moving to the next topic. So that's all with this video. We have seen creation and recursive display. And for the remaining operations on circular linked list, I will be using the same program. In this video, we'll look at insert operation, inserting in a circular linked list. So already in linear linked list, we have learned how to insert. So let us recall few things from there. So first of all, I will label the nodes. I'll give the indices to the nodes. Let us call this node as 1, first node, second, third, fourth, and fifth node. So what are the positions I have for inserting a new node? I can insert it before first node, that is head node. So this is 0th index and this is first. This is in between second and third. This is second and this is third and this is fourth and this is fifth. So I have total 6 positions for insertion. I can insert a new node anywhere out of these 6 positions. If you remember, in linear linked list, we had 2 cases: inserting before first node or inserting at any other given position. So here we have 2 cases: inserting before head and inserting at any other given position. Whatever the position you want, you can insert it there. So 2 cases are there. Let us look at second case first, inserting at any other position. What is the procedure? Suppose I want to insert a new node at a position 4, means here I want to insert a new node. Let us insert a new node there. I'll remove this. First of all, create a new node with the help of a pointer t and insert data. Now for inserting a node here, I should link this one to 5th node and 4th node should point on this one. So I have to manipulate this 4th node also, change that one. So for that I need a pointer here. So that pointer I can bring it from first node, that is head node, and I should move the pointer 1, 2, 3 times. Then the pointer comes here. Once the pointer comes here, I can make t's next point on p's next. P's next is this 5th node, and also I can modify this pointer, that is make this p's next point on new node t. This is the method for insertion. So this procedure is same as what we have seen in inserting in a linear linked list. So same procedure is there. Let us have a look at the code once again. I'll just write on the code. Here I have written the code. I need a pointer p upon head node. Then with the for loop, move p for position -1 time. If the position is 4, so then move p for 3 times. Then create a new node. I am creating a new node and filling the data, t's data. So data is filled. Then t's next is p's next. So t's next is pointing on p's next, which was already pointing here. Then p's next is t. So p's next is pointing on t. So this is the code for inserting at a given position. The code is same as what we have saw in linear linked list. So you are already familiar with the code. Then one more important thing, analysis. This procedure takes minimum time when you want to insert here after first node, and it takes maximum time when you want to insert after last node, if this is the last node, right? So after head node, if you insert, it takes minimum time. So minimum time is constant time. So this procedure takes constant time when you want to insert here, and it takes maximum order of n time when you want to insert after the last node, right? So in a circular linked list, there is one position where we can insert in constant time, and that position is after head node. Now we will see how to insert a new node before head node. Now for inserting before head node, what are the things I have to do? Let us see the procedure. First of all, I should create a new node with the help of some pointer t. Then insert data. Then t next should point on head. Okay, this is done. But one more thing I have to do. This last node should point upon t. So I have to manipulate or modify this last node. So I should reach last node. So how I can reach last node? Take a pointer p from head node and go on moving it and stop here. On what basis I can stop there? Because its next is equal to head. So stop on the node whose next is equal to head. So stop on that node. So p will move and stop at this node. Then what I have to do? P's next should point on new node t. So p's next, that arrow link is coming till here, you can see. So I'll extend it and make it point on t. Now if you start from head, this 8 will send on 3, 3 will send on 9, 9 will send us on 6, 6 will send us on 2, and 2 will send us on 10, and 10 is linked to 8. So this node is inserted inside circular linked list. Now one last thing. Shall I move head and call this as new head? So if somebody comes on the left hand side of head and sits there, will you make him a head? No, need not be. If somebody comes before first and sits before first, then you can call him first, new first. But a new head is not necessary. So logically, you don't have to move head. Head will be that same node. If at all you want to change, you can move that head. I prefer let the head be same node. Don't move it. Just we have inserted a new node before head node. This is same as inserting a new node after last node. What was the last node? 2. Then after that 2, who is there? 10. So this is the last node. And then it is connecting to head. So inserting before head or after last node is the same. Only the difference is whether you want to move head there on a new node or not. Alright, procedure is same. So head is your choice, moving head is your choice. So inserting before head or inserting after last, both are same. So let us write down the procedure for doing all this. I'll write down the code here. So what I need is, I will create a new node and fill the data. So first I will create a new node. Node is created. Let us fill the data. Then let it point on head node. So t data is filled with the value and t's next is pointing on head. Now what I have to do is, I should go on the last node and make it point on a new node t. So for that I should take a pointer p from here and make it move till last node. So for that I will have one more pointer, node p assign head. Now that should move till last node. So while p's next is not equal to head. So it will stop when p's next is equal to head. So right now p's next is equal to head. So it will stop. And every time what I should do, move p. P is assigned p is next. So p will be moving upon next node. So this loop will move p till the last node. Then that last node should point on new node t. P's next should point on t. Then if you want to move head, you can move head on new node. Head assign t. So this head node will point on new node. So this is the procedure for inserting before head or also after last. So even this procedure is also inserting after last, but this is based on the position index. So there were two cases, inserting before head or inserting at any other position. So this I can call it as inserting at index 0, and this is any other index. So let us combine these two and write a single insert function. So I will write a single insert function, then I'll explain that one. Here I have an insert function. Let us quickly look at this one. See, insert function is taking two parameters: at what position you want to insert, at what index you want to insert, and what value you want to insert. Then here, first condition, if position is 0, means you want to insert before head node, then already we have seen what are the things we have to do. But here I have taken care of one more condition. See, here I have created a new node. Then in this statement, condition I am checking, is it the first node? It will be a first node. If head is null, means it is the first node. If this is the first node, then head should point on that node, and head's next should point on itself. Like already we have seen in previous video, if there is one single node, then head node will be pointing on itself. So that's what I have done. If head is null, means this is the first node. So I have taken care of that one. Otherwise, the procedure already I have shown you. There is no space, so I have combined more than one statements in a single line. So already you have seen the procedure. You should take P till the last node, and this node should point on head, and that last node should point on new node T. So all that procedure I have shown here. Else, if there is any other position, then this is the regular code for inserting a new node at any given position. So the same code is there. But one thing is missing in this code. Here I am not checking whether the position is valid or not. Like suppose 1, 2, 3, 4, 5 nodes are there. So I can give indices from 0 to 5, not beyond that. So I am not checking here whether the position is going beyond that one. If I am not checking what happens in this code, you try to analyze this one. Right? When I write the program, that time I will include that condition also. I will check that also. Finally, analysis of insertion is that if you insert a new node after head, that is after first node, the time is constant, then it is growing and growing. At the last node it is n, or even before the head node also it is n. So there is one position where the time is constant. That's all about insert. In this video, we will write a insert function for inserting a node in a circular linked list. So already I have started a project in the previous video, and the same project I am using, which is already having functions for creating and displaying linked list. I'll update the same program, and here I will write on a function for insert. So let us write a function above main function, void insert. I will pass head as a pointer. So let us take it as P because we have been using P. Next is the index at which I want to insert. Then next is the element that I want to insert. Then for insertion, I may require few things like a temporary pointer. So I will declare a pointer that is T. Then I may require some variable. So I'll take some variable I. Now, as in linear linked list, we were first checking whether the index given is valid or not. So even without checking also we can do it. Like if the index is 0, then definitely we are going to insert any node. Otherwise, if the index is going beyond the length of a linked list, then we should stop. So here, first of all, I will write on the code for checking if a index is 0. So first, if the index is 0, the position is 0. If the position is 0, then I have to insert a new node before head node. So for that, first of all, I should create a new node. I will write on the code. I have created a new node. Then set the data to X. Then node is created and the data is set in this new node. Now, as we are inserting before head node, so first of all, check if head is already null. If head is already null, means this is the first node you are going to insert. Then if it is the first node, then head should point upon T, and then head should point itself. Head caps next should point on itself, that is head. Otherwise, there are some nodes already in a linked list, then I should take the help of pointer P and scan through a linked list and reach the last node and make necessary changes. So using while loop, I can say while P's next is not equal to head, go on moving P assign P's next. Then once P has reached on the last node, then P's next should point on new node T, and T's next should point on head, then move head onto new node T. So that's all. So already we have discussed this type of code on whiteboard. So this is inserting before head if index is 0. Else, if the index is not 0, then the code is same as the code for inserting in a linear linked list. So again, I have to create a new node and set the data. So first of all, using for loop, I will move p and make it point on the index where we want to insert. So index is less than this one, and then I plus plus. In the same line, I will write down p assign p's next. So p will be moving to the nodes and it will be stopping at the node where we want to insert. Then create a new node. So for creating a new node and initializing data, already we have the code. So I will copy that code here. Yes, node is created. Then the necessary links I have to modify, that is a t's next should be pointing on p's next, and then p's next should point on t. That's it. So a node is inserted. So the code is little lengthy. So already I have discussed everything. Now just I am typing it for the demonstration. Now one thing I did not do here, that I am not checking whether the index given is valid or not. Like in a linear linked list, you remember we have written the code for checking if the index is valid or not. So here I should have some code like if index is less than 0 or index is greater than count or say length, then stop, don't insert anything, just return. So I should write a function for length also. Okay, here I will write on a function for length, integer length, struct node star p, and here I should have some variable length, and this is initialized with 0, and with a do while we can go on incrementing length as well as moving p to next node until it reaches the last node, that is while p is not equal to head, and after this return length. That's all. It's a simple function for finding length. So already we are familiar with this code. We have written this in linear linked list, but now the loop is different. We have to use a do while loop for this one. That's all. So insert function is ready. Now here inside the main function, I will try to insert a new element, that is 10, after node 3, that is at second position. So insert, I should pass head as a pointer, then index, that is at 2, and I want to insert value 10. Then after that it will display a linked list. Yes, 10 is inserted after 3. You can see that 2, 3, 10, 4, 5, 6. It's working. Let us check if we can insert after 6, that is at index 5. So 10 should be inserted after 6. Yes, 10 is inserted after 6, that is 2, 3, 4, 5, 6 and 10. Now let us check with index 0. Can we insert it before 2? Yes, it is inserting. 10, 2, 3, 4, 5, 6. Yes, it is working. So that's all. There's the insert function. So write this program by yourself, write this function. A PDF is given. You can look at the program in that PDF and you can type it by yourself. For any help, you can use that PDF. In this video, we'll look at delete operation. There are two cases for deletion, just similar to linear linked list. Two cases are deleting head node, that is this node. So what is special in this one? If this node is deleted, then some other node you have to make it as head node. You have to move head. So whichever one you can select because it is circular. So we will be selecting just next node as a head node. Now second one is deleting a node from given position. So any other node like third node or fourth node, fifth node, deleting a node from any given position. So this procedure is same as deleting from linear linked list. So first let us look at this procedure. Let us look at these steps quickly because we already know about this one. Then next we will look at deleting head node. So let us see deleting node from a given position. Let us delete a node from fourth index, that is this node I want to delete. So what is the procedure? If you want to delete this node, then you should manipulate this node and make this third node point on fifth node. Then you can delete this node. So for that, I need a pointer on this fourth node also and third node also. So you remember we will have one pointer, that is a tail pointer. So we'll take two pointers. One pointer will be moving and the second pointer will be following. Or else we can bring a pointer till third node and take one more pointer on next node. or we can bring 2 pointers from the beginning. So 2 options are there. So now I will be bringing just 1 pointer from here till 3rd node, then I will take 1 more pointer here. So I will not be moving 2 pointers, I will be just moving 1 pointer. So let us see. Let us take a pointer P on head node. I have to delete 4th node. So I should bring it on 3. So how many steps it should move? 1, 2. So only 2 steps. 4th node means just 2 steps. It means 5th node means 3 steps. So 2 steps less. So I need a pointer P. So I will directly write on the code P assign head, P starts from head. So with this, this for loop will move P for position -2 times. So P will be pointing on a node before the node which we want to delete. So 4th node means 3rd node. Now I need a pointer on 4th node also. So take a pointer Q here. So Q is P's next. So Q is P's next. So Q will be pointing on the next node. Now what changes I have to make? P's next should point on Q's next. So P's next should point on Q's next. So P's next is pointing on Q's next. So this is over. Now I can easily delete this node. It's not a part of linked list. So I can take out the value and delete it. So take out the data in variable X and delete the node. So this procedure is same as deleting from linear linked list. Now let us see deleting head node. If I am deleting head node, this node I can make it as head node, but the last node should point on this new head node. So this is the modification I have to do. So if I am deleting first node. So for doing this, I should take a pointer P upon head node and move it until it reaches last node as per this head node. Then I should make that last node point on next node of head. That is, this link will change. It should point here. Then delete head and move head to this node. So head will be removed and this node is deleted. These are the steps. So for this, let me quickly write down the procedure for this one. So I will write down the pieces of code that perform these operations. I need P upon head. P will move until it reaches last node. So P is moved until last node. You already know the condition is P's next is not equal to head. Then P's next should point on head's next. So this is pointing here. This is pointing here. Then I should take out the data and delete this head. Data is taken in X. Delete head. This node is deleted. Then I should make head point on this node. What is this node? P's next. So make head point on P's next. So I have the code for deleting head node. I have the code for deleting any other node. Now analysis. The time taken for deleting head node is n because I have to take P till the last node. And the time taken here is minimum constant, maximum is n. So for which node it is minimum? Second node. If you are deleting second node, time is constant. Otherwise it is n. So I will write on a complete function for deletion and I will show you. So here I have a complete delete function. Let me read it out. If position is 1, that means I want to delete first node. Then we should have a pointer P moving up till the last node. So this is the code for moving up to last node. Then here I have taken the data from head node. In these statements, I am taking care here that if P is equals to head, means this is the only node. There are no more nodes, just there is single node in a linked list. Then if you make P point up to last, then P will remain there only. If there is a single node. Then if single node is deleted, then I should make head as null. So that I am taking care of here. So if there is a single node, then I should handle it specially. Otherwise, make P's next, that is point on head's next. Last node should point on this node. Then delete this node and move head to this node. These statements are there already. We have seen these statements that are in single line I have written. Then this is the code for deleting a node from any other given position apart from index 1 or position 1. Now here again I did not check the condition whether the position given is valid or not. And if I am not checking, what happens? You have to analyze this one. Figure out, take some position that is beyond this size 5 and take a linked list 5 and take the size as 6 or 10 or something. Then check what happens. While writing the program, I will write down that condition. In this video, we'll look at the demonstration for delete operation. So I'm continuing in the same project. So just above the main function, I will write down a delete function. It will take a pointer to head node. Let us call it as P, and the index from where we want to delete an element. Then I may require more pointers like Q. I will take a pointer Q also, and I will take a integer variable that is for traversing a linked list. Then the first condition, if index is valid or not. So if index is less than 0, or if index is greater than length of a linked list, so I should pass head to this one. If so, then I will return -1 saying that the index is invalid. Now otherwise I can delete, but for deletion I should make sure that if it is head node, that is index is 1, then I should delete head node. So if index is equal to 1, then I have to delete head node. So for deleting head node, P is already pointing upon head node, like I have to pass this as a parameter. P is upon head node. Then I should traverse through a linked list and I should make P point upon the last node. So using while loop, I will move P while P caps next is not equal to head. I'll be moving P. I'm writing in the same line. P is next. And once it has reached on the last node, then I can take the data from head node in a variable x. Data is copied. Then one more thing, I need a variable x also. So I will declare variable x on the top and come back to this line. Then after deleting head node, I should also make sure that is it the only node, that is it a last node. If it is last node, then head will be equal to P. If head equal to P means then I should free head. Instead of delete, we have free function in C language. Then I should make head equal to null, means head is assigned with null. Else, if it is not the last node, if it is not the only node, then I should make P's next point upon head's next, so that head node is released logically. Then free it from the main memory, that is from heap memory. Then make head point on next node of P. P is next. So this is all what I have to do if the index given is 1. If index is not 1, then the procedure is similar to deleting from a linear linked list. So for that, I will use a for loop and make it repeat for index -2 times. So while I is 0, I is less than index -2 and I plus plus. And every time move P to the next node. Now P will be pointing a node before the node that we want to delete. Then we need Q to point on P's next node. Then I can delete that node with Q, and that's the node actually we want to delete. So but before that, P's next should point on Q's next. Then take the data from Q, then free Q. That's all. It will be deleted, and finally I should return the deleted element, that is X. See, there are more than one cases, like if index is 1, that is we are deleting first node. Then is it a last node, so we have to make head as null. Otherwise delete head node and make some new node, next node, as a head node. And if it is not first index, then we should delete the element, just like how we have deleted in a linear linked list. Now inside the main function, already we have created a linked list out of these 5 elements. Now let us call delete function by passing head, and let us delete node from index 1, that is first node 2. Then after that, our display will display a linked list. Let us run. We should get 3, 4, 5, 6. Yes, we got 3, 4, 5, 6. First node is deleted. Let us delete second node. So 3 should be deleted. We should have 2, 4, 5, 6. Yes, we got 2, 4, 5, 6. Then let us delete the last element, that is index 5, 6. Node 6 is deleted. Now we have 2, 3, 4, 5. So it's perfectly deleting all the indices, whichever the index we are giving, it's deleting an element. Let us give an index 8 and try this one. The linked list is as it is 2, 3, 4, 5, 6 because the index is invalid. Already we have checked the condition here that if the index is invalid, then return -1. Otherwise, it will delete and return the element. So in my main function, I am not taking that deleted element. If you want, you can take the deleted element and display it. So that's all with this delete function. And upon circular linked list, I have shown you display, insert, delete, and length function. Rest of the function, what all we have done upon linear linked list, you can write them on circular linked list also. And that's a student exercise. In this video, I'll give you introduction to doubly linked list. This is an example doubly linked list. The previous linked list what we have seen, now we can call them as singly linked list. So this is doubly linked list. So what is this singly or doubly linked list? Let us look at this one. Singly linked list, every node will have a pointer to next node in a singly linked list. But here you can see that a node is having a pointer to next node as well as previous node. So it means from one node I can go forward as well as I can come backward. So I can access this list of elements bidirectionally. I can traverse them in either direction. Suppose I am starting from first node, that is number 6, then I can go to 9, then 3. Suppose I want to go back previous, so I can come back here. Or I want to go to next, I can go to next. Like inside browser, if you have visited some website and you have clicked some links and you have gone deeper and deeper, then you can go forward and backward afterwards. So if you come back, you will be back on the previous page. If you say I want to go forward again, so then you can go to this page. So every new page will be added to a doubly linked list like structure so that you can move in between the pages if you want. If you take the example of a contact list in our mobile phone, then you can scroll up and down, you can move in both the direction, you can go to next contact or the previous contact. So that's what it is possible using doubly linked list. So now let us see how to define a node of a doubly linked list, a particular node. So I'll show the node structure. So this is a node structure. Node is having 3 elements or 3 data members. One is data and one is pointed to a previous node and next is pointed to a next node. So there are 3 things. So every node is containing 3 things: data pointed to the previous node, pointed to next node. Now I will define the structure for this node using C language. This is a structure in C language. First is a pointer of type same node, then next is integer type data, and again the pointer of type node, that is next pointer. Now how to create this node and how to fill up the node, we already know, we don't have to learn anything new. It is same as singly linked list. So just as a sample, I will create one node and fill some data and show you. So for creating a node, I should have a pointer. So I will take a pointer, struct node t. T is a pointer. Suppose t is a pointer. Now to that t, I will create a new node and assign. So for creating a new node in C language, we should use a malloc function, but that will be a little lengthy. So I am using C++ syntax, that is new, for creating a new node. So new node, a node will be created. This will create a new node having 3 members. Now this is data and this is previous pointer and next pointer. So I'll fill up all 3, first previous, then data, and then next. T's previous is null, so this is null. T's data is 10, so the value 10 will be written here. T's next is null, so this is null. So this is how we can create a new node and fill the values. And if you want, you can link this node in this linked list also. Now next thing, what are the operations that we can perform on doubly linked list? Same as whatever we have done on singly linked list. Like displaying a linked list, counting the number of nodes in a linked list, finding maximum, finding minimum, searching, various operations. So the same set of operations, but only the data structure is different. The difference is that you can move in both the direction. That's all. The benefit of using doubly linked list is we want to access in either direction. That's it, nothing more than that. In the next video, we will see few operations on this doubly linked list. In this video, we will have the demonstration for doubly linked list. So we will create and display doubly linked list using C language program. So I'm starting a new project for doubly linked list. I will call it as doubly LL, that is for linked list, and the language selected is C language. Now next, create a project. Project is ready. Go to the main function, clear all these comments. Project is ready. Now for implementing doubly linked list, first of all, we will have to define a structure for a node. So as we have already seen that it will have 3 members. First one is struct node, that is a pointer for previous node, and next is data, integer type data I am taking. Next is a struct node that is pointed to a next node. Then here I will take a pointer for first node that is first and initially assigned as null. Now as we have done for linear linked list and circular linked list, same way I will write a function for creating a linked list. It will take a array of elements and create a linked list. So first is array of elements, then the second one is number of elements. Now here for creating a new node, I should have a pointer, that is stem pointer t, and also for last node I will take one pointer. Then I may need a variable like I for scanning through an array. And if any more variables are required, then I will declare them. Now the first thing I have to do is create a first node by using first pointer. So struct node. For this doubly linked list node also I have given the function name as struct node. So size of struct node, a node will be created using malloc function. And one more thing I have to do is that I should include header file, that is stdlib.h. Then coming back to the create function, a node is created, then in first data I should have element from first location of an array, that is index 0. Then I should set the pointers like previous as well as first pointer, that is next, to null, because this is the only node. And one more thing is I should set last as first. So last is also pointing upon first node. Now with the help of this last pointer, I can continue creation of rest of the nodes and go on joining them in a linked list. That I can do it using for loop. So for I assign 1 onwards, because 0th element already we have taken, then I plus plus, then inside for loop I should create a node every time. So already the code is here for creating a new node. I will copy that code and paste it here. Then I should set the data of this new node as a of I, and as I have to always insert a new node after the last node, then I should say t's next should be same as last next, and t's previous should be same as last. Then last pointers next should be pointing upon t, and after that I should make last point upon new node t. That's all. These are the steps for adding a new node every time at the end of a linked list. Then next I should have a function for displaying a linked list. So I will have a function display which will take a struct node pointer that is upon the first node, let us say p, and while p is not equal to null, it will be displaying the element. So printf display an element %d and p's data. Then p should be keep on moving upon next node. Then after printing all the elements, I should give a line gap so that I get some formatted output. I get some free space after the output. That's all. Then likewise, I will also write on a function for finding the length of a linked list, that is length. It will take struct node pointer to first node. Then here I will take one length variable that is initially 0. Now using while loop, I can traverse through a linked list by every time incrementing length and also moving p to next node. Then finally at the end of the function I should return length. So yes, all the functions that we have been writing for linear linked list and circular linked list we have written here also. Now inside the main function I will create a linked list and display its length and also display its elements. So first of all I will take an array of elements like 10, 20, 30, 40 and 50. Then I will call a function create by passing array and the number of elements are 5. So create function should create all the elements. Then I will print the length of a linked list. So first /n, then I will say length is %d, then also /n. Then here I will call the function length by passing first pointer. Then I will also call display function for displaying all the elements of a linked list by passing first pointer. That's all. Main function is ready. Let us run the program. Yeah, here length is 5 and it is displaying all the elements, that is 10, 20, 30, 40 to 50. So everything is perfect. So practice this program. I'm providing this same program code as a PDF below this video. You can download this, and if any help you can look into this one, or if you face any problem then you can contact me in question answer session. That's all. In this video, we will learn how to insert a new node in an existing doubly linked list. There are two cases for insertion. First is inserting before first node, and second one is inserting at any other given index, So right now in my example, there are 5 nodes. What are the positions where I can insert a new node? I can insert a new node before this node. So let us call that index as 0. So I can insert at index 0, or after this node, this is 1 and this is 2, second index, and this is third index, fourth. And if I am inserting at last after the 5th node, then this is 5th index. So total 6 positions are possible where I can insert a new node. So inserting at index 0, I am calling it as inserting before first node. So let us look at these cases. So first, let us see inserting before first node. What should be the procedure? Let us see what are the steps required for inserting a new node before first node or at index 0. First step is create a new node with the help of some temporary pointer. So I will create a new node. Then set the value here. So I am setting the value 10. Then how many links I have to modify? 1, 2 and this one. Total 3 links I should modify. So first I will make this as null, previous as null. So its next should point on first, and first previous should point on this one. So total 1, 2, 3 links I have modified. Then after modifying 3 links, this has become a first node. 10 is the first node. From 10 you can go to 6, 9, 3, so on. Or from 6 if you come back, you can come on 10. So I should bring that pointer first upon this new node. So bring the pointer first upon new node. So move first from here. So these are the steps I have to perform. Let me write down instructions for this procedure. First of all, create a new node. New node is created, then fill the data. This is filling the data, set the value here. Then make this link as null. Then make this link point on first, T is next on first. Then make first previous point on T. First previous on T. Then bring first on new node T. First on new node T. So these are the steps. Total 3 links are modified. 1, 2, 3. These are the 3 links modified. And I need one extra pointer T for creating a new node. So the number of steps involved here are 1, 2, 3, 4, 5, 6. Total 6 steps are there. So 6 is constant. So the time taken for inserting a new node is constant. Now let us look at another case, second case, inserting at any given position. I want to insert a new node at position 4, that is index 4. So if position is 4, so here I want to insert a new node. So let us see what are the steps required for doing this one. First of all, create a new node with a temporary pointer, say T, and fill the data here. Now this node should come in between 4th and 5th node or after 4th node. So what are the links I have to modify? I should make this T's next point on 5, previous point on 4. Then 4's next should point on T, 5's previous should also point on T. So total 1, 2, 3, 4. 4 links I have to modify. So for modifying these nodes, I should have a pointer over this node. Do I need on both the nodes or just one node is sufficient? I think one node a pointer is sufficient. So let us take one pointer and bring it on 4th node. So directly I cannot bring a pointer there, so I have to bring it from first node. So take a pointer P and move it so that it comes on 4th node. So how many times it should move? 1, 2, 3. So it should move for 3 times, then it will be on 4th node. Now I have a pointer P upon 4th node. I will make modifications in links. Let us do it. First one, T's next is P's next. This node address is present here. P's next, that is T's next. This is the first one I am modifying. I'll remove this. We know its position is 4. Then T's previous is P itself, this node itself. So this is the second one I am modifying. Then third one, this node's previous. So I can reach this node now by T's next as well as P's next. I can reach here. So P's next is this node. Its previous, this one, should point on T. So this is the third modification. Then last, P's next should point on this node. So this is fourth modification. So I have changed 4 links. So that's how this is inserted. So from node with 7, if I say next, I'll be going on 10, then next means 2. Then again from 2, if I come previous, it's 10, then previous means it is 7. So I'm able to move in either direction, and that node is inserted in between 4th and 5th node. Now let me write down the instructions for this one. So first of all, create a new node. Then fill the data in the node. Data is filled. Then I need a pointer P upon this 4th node. So as we are already familiar that I should take a pointer P from here and go on moving it for position -1 time. So I can do it using for loop. So directly I will write down the code for moving P so that it reaches 4th node. So this for loop will move P so that it reaches 4th node. Now I have to modify links. So first link, as I said, T's next should be P's next. So T should point on this node and whose address is present in P's next. So it is modified already now. So it was present here. So T's next is P's next. Then T is previous. This should point on P. T is previous should point on P. Then the third link I modified was this one. So this I have to handle it specially. What is special in that? See, this is T's next or P's next previous. So whether there is a next node available or not. See, if I am inserting after 5th node, then there is no next node. So if I say next, okay, it is null, but I cannot say it's previous. So this third link I can perform only if there is next node present. So here I should do it conditionally. I should check that if P's next is available. This is sufficient. If P's next is not null or not 0, it's not 0. Then say P's next previous as a T. P's next previous as a T. P's next, this one. This one means this node. Its previous means this one is assigned with a T. So I have modified this third one. Now fourth one, P's next is T. So P's next is T. So all these steps are over. So these are the steps for inserting a new node at a given place. Now analysis. This was for inserting before first. Time was constant. What about this? The time depends upon movement of P. If P moves up to the last node, the time is maximum. If P remains on this one only, means if you are inserting after first node, then time is constant. So this procedure's minimum time is constant, maximum time is n. So minimum time is constant and maximum time is n. Then about pointers, links. How many pointers are required? In this case, 2 pointers are required. If you are inserting before first, just 1 extra pointer is required. How many links are modified? Inserting before first, 3 links are modified. If there is first node. If the linked list is null, just 2 links are modified. And if you are inserting at any other place, 4 links are modified. If you are inserting at the last, only 3 links will be modified. This one will not be done. So minimum 3 links, maximum 4 link. I said that this third link, we have to handle it specially. So it may or may not be performed. Now I will write a single function while writing a program. So I will write a program and show you that time I will combine these two and make it as a single function. That's all about insert. In this video, we look at a demonstration of insert function in a doubly linked list. So already I have started a project for doubly linked list in the previous video. So I'm using the same project here. Already I have structure defined and all the other functions like create and length and display functions are available. Now a new function we will write here about the main function, that is insert. So let us write function insert. Insert will take node pointer to the first node and it should take an index where we want to insert and the element that we want to insert. Now I may require few variables, so I will declare them, that is node pointer t for new node. Then I need some variable like I. So if any more variables required, I will declare them. So this has become a common thing for us now. We have written the same function upon 2 linked lists and it's going to be similar with minor changes. So first of all, I should check whether the index given is valid or not. So if index is less than 0, or if index is greater than length of a linked list, for length I should send first, or I can send p also, then we will simply return. That means we will stop the function, we will not do anything. If it is valid, then we should check if the index is 0. If the index is 0, then it's a special case. We have to insert a new node before first node. So first of all, I will create a new node using malloc function. So I already have the code, so I will copy that code here. So this will create a new node. Then I should set a data. T's data should be set as x, and t's previous should be pointing upon null because there is no node before this node, and t's next should be pointing upon first node because we are inserting it before first node. Then first node's previous pointer should point on this new node, that is t, because this is linked before first node, and first should be brought upon t. Yes, these are the steps already we have seen. So that's all. This is the way we can insert a new node at index 0, that is before first node. Else we have to insert it at any other position. So for inserting at any other position, first of all we should move p onto that index. So for that I can take a for loop, and for I assign 0, I is less than index minus 1 and I plus plus, and every time p should be moved onto next node. So p will go and stop at a node after which we want to insert. Now create a new node with a malloc function. When a node is created, I will set the data for this node, set data assign x. Now I have to provide proper links to insert this new node at a given index. So first thing, I will set the previous pointer of this node as p, and next pointer of this node is same as p's next. Then I have to make two more changes in the links. Like if p's next node is there, means if it is not null, then I should make p's next previous as t. Then I should make p's next also point on t. So 4 links are modified, and this one of the link is conditional. That is, if next node is there, then only we can do it. If it is not there, then only 3 links will be modified. Otherwise 4 links will be modified. That's all. This code will insert a new node at a given index in a linked list. So already we have a linked list here created for these elements. So let us try to insert a new element at some given index. So I will try to insert after second node. So I will give index as 2 and the value is 25. So after 20, 25 should be inserted. Yes, it is working. 10, 20, 25, 30, 40 and 50. Let us insert this element after index 5. So let us see whether it works. After 50, 25 should be inserted. Yes, it is getting inserted. Let us change the index to 0. Yes, 25 is in the beginning. So it's working perfectly. So that's it. You have to practice these functions. This will improve your programming skills and improve your logical thinking. In this video, we'll look at a delete operation on a doubly linked list. There are two cases for deletion. Just like a linear linked list already we have seen. So two cases are there, that is deleting first node or deleting from a given index, deleting a node from a given index. So deleting first node is a special case and deleting any other node is a common case and it's another case. So first we will see how to delete first node. What are the steps required? Say I want to delete this node. After deleting this node, this should become the first node. First is pointing here, so first should move to the next node. So I should move first. But before moving first, let us take a pointer p upon this node and then move first. So first will move to next node. So take p upon first and move first to next node. So this is the next node. Now, with the help of pointer p, take out the value if you want, take out the value and then delete the node. So this node is deleted. And first previous, this should point as null. And while doing this, you should be careful whether first is really pointing on some node. Suppose this was just a single node, then first will become null. So you cannot make first previous as null. There is no first previous. So I have to do this little carefully. That check whether first is not null. If not null, then make it as null. So first previous, make it as null. Let me write down the steps. First step is bring p upon first. So P upon first. Then move first to next node. First assign first caps next. First assign first caps next. Then take out the value and delete the node. P's data is taken in X and delete the node. Node is deleted. Then when this node is deleted means this is gone, right? So I should make this as null. So that I should check if really first is pointing upon some node. So if first means first is not null, then the same line I will write down, make first previous as null. So I have to make this as null and remove the link from here. First previous is made as null. So this is made as null. So these are the steps required. And these are constant steps. 1, 2, 3, 4, 5. Few steps are there. So 5 steps. So the time taken will be constant. Now let us see the procedure for deleting a node from given index. Suppose I want to delete fourth node. Position is 4. Suppose position is 4. How to delete that node? Let us see the procedure. If I have to delete fourth node, then this third node should point on fifth node and fifth node should point on third node. Then this node is not reachable. You can delete the node. So for this, I have to modify two nodes and delete one node. Delete fourth node, modify fifth node and third node. So two nodes I should modify. So total how many nodes are involved here? 3 nodes are involved. Then how many pointers we need? 3 pointers. Is it possible using single pointer? If I have a pointer here, yes, I can say next and I can access this node. I can say previous and I can access this node. So let us do it using single pointer. So where I should have a pointer? I should have a pointer upon this node. So let us bring a pointer P from first to that node. So if I have a pointer P and bring it here, so how many times I should move it to bring it on fourth node? 1, 2, 3. So that code I will write down here. P is upon first and move P for position -1 times so that it comes here. So with this for loop, P will come on to this node. Now what are the links I have to modify? P's previous, its next should point on P's next, this node. So this is the address. So P's previous next should point on P's next, this node. So P's previous next should point on P's next. Then this link will be pointing on this one. So if you come from here, 6 sends you to 9, 9 will send you to 3, 3 will send you to 2. So I am not able to reach on this node. So one link is removed. Now next link I have to remove. P's next means this nodes. Its previous should point on this node. So that is P's previous. So here I should write on the address of this node. So the address of this node is available here. So it means this value should be copied here. So P's next previous. P caps next caps previous should point on P caps previous. So but before writing this, one important thing. If suppose there is no node after fourth node, fourth is the last node, right? There is no node on the right side. Next there is no node. Then I cannot access it. It's an error. If you try to access nulls next or nulls previous, that's an error. So I can access that node if it is present. So I should check the condition whether P's next is there or not there. Means is it null or not null. So if it is not null, I should do it. So first of all, check P's next. Is it null or not? If P is next, then P's next previous. P's next previous should be assigned with P's previous, this node's address that is present here. So assigned with P's previous. So this link will also modify. Now this node P is not reachable. From here also you cannot reach P, from there also you cannot reach P. From 5 we are directly coming on 3, from 3 we are going directly to 5. Now this node can be deleted. So take out the value and delete the node. X assign P's data, take out the data and delete the node. Delete P will delete the node. So this is the procedure for deleting a node from given position. So we have seen both the procedure, deleting first node, deleting a node from any given index. Now a little bit of analysis. How many extra pointers required? Just one extra pointer, P. In both the cases we have used just P. Here also we have used P, here also. If you read the code, you don't find any other pointer apart from P. Second one, analysis. This was constant. Now this depends on how much P is being moved. So this for loop, it depends on the for loop. This will move P. So it depends on the position. If the position is last position, so the time is maximum, say order of n. Or else if the position is second position, this node, then the time is minimum, that is constant. Means this loop will not execute at all, just these statements will execute if you are deleting second node. So that's all about insert. Now a complete function and using it in the program, I will do it as we are used to with the previous linked list. Now similar way, I will combine these and I will write it as a single function. In this video, we'll look at a function for deleting a node from Doubly linked list. So I'm continuing with the same program. This is the same main function where a linked list is created and it is displayed. Now other functions are already there which we have written in the previous videos. Now just I have to include delete function inside this program. So let us write delete function. Return type is int and function name is delete. It should take structure node to first pointer, let us call it as P, and we want index where we want to delete. Then for deletion, I may need temporary pointer. So like Q, I will take a temporary pointer. Then I may need a variable X, which I will initialize it as -1 as well as I. Then now the procedure starts. So the first thing is I should check whether index is less than 1 because the minimum index is 1. Then if index is greater than length of a linked list, so I will pass P or even I can pass first. If index is less than 1 or greater than length, then return -1 means index is invalid. Then next we should check if the index is 1. If the index is 1 means we want to delete first node. So it's a special case for deleting first node. Then the method for deleting first node, like P is already pointing upon first node, will be passing P as a parameter to this function. So I should move first pointer to next node. And if first is not null, like if first means it has not become null, then first previous should become null. Then I should take the value from P's node inside X, then free P, delete a node. That's all. So move the first pointer to the next node and make its previous link as null, then delete the node. So first node is deleted. If it is not first node, then I should reach the index where I want to delete a node. So using a for loop, I can move this pointer P to index -1 position I++. Then every time say P assign P's next. P will be reaching at an index where we want to delete a node. So P will be pointing upon that same node. Then as we have discussed on the whiteboard, so I have to modify the links. So I will modify the links first. That is P's previous nodes next should be assigned as P's next. That's what I have shown you. And then one more link I have to modify, that is P's next node's previous. So this I should do only if P's next node is there. If it is there, then only I should do this one. So then P's next node's previous should be assigned with P's previous. That's all. Both the links are modified. Then take the data in X P caps data, then free node P. Node P is deleted. The next is take the data from P's node, that is P caps data, then free P. P will be deleted. So this is what we have already seen. So I have completed the code. Then return the deleted value X. So delete function is completed. So the code is little lengthy because there are more than one cases. Now coming to the main function, I will delete first node and let us see what happens. Delete. First of all, I should point a pointer to the first node and the index is 1. So first node should be deleted, that is 10 should be deleted, and I should get the elements 20 to 50 when I am displaying it. So let us run. Yes, 20, 30, 40 and 50, these are displayed, so it means the element 10 is deleted. Then let us delete the last element, that is index 5, and again run it. Yes, 50 is deleted. Let us delete the third element, so 30 should be deleted. Yes, 30 is deleted. The elements that I am getting are 10, 20, 40 and 50. That's all, it's working perfect. Here I am getting a warning that this pointer q, actually I did not use q in delete function, so I will make it as comment. So that's all with the delete function. Let us look at some operations on a doubly linked list. Displaying a doubly linked list. With this, we will learn how to traverse a linked list. The next, we will also learn how to reverse a doubly linked list. So first, let me show you the procedure for displaying a linked list. For displaying a linked list, I should traverse all these nodes. So for traversing all these nodes, I should start from first node. Yes. Then for traversing the nodes, I should move to next node. How to move to next node? P is next. Then go to P is next, then P is next, P is next. And until P becomes null, I can continue this. So this is same as linear linked list. There is no change at all because I am moving only in forward direction. If you are not traversing all nodes, but you are moving in between the nodes as per the requirement, then you can use both the links. But suppose you want to scan through the linked list, then you have to go to next only. So for displaying a linked list, the code will be exactly same as the code for singly linked list. So let us see this. First of all, take P upon first node, P upon first node. Okay. Then do what? Print this one. So printf. Data is printed. Then move to next node. Move to next node. Then same way, go on repeating this. Print and move to next node. Print and move to next node until you reach null. So this can be done using while loop. While P is not equal to null. That's all. These steps will display entire linked list. So the code will be same as a single linked list, and for all the operations the code will be same only. Like finding maximum, finding minimum and searching, for everything the code, same code works here also. Just the node structure is different. Now let us see how to reverse a linked list. For reversing a doubly linked list, if I am reversing this node, then this previous should become 9 and the next should become null. So I will modify this. This should point on 9 and this should become null. So I have swapped the pointers, interchanged the pointers of 6. Now next was 9, but now previous is 9. Okay, take previous and go here. Now let's say P is here again. So let us continue and reverse a few nodes. Then interchange the pointers. So see, this is pointing on 6. So this should point on 3 because this is pointing on 3, right? So this should point on 3. Then this was on 3, let it point on 6. Interchanged. Then move to this node. Where is the pointer of this node? It's not in next, it is in previous. So okay, take previous and go there. Then again interchange this. So in this way, if I interchange all, so I have interchanged all of them. Now if I start from here, I have to say previous, then it's previous. So if I start from P, its next is this one, this node. Its next is this one, its next is, so that has become the first node. So I should move first to that node because that node has become a first node. So the procedure is very simple. Just scan through the nodes and swap the pointers. So I will write on the procedure. P should start from first node. P should start from first node. And I should repeat this procedure until P becomes null. While P. And what I should do every time? Swap. So for swapping, I have to take temporary pointer. So this is a temp assign P is next. Then P is next assign P is previous. And P is previous assign temp. After swapping the pointers, I should always move to next node. So next is already changed. So I should take previous node and go there. So P should move by taking previous node because links are already interchanged. So this procedure will be interchanging the pointers and it will be reversing the links. Then one more thing I should take care that upon the last node, first should be pointing upon the last node. So how do you say it's the last node? Its next is null. So if any node's next is null, when you have reached on that node first time and saw that its next is null, means that is the last node, bring first there. So I should continuously check that also. I will write on the code here. If P is next is equal to null, then bring first upon P. That's it. So this all goes inside loop only. So this is the procedure for reversing a doubly linked list. So that's all. I have shown only few operations on doubly linked list because rest of them are similar to singly linked list. That's all about doubly linked list operations. So we will see everything inside a program. In this video, we'll look at the demonstration for a function to reverse a doubly linked list. So already we have seen the board work and I have explained you the procedure. Just I'll write that function and show you. Let us write a function about this main function void reverse. Let it take a pointer to a node, that is first node. Procedure is very simple, just we have to scan through the entire linked list and swap their pointers. So for swapping, I should have one more pointer, that is a temporary pointer temp. Then using while loop, I will scan through a linked list while P is not equal to null, then swap the pointers. So first in a temporary pointer, take P's next, and then in P's next assign P's previous, then in P's previous assign temp. That's all. Now pointers previous and next are interchange. Now P should move to next node. So now the pointer is stored in previous. So P should move to previous node. So previous node will take it to a next node. Then on that new node, I should also check if that is the last node. If P is next, this node is not yet changed. If it is equal to null, means it's a last node. Then first pointer should be pointing on that last node P. That's all. So here already I have a main function which is creating a linked list of values 10, 20, 30, 40, 50. Then also I am displaying a linked list. But before displaying a linked list, let us reverse it. Reverse first. Send the pointer to a first. Now let us run the program. Oops, there's an error. See here, when it is reaching on the last node, there is no next pointer for the last node. Now P is null. So here I should add one more condition that if P is not equal to null and P's next is null, then change this one. So this is the extra condition. This I have not shown you on whiteboard. So extra condition I should add because before checking P's next, I should make sure that P is not null. Let us run the program once again. Yes, linked list is reverse 50, 40, 30, 20 and 10. So the elements that we have inserted in a linked list while creating a linked list, those elements are reversed now. That's all. You can try this function by yourself. In this video, we'll learn about circular doubly linked list. This is a doubly linked list and also it is circular. That is, this first node or head node is pointing on the last node or last node is pointing on the first node. So these are a collection of doubly linked nodes which are circularly connected. So already we saw circular singly linked list. This is doubly linked list. So the benefit of this linked list is you can access in either direction, bidirectional, as well as circularly we can access. So far we have seen various types of linked lists. Comparisons, we will do it in some other video. So let us learn few things about circular doubly linked lists. So this is basically a doubly linked list only. So I don't have to explain much. I'll just give you few important points and rest is a student exercise. So let us look at some operations. Like first of all, I want to traverse this. So for traversing, I may be starting from head node. Then I can go to next and next and next node and next node. And again, if I say next, I'll be upon head. So how we have handled singly circular linked list? Same way we should handle it. We have to scan it, all the nodes, and once we reach to head once again, then we should stop. If I want to display linked list, how the code should look like, let us see. I should take a pointer upon head node. Then for printing, print the data, move pointer to next node. So printing and moving, I have to do it repeatedly using do while. Do while P is not equal to head. So if you remember, in a circular single linked list also we have used do while loop because using while loop it was not possible. So the same thing we have to do here also. Now rest of the operations are similar. Now let me tell you the few important things related to insert operation. So let us look at insert operation. If I want to insert any node at a given position, let us say this is first node, second node, third node, fourth node. I want to insert a new node after fourth node. Then the procedure is same as how we have inserted in a doubly linked list. That is, bring a pointer upon this node, create a new node, fill the data, make this point on this one and this previous point on this one. So this next should point here and this previous should point here. So 4 links I have to modify when I am inserting any node at any place. So the procedure is same as doubly linked list procedure. Then how about inserting a new node before head node? So for this, I should take a pointer and create a new node and fill the data here. Then what are the modifications I have to do? In a doubly linked list, I was supposed to, in a doubly linked list, we were making only 3 changes. These 3 links were changed. But here I have to modify this last node link also. Instead of pointing on head here, it should point on this one. So this is the change I have to do. So it means I should modify 4 links. So yes, the important thing here is wherever you insert in a circular doubly linked list, you have to modify 4 links. So let us see how I can do that and how much time it takes. This should point on head and this should point on heads previous, means that node 8. So I will draw a link from here. So how I can get the address of that node? Do I have to traverse the whole linked list? No. I can say heads previous, that is heads previous. So I can get the address of that node in constant time. But I don't have to scan through this linked list and reach there. That's the important point here. If you want to reach that node is actually, we are calling it as last node. So we can also call it as a node previous to head node. A node previous to head node. Because if you take a previous pointer, you will get the address of that node. So that you can get it in constant time. So for adding a new node before head node, the time will be constant because you don't have to scan through the linked list for reaching that last node. I will complete other links also. So this is pointing on this one and the previous is pointing on that node, and heads next, this should be pointing on this node, and this 8, how I can reach on that node? T is previous, already I have a link there, so that should be pointing on T. So now you can see that from T I'll be going to this node 6, then 6 to 9, 9 to 2, 2 to 7, 7 to 8, 8 to again T. So yes, this is connected circularly. So how much time it has taken? Just create a node and modify the links. So the time is constant. So if you are inserting a new node before head node, time is constant. And one important property we learn is that to go on that node, we don't have to scan through the linked list. Just take a previous pointer and you can go there. That's all. Similarly, you can try out delete operation by yourself. I have shown insertion operation. That is sufficient. Delete, you work out on it. It's very easy. Then few more important things I'll tell you. If suppose there is a single node head, there is a single node. Suppose the value is 6. Then how it should look like? This next should also point on itself. Previous should also point on itself. So then it is circular doubly linked list. And if there is no node at all, then linked list is empty, then it should be null. If you remember from circular single linked list, there the problem was if it is null also we wanted it to be circular. So if that is the case, then you should have one more dummy node, that is head node, empty node. So anyway, I don't want to include that one here. So this topic remains as an exercise for you. So you prepare the complete code for all the operations on this one. So basically main important operations are insert and delete, complete insert operation and delete operation. These operations you must write down complete code. So what are the cases? Inserting before head or inserting after any other position, all those cases you should take care. So that's all about circular doubly linked lists. So in one of the coming videos, I'll compare all the linked lists and I will discuss the advantages and disadvantages of those linked lists. In this video, let us compare various type of linked lists that we have studied. So here are various type of linked lists we have seen. This is linear single linked list. So every node is having just a single link. Then circular single linked list. So this is single link, but also it is circular. Then a linear doubly linked list. So this is linear, but two links are there. That is on the next as well as previous. Then this is circular doubly linked list. So this is doubly as well as circular. Two links are there as well as we can access it circularly. So we'll compare them based on this criteria, that is space and the insert, delete operation and traverse. So we'll compare these. So first thing about space. Which type of linked list takes more space? See, this is for data and this is a link. So along with the data, it's also taking a space for storing the address of the next node. So here 4 nodes are there. So it means I can store 4 values. Along with values, 4 pointers are also required, which will store the address of next node. So for 4 elements, 4 extra pointers. For n elements, n extra pointers. What about this? Again, same n extra pointers. But these two linked lists, if you see, they require 2 pointers for each node. So 2n extra spaces are required. 2n. So now we should count this 2n, double the space. So I can say that doubly linked list takes double the space of pointers required in singly linked list. Double for pointers only, not for data. So this is about the space. Then let us talk about traversing. First, traversing. So we can move only in forward direction. We can move forward as well as circular direction. We can move in either direction. This we can move in either direction as well as a circular direction. The next about insert and delete operations we will discuss. We have already seen all of them. So if we take insert operation, in all these linked lists, inserting before first or before head is a special case and inserting at any other place is a common case. Now inserting before first in this linked list takes order of 1 time. And here it takes order of n because we have to modify this link also and we have to traverse. And inserting before this side takes order of 1 time, constant time. And inserting before this one takes constant time. Though we have to modify this one, but we don't have to traverse this, we can directly go from here and modify it. So it takes constant time here. So only in this linked list, that is singly circular linked list, if you are inserting on the left hand side, time is order of n. Then how many links are modified when you are inserting on the left hand side? Here only 1 link, that is a new node will be linking. Here 2 links, new node will be linking as well as this node will be pointing on new node. Suppose there is a new node, that should also point on this one. So 2 links are modified. Here 3 links are modified. New nodes 2 links as well as this link. Then here 4 links are modified if you are inserting on the left hand side, that is before head node. Next, let us talk about inserting at any other position. So inserting at any other position takes minimum constant time, maximum n time. And the procedure there and here is same. Inserting here is constant, inserting at the last is order of n. And here also same. And here also same. So in all these linked lists, the time taken for inserting at any other position is same. But what about links? When you are inserting here, we have to modify 2 links. If you are inserting, we have to modify 2 links. and here we have to modify 4, and if we are inserting after last node, only 3 links are required. As I said that there is no node beyond, so you don't have to make it point on this one. Like if I am inserting here, then this should also point. If I am inserting here, there is no node to point on this one. So only 3 links when you are inserting at the last. But here, always 4 links. So this is about insertion. Let us talk briefly about delete, because most of the things came under insert only. Delete. Again, for deleting head node case is different, and deleting any other node case is different. Let us see deleting head node. If you're deleting this node, then simply you have to move first and delete the node. No links are modified, time is constant. Deleting this one, we have to make this last node point on this one. So this change needs, for changing this, you have to move till here. So it's order of n. So here deletion of this one is constant, and here deletion is order of n. And here deletion again constant. And here deleting this node, we have to move ahead and modify that node also. So we can go from here and modify it. So it's constant. Only in this linked list, head nodes deletion is taking order of n time. Otherwise, in any of the linked lists, if you are deleting head node, time is constant. Next, how many links are modified? When you delete this, no links are modified. Just we have to move first pointer. Here, we have to modify 1 link when you delete head node. Then here, if you are deleting 1 link, you have to modify this, we have to make null. Then here, we have to modify 2 links. That is, we have to make this one point on this last, and last should point on this one, because this will be a new head. So 2 links are modified when you are deleting head. Next is deleting from any other position. So the time taken for deleting a particular node, the minimum time is, if you are deleting this node, constant. If you are deleting any other node, it depends on its location, that is order of n. So here also same thing, here also same thing, here also. In all, deleting a node from given position takes order of n time, minimum 1, maximum n. Then what about pointers? If you delete a node, we have to modify this link. If we delete a node, we have to modify just 1 link. So 1 link is modified when you are deleting a node. Then here, if you are deleting a node, this one, then we should make this point on this one and this one point on this one. So 2 links are modified. Then here also, if you are deleting a node, 2 links are modified. But in this linked list, if you are deleting last node, then you don't have any node on that side, so you don't have to modify 1 link. So only 1 link is required. Minimum 1 link will be modified when you are deleting any node from any given position. Now one more point I will discuss about deletion. If I am giving you a pointer already upon this node, on this node, suppose there is a pointer pointing here, how much time it will take for deleting this node? So for deleting that node, just I have to make it as null and delete that node. So yes, it is constant. So if you already have a pointer, you don't have to bring it from here, then the time is constant. But what about if a pointer is pointing here and you have to delete the same node? How much time it takes? Same node means I should modify this node. Now for this, I should come from the beginning again. So randomly on some node, if a pointer is given, how much time it will take to delete that same node? So for that, I should modify previous node. So the time is order of n. It depends on the position that you are giving. This is one thing. Now in this doubly linked list, if a pointer is given here, how much time it will take to delete that same node? So I can go to previous and make it point on next, and go to next and make it point on previous. So being on that same node, we can change the pointers and delete the node. So time is constant. So with this we can understand that here being on the same node, we can modify both the pointers, but here being on the same node, you need to modify previous node point. Now last thing, which linked list we should use? It depends on your requirement. If you have to access data one by one and you don't have to come back to any data, then you can use this singly linked list. For example, if you are implementing queue, so you'll be going to the next and next and next. So you will be accessing next node every time, so you don't have to go back. So you can use singly linked list. And if you want to access circularly, then you can use this one. Then again, this is the benefit of this one is bidirectional. This is bidirectional and circular. So this is a final linked list which is having all possible features. You can move in either direction, bidirection, as well as you can move circular. So this is perfect linked list, that is circular doubly linked list. So what I say that the best linked list is this one, but it takes extra space, memory space for the pointers. If you are worried about the pointers and you think that that is taking a lot of space, then go for single link. No, I have to move in both the direction, come back again here. I don't want circular, then go for this one. Actually this is taking and actually these two are taking same space. So there is no meaning in having just a doubly linked list, not a circular. So a doubly linked list, if you have, you can make it circular. So doubly circular linked list is best. So you can always use that. If I talk about languages like Java, it provides built-in classes for linked lists, and that linked list is this one. So Java doesn't have classes for all type of linked list. Though C++ STL, there is a forward list that is single linked list, and there is a list that is this one. But in Java, there is only one linked list, that is circular doubly linked list. Because nowadays space is not an issue, so we can go for this one. If in any system, if you are making it for any device with a limited memory, then you can think of space and you can go for the single linked list. Now what I believe is that in academics, we learn about this to get the idea about what is linked list. Then we learn this to, okay, we can make circular also. We learn one extra feature. Then we learn one more feature and say, okay, it can be accessed bidirectionally also. Okay. Then finally we see this one, that it is circular also and bidirectional also. Directly if you see, this is a little confusing. So that's how, if after crossing all these, this becomes damn easy. So that's how in academics it is covered like this. So we are used to with this one. But actually based on the requirement, you can go for any one. Now if you're using language like Java, you don't have any option. You have to use this one. So I say that if memory space is not a constraint, you can blindly go for this one. So that's all about comparisons of linked list. In this video, we'll compare array with linked list. Basically, these are two physical data structures. In the beginning videos, I have explained that there are two physical data structures, or we can use combination of these two data structures. So basically two physical data structures, array and linked list. So using these data structure, we implement other logical data structures. So let us compare them. First thing, where they are created in the main memory. Array can be created inside stack as well as it can be created in heap. Linked list, it is always created in heap. There is no meaning of creating it inside stack. Next, let us compare their sizes. This size is fixed. Once you created an array, you cannot increase or decrease the size of same array. You have to create another array. Next, linked list is in variable size. You can grow as much as you want. As much as heap memory is available, it can grow. When heap is full, then you cannot grow further. So this is fixed length and this is variable length. Next, advantage and disadvantage based on length. This is in fixed size, so the chances of getting perfectly utilized is less. Either it may be having some spaces left over, or it may not be sufficient for storing all the elements. So this should be used when you are sure that you will not get the number of elements more than this size. So if you know the maximum size, then create an array. It may be wasting spaces if you are not storing it fully. But linked list, when you don't know what is the length, you can go on creating nodes and go on adding it, and also you can go on reducing it. So when you're not sure how many elements, the list size, what is the size, then you can go for linked list. Then about space consumed. See, this will occupy space only equal to the size of the data. Suppose these are integers. This is the space for an integer, But here, this is the space for an integer, this is a space for pointer to the next node. Space for integer, pointer to next port. So inside every node for every data, there is an extra space required for storing the link of next one. So linked list takes extra space. Next, accessibility. This can be accessed randomly. Suppose I want to access something here. I can say A of 6 and I can access it. I can say A of 3, I can reach here. A of 9, I can reach here. But this can be accessed sequentially. If I have to access something here, then I should start from first and go on moving and reach here. If I have to access something here, then I should start from first and go on moving and reach here. Next, faster access. Who is a faster access? This is inside the stack, it is faster. Inside heap, two-step access, indirect access. This is always inside heap, so this is always indirect access. And also, this is random and this is sequential. We already discussed that. Now next, insert and delete operation. So for that, I will fill up few elements and then we will discuss about it. Let us talk about insert. If I am inserting any element here at this side, so I should say inserting from right hand side. So it takes constant time. Just I have to write on the element. If I want to insert any element here, then I have to shift all the elements. So it means, let us say we are inserting from left hand side, from this side. So for shifting elements, it takes time. So it's order of n. So inserting that side is 1 and inserting this side is n, right? So this is minimum to maximum. If you insert here, it's n. So a little less than n, but still we say n only, right? But here always here means always constant. Let us see here. Let us look at the linked list. Inside linked list, if I want to insert here, just create a node, link it and move first. So this is constant. If I am inserting on the left hand side. If I want to insert something here, then I should move pointer P and bring it on some node, then I can insert a new node. So if I am inserting from that side, so let us say right hand side, then the time is order of n. Order of n. Here it is 1, there it is n. Because I have to traverse through this linked list, then I can insert it. Here I have to shift the elements, then I can insert an element. So that side 1, this side n. But here this side 1, that side n. So if I talk about who is which, if I say insert operation is efficient on which data structure, so it is same. In array, shifting of elements. But in linked list, movement of pointer. So the time this side is 1, there it is n. There also we have 1 on that side, n on this side. Now it depends from which side you want to insert always. If you are inserting always from right hand side, then array will be faster. If you are inserting always on left hand side, then linked list will be faster. But one more important criteria. See, there is no shifting of data involved here. Shifting of data is involved here. You have to shift the data. So my data is integer. So 2 bytes, if I am assuming that integer is taking 2 bytes, right? So 2 bytes. If it is a double, then 8 bytes. If it is a student record of 200 bytes, then 200 bytes. So this is costly. Movement of data is costly. Here there is no movement of data. Then when it comes to data movement, this is better than that one. Because of shifting of the data, the time is more there, and otherwise they are equally efficient, only the sides are different. Now let us see delete. If I am deleting something from this side, delete 2, only the length of the list will be reduced, length of an array will be reduced. So it is order of 1. If I am deleting 8, then I should shift all the elements this side. So again, it is order of n. So deleting from this side is order of n. So insertion or deletion both takes order of n time here, and insertion deletion both takes order of 1 time here. Then come to the linked list. Deleting this node. Deleting first node, constant time. So same time, I don't write it again. Then if I want to delete this one, so first of all I should reach this node, then I can delete this one and modify this link to null. So if I am deleting this, then it is order of n. So it means if I am deleting from that side, then it's order of n. From this side, it's order of 1. So as far as I am going, the time will be more. Okay. Here, as far as I am going from in this direction, the time is more. If I am going that direction, time is less. Here, that direction is more. This direction, it is becoming less. So only the direction is different. Otherwise, the time taken for deletion is same. Both are equally efficient if data is not an issue. If data is larger, then here shifting of elements will take a lot of time, and there is no shifting involved here. So this is better. in terms of data movement. The next, searching. See, upon array we can perform linear search as well as binary search. This takes n and this takes log n. But in linked list, we can perform just linear search which takes order of n. We cannot perform binary search. If we perform, then it will be taking n log n time. So we say binary search will be inefficient upon linked list. Reason, binary search means the elements must be sorted and we should go in the middle of a list. We know it well, right? We should go in the middle of a list. So when you are going in the middle of a list here, directly you can go. If I want to go into the middle of this list, so 0 plus 5 by 2, that is 2.5, floor value is 2, so I can go on to index 2 directly. But here going in the middle means I should scan through all the nodes and go in the middle. So this movement needs n time. Here it is faster because directly we can go in the middle. So always in the middle means log n time. So here also we will go always in the middle, log n time. But to reach middle, we have to start from first. So it's n. So it will not be log n, it will be n log n. So we say binary search we can perform. But binary search is famous for its log n time. But it will be more than that. So we say we can't perform binary search. We did not learn anything about sorting. But one thing I want to tell you, most of the sorting methods are designed for array. Some of the sorting methods are designed for linked list. So sorts, insertion sort and merge sort, they are designed for linked list. They are more friendly to the linked list. They are suitable for linked list. So we have this topic. We will learn about this one. That time I'll explain you how insertion sort is friendly with the linked list. They are suitable for linked list. We will see that later. So that's all. I have compared array versus linked list. Now who is the winner here? Depends on the requirement. Depends on the requirement, right? If a space is the issue, this is better. Faster access, this is better. Variable length, this is better. Fixed length, this is better. Data is large, we don't want to move, this is better. We are always inserting from left side, this is better. Inserting always from right side, this is better. There are many things that decides. So you have to select the data structure carefully depending on your requirement, right? So study how you are going to use the data structure in your application. Depending on that, you select the suitable one. So I have compared them on various criteria that will help you to decide which data structure to use. So that's all about comparison of arrays and linked list. The topic is finding middle node of a linked list. We want to reach on the middle node. See, as an example, I have taken 7 nodes in a singly linked list here, and this is the middle node. 3 nodes on this side, 3 nodes on that side. If suppose there are only 6 nodes, like this node is not there, assume this is not there, there are only 6 nodes, then which is the middle node? Now, either I can stop on 3rd node or 4th node, right? Any one node I can stop on. Because if there are even number of nodes, there is nothing like middle. So either 3rd or 4th, if in a 6 nodes, if you have to find the middle node. Now, what should be the procedure for reaching middle node? So there can be more than one solutions. First solution, find the length. We already know how to find the length of a linked list. We have already seen the procedure. Once you know the length, suppose the length is 7, then reach on middle node, right? Reach to mid node. So which is a middle node? 7 by 2. So this will be 3.5. So we can take it as a seal of 7.2, that is 4th node. So I can take a pointer P upon the first node and move it for 4 minus 1 times. So 1, 2, 3. So 4 minus 1 is 3. So reach till here. So actually I have to reach on 4th node. So this is the 4th node. 4th node means move P for just 3 times. So 4 minus 1 time. If I move the pointer for 4 minus 1 time, then it will reach there. This is one method. So I will not show how to do this one. You know it very well. Just I am discussing the method. See, in this method, first of all, I have to find the length. Then afterwards, I have to take a pointer and move it until it reaches the middle node. So I have to scan the linked list 2 times. No, I want to do it in a single scan. Single scan. How to do it? So let us see the second method. So for finding a middle node in a single scan, we will take 2 pointers. So already we have learned the concept of tailing pointer, that one pointer is there and behind that we will have one more pointer. So for that I will take 2 pointers. Let us call first pointer as P and the second pointer as Q. Now one pointer will move it 1 node at a time, and second pointer we will move it 2 nodes at a time. So let us say P we will move by 1 node and Q by 2 nodes. So in this way, by the time Q reaches the last node, P will be in the middle. So because the distance traveled by P will be half of Q. So let us do it by taking 2 pointers. So already I have taken 2 pointers P and Q. How to do it? Let us do. So first move Q for 2 nodes. 1, 2, 2 nodes. Q is not null. So move P also 1 node. Then again move Q for 2 nodes. 1, 2. So Q is here. Now Q is not null, so it has not reached end, so move P also. Then move Q for 2 nodes, 1, 2, so Q is here. Then move P by 1 node. Then move Q by 2 nodes. So first node itself Q becomes null, so we cannot move further. Then move P. Shall we move P? No, Q became null, don't move P. So it means we are on the middle of a linked list. So by using 2 pointers we can do this. So here I have 7 nodes. I'll do it again by taking 8 nodes. Just watch it. Now I have added 1 more node to a linked list. So total there are 8 nodes. So middle node means I should stop at 4th node. So let us see, will it stop at 4th node or not? So 1, 2, 3, 4th node, right? Then 1, 2, 3, 4, 4 nodes that side. Let us run the procedure. Move Q by 2 nodes. Okay, Q is here. Then move P by 1 node. Move Q by 2 nodes. 1, 2. Then move P by 1 node. Move Q by 2 nodes. 1, 2. Move P by 1 node. Right? Then move Q by 2 nodes. 1, 2. So Q becomes null. As Q has become null, we are not moving P. I already told you. So don't move P. So Q became null, then stop. P is on the middle of a linked list. So this is the procedure for finding a middle node in a single scan. So this can be done by using 2 pointers. Right? Now one thing I would like to show you, that in the previous method, first method, we were first finding length. So just like Q, then we were reaching the middle of a linked list by using P. So same amount of work is done. So amount of pointer movement is same, but only the difference is previous method was not in a single scan. This is in single scan, right? In the previous method, first we perform length, 1 scan, then second half of a scan. But here 2 are done simultaneously. That's it. That's the difference. So if I write the program code for this one, this will be in a single loop. Like P as well as Q, they will be starting at first, then while Q, means while Q is not null, because who will become null first? Q will become null first. Then what to do? First Q assign Q's next, right? Q will move to 1 node. Then if Q means Q is not null, then Q assign Q's next. So this is the second movement. Then if Q means Q has not become null, then P assign P's next. So Q will move for 2 times, P will move for 1 time, and P will move if Q has not become null. So this loop will make P point on the middle node of a linked list. So this is a simple code. Now next, analysis. How much time it takes? It takes order of n time. Why? We are just scanning through a linked list once. That's it. So the program code you have to write down. I will not show you the demonstration of this one. You can take a linked list. Already we have programs for creating a linked list. Just you have to write on this piece of code as a function you can write, as well as you can write the same thing inside main function and check it. So after this you can display a node, right? So you can display a node to confirm whether P has reached the middle of a linked list or not. So you can print P's data. So you can know where P is pointing. Is it a fourth node of your linked list or not? So by printing this you can know. I'll show one more method using a stack. I'll remove this. Now third method, I will take a pointer P upon first node and I will take a stack. Now I will scan through this linked list and each node I will put it inside the stack. So I will put the address of a node, that is 100. Then P will move to the next node, so 110. Then P will move to the next node, it's 130. Then P moves here, right? P is here, so P 150 is inserted. Then P is here, so 200 is inserted in the stack. Then P moves to next node, so 220 is inserted into the stack. Then P moves to next node, so 240 is inserted into the stack. Then P moves to this next node, so 260 is inserted into the stack, right? Then P becomes null, so stop. So we have scanned through this linked list and every address I have pushed it into the stack. I'll complete this one, right? So what is the size of this stack? We can know the size of the stack. 1, 2, 3, 4, 5, 6, 7, 8, right? So 8 by 2. So we want a middle node. So 8 by 2, if I take seal value, then I get 4. So simply pop out 4 nodes from the stack. So 4 addresses, 1, 2, 3, 4. So this is the address of the middle node. So let us try it for 7 nodes. If 7 nodes are there, then I should pop out 3 nodes from this one. Then 4th node will be yes. So I should take it as floor, not as seal. So this also it should be floor. So for 8, floor or seal is same thing. So how many nodes I should pop out is floor number of, that is 8 by 2 or 7 by 2. So if I pop out 3 nodes, then 4th node, that will be a middle node. So this is another method. So take all these addresses inside the stack, then pop out half of the stack, then middle node will be there. So again, this is not using single scan, but we are scanning a linked list only one time, right? But the rest of the process is outside the linked list and it is inside the stack. So we can say we are scanning a linked list only one time, right? So we are getting the addresses from the stack. So this is another solution. So what is the time taken by this one? Time taken is same thing, order of n. Then half of the elements are pop out from the stack, so that's also n, right? Or n by 2, so it is n. So total amount of work done is n plus n by 2 also if you take, it is order of n. That is linear. And one more thing, for writing the program for this one, we should have a stack of linked lists, that is nodes type. So these are all pointers to nodes. So you should take a stack of nodes and you can fill the addresses of the nodes in the stack. So try to write on the program. Anyway, in the coming sections, I may be showing a stack of addresses. So that's it. So you have to implement this one. You have to write on a program for this one. The topic is finding the intersection point of two linked lists. If suppose the two linked lists are having some common collection of nodes, like here in the example, this linked list is having these 8 nodes and this is having 7 nodes. So these 4 nodes are common to them. Like this node is pointing on this one, so this portion of a linked list belongs to this linked list also, second linked list also. So those set of nodes are common. We want to find out the starting point of common nodes, that is intersecting point of two linked lists. So how to solve this problem? This is a single linked list. We can just move only in forward direction. We cannot move in backward direction. Shall we start from here? If we start from here, then how we should move? Shall we move one node at a time? One node at a time. If we move one node at a time, then this is having less number of nodes. We'll reach that intersection point early. and this is having more number of nodes. So from here you cannot trace from this side, right? How can we know that both are? See, at a time if you are reaching on the same node, then you can see that okay, this is the same pointer. But from this side, we cannot reach at the same time. But from that side, if you come backward, you can reach. Let us go to the end of the first linked list. Okay, reached. Then let us go to the end of a second linked list. Yes, reach. Now come backward, come backward. Now this is the point. Till here we will get same addresses. The next node's addresses will be different. So once you get a different addresses, you can say that the previous one was a intersection point. Yes, this is a procedure. Yes. So the procedure is we have to find the intersecting node by traversing from backward. How you can traverse from backward? We cannot do that because it's a singly linked list. We can move only in forward direction. Then how it is possible to traverse backward? It is possible using stack. Yes, it is possible using stack. So when you cannot traverse backward in a single linked list, stack will help you to get back the previous node addresses. So yes, let us see the procedure how intersection point can be found by using two stacks for two linked list. So I'll show you the procedure. Just watch the procedure. See, take a pointer P upon first node of a linked list, then scan through this first linked list and go on pushing the addresses of these nodes in the stack. So I will go on simply writing the addresses because we already know first is 100, 110, 130, so on. So I will write down 100, 110, 130, 150, 200, 220, 240, 260, 200, 220, 240, 260. So by taking a pointer upon the first linked list, I have gone through all the nodes and have pushed their addresses. Now I will take a pointer P upon second linked list, then I will scan through all these nodes and take their pointers and push them into this stack. So let us start. 300, 310, 330, 330. Then next after this 200, 220, 240, 260, 200, 220, 240, 260. Now I have two stacks filled with the addresses of the nodes of two linked list. Now from the back side I should check from where the addresses are changing. So I'll do it by popping out the addresses from the stack. Now let us start popping out the addresses. Pop out one address. See, both the addresses are same, so delete them. Yes, so it means we are coming from last nodes backward, right? Now these two addresses are same in both the stack. Pop out. These two addresses are same. Pop out. These two addresses are same. Pop out, right? And whichever the last one you are popping out, try to maintain its copy, right? So the last address we have pop out is 200, right? So always first 260, then 240, then 220, then 200. So the recent one you have to maintain. The next address, check them. Oh, they are different. So from here, the linked lists are different, right? So what was the last node having a common address? See, this was. So what is the intersecting point of two nodes? This is the intersecting points of two linked lists. So that's how from these stacks we can find out which is the intersection point of two linked lists. So if I do analysis, the time is order of n nodes and n nodes, so total time is n plus n. Then if you ask, we are deleting the elements from the stack also, so okay, include that n also. Total 3n, so it is linear actually. So I'll remove this and show you the program code. Let us write the code for this one. See, first of all I will scan through this first linked list and I will push the addresses of all those nodes in the stack. So for that, let us take pointer P pointing upon first, this one, and I should scan through this entire linked list. So I should say while P, that is P not equal to null, or even I can say just P, while P, what I should do, push into the stack. Let us say stk is a variable of type stack which can store the addresses, and I have to push P. So this is called by address, right? So I have written it in a single line. Now same pointer P I will utilize for second linked list also. So P assign second. Then while P is not null, I should push all these addresses. So while just I will say P while P and push into second stack. So let us call it as STK2 and I will push the addresses of nodes P. So let us change this name as 1, STK1. So this is stored in stack 1 and this is stored in stack 2. Now I have to pop out the addresses from the stack as long as they are same. And once I get a different address, I should stop. So let us write down here while I should check the topmost element of a stack. So I will have a function called stack top, and I will pass first stack, that is STK1, right? And this stack top value, I should continue as long as they are equal. So if it is equal to stack top STK2, so this is STK2. So as long as the topmost element from two stacks is equal, I should go on doing it. What I should do? Pop out the address from two stacks. So here I will write down, I'll take a pointer P and I will say pop from ampersand stack 1 and also in the same line I will write just pop out an address from address of stack 2. So I have to send it by address, right? So stacks I have to send it by address. So this is ampersand STK2. That's all. See, this loop will pop out the addresses from both the stack, right? Pop out from stack 1, pop out from stack 2, and any one of the value I can take it in pointer P. So pointer P will be having the last node deleted from the stack. So this will be checking and it will stop if the addresses are different. So the last address that is popped out will be in variable P. So P is the intersecting point of two linked lists. And if you are preparing these two linked lists, then you can print, at last you can print this one, printf %d P's data. If you print this data, then you should get this intersecting point of two linked lists. Loop. After the loop you can print. So that's it. This is the program code for performing this procedure. So in this one you should be ready with these functions like push and pop and the implementation of stack, and that stack should be storing the addresses of these nodes, right? We have already seen the stacks which are storing integer type of values, but now you have to store the addresses. So you have to write down the program for this one, implement this program. That's it.